Nimisha,
Yes,
please.
sir.
Please.
So we are moving to the technical session 2 of the second day. It will be chaired by Dr. Deepa Janardhan, who is specialized in computational chemistry. Currently, she is the assistant professor in Department of Chemistry, Central University of Kerala. I welcome ma'am to chair this session.
Thank you, Nimisha. First of all, let me thank the organizers for giving me opportunity to chair the session and introduce the renowned professor, Professor Ramasamy, P. Ramasamy, who is a professor and chair of the computational chemistry from the Department of Chemistry, Faculty of Science, University of Mauritius. So, Sir Professor Ramasamy has, after completing the MSc and PhD chemistry from the University of Delhi, actually he obtained his PhD in physical chemistry in 1996. After that, Sir joined after the postdoctoral researches. He is a visiting professor. He has a visiting professorship of several universities like the King Saudi University, University of Johannesburg, University of South Africa, and several other renowned places. Sir is a fellow of Royal Society of Chemistry also. He has worked as a initially joined as a lecturer in chemistry and then promoted to associate professor, and then currently he is a professor and chair of the computational chemistry group. He has authored more than 230 research publications in the international peer review journals. He has guided several PG, MPhil, and PhD students. He has also many number of several funded projects. Sir's research area is in the computational studies on molecules and clusters, mainly the structure and spectroscopic properties, reaction mechanism, calculation of activation barrier and thermodynamic properties, rate constants, etc. So his group is also exploring these computational studies and then the novel products that is not yet synthesized, but we can predict using the theoretical predicting power of the computational tool. So he is using that tools for predicting the molecules and clusters. Today's research talk on the computational chemistry methods as applied to solid state. So more than 25 years teaching experience, Sir has also got the best teacher, best scientist award from the Mauritian Scientist Award in 2016. And he is also a scientific board advisory member of the Organization of the Prohibition of Chemical Weapons. And he is an excellent teacher, so of the having so much teaching experience. So I am sure that our students are going to benefit greatly from the Professor Ramasamy. So with this short introduction, I invite Professor Ramasamy to deliver today's talk on computational chemistry methods for the solid state.
Thank you very much, Madam. I hope that I am audible to the participants.
Yes, sir, you are audible.
Thank you. So very good morning to everyone. I am Ramasamy from the University of Mauritius. I am also a visiting professor with the University of Johannesburg and University of South Africa. So first of all, I would like to thank you, Madam, for the kind introduction and the organizers for inviting me and holding this online meeting. And I'm pleased to note that there are many participants, and from what I can understand also, there are many young scientists. Well, today I will be talking about computational chemistry methods as applied to solid state chemistry, to solid state science, right? But then, well, I didn't know about the background of the participants. So I will try to go about the way that is really from the basics, what common mistakes that most probably may be done, and how possibly to rectify these mistakes. So, because don't forget that there are many things that we can really learn based on the mistakes that we are doing or others are even doing, right? But before I really start with my talk, allow me to go for a certain back history of it. So I hope the change of the slide is okay. Can you see the change of the slide?
Yes, sir.
Yes, sir.
Perfect. Right. So if there is anything which doesn't go right, don't hesitate to stop me. So I always like to keep this slide because, you know, there is always a confusion, right? Where is Mauritius? Because just before joining this talk, I received an email from someone who said, how are you? You are fine. I'm looking forward to visit Malaysia with my family. But, you know, so there's a confusion between Mauritius, Malaysia, Mauritania, and so on and so on. But, well, Mauritius is a very small island in the Indian Ocean, right? So for those who are not aware of it, but it's always good to keep this slide. And whenever I'm giving a talk to like participants from India, I also like to keep this slide for a good comparison. It's always like to compare Mauritius and Mother India. So in Mauritius, India is basically known as Mother India, right? So in terms of the area, right? So you can see that Mauritius is almost 2,000 kilometers square, whereas you can realize the size of India, right? So this will be almost 3 million kilometers square, right? Now, in terms of population, so Mauritius has a population of 1.3 million, whereas the figure is almost the same for India, but of course the unit is different, right? So we are talking from million to billion, right? So I think this gives you an idea about the type of research, the type of things that might be going on in terms of the education and so on. So I think this pathway, this background is also very important for you to get into before really going into the actual science that I'll be talking today. Now then, some pictures of Mauritius. I always like to do it the reverse. I see that many speakers, they talk about the science and then Mauritius and their country. I like to do it the reverse. I give an idea about where we are and then get into the subject of what I'll be talking today. So Mauritius is, well, it's like I said, it's an island in the Indian Ocean, and then it's quite famous for like three things: the sun, the sea, right? And you can see now, for example, you have the beach and the sun. But unfortunately now with the pandemic, you have the tourism industry, which has been badly affected, right? And now this one, it's a crater, right? So this one is a crater, a volcano, right? It's supposed to be a dead volcano, but some scientists saying that's a dome at one. So, but I really hope that it's a dead one, because if it is dome, and the day that it erupts, Mauritius will disappear, right? And this is a Lemon Mountain, which is now officially recognized by UNESCO, right? And why it is now recognized by UNESCO is because when slaves, they were trying to escape their masters, they were hiding themselves on the mountain, but then when their masters came to look for them, they jumped to death, right? So this is the issue. And so this is a slide about Mauritius. My next slide is about the University of Mauritius. So it might be good for you to know that, of course, I don't know about your university, but in Mauritius, basically, we used to have only one public university in Mauritius. So many years back, there was only one university. But now, basically, there are some, I think, 4 or 5 public universities, although you have so many private universities. Now, the University of Mauritius, if you see this building, which is down, right? So this is the building which was there some 50 years back, where the research was only focused towards agriculture. So you might realize that there's a reason for that, because Mauritius was dependent on agriculture at that time. And therefore, there was a focus on having university education in the agricultural sector to promote research for sugarcane and so on and so on. But over the years, diversification has taken place, and now we have a full-fledged university with all the different faculties. I can tell you that we have almost 10,000 students across all the faculties and about 1,000 academic staff. But then, if we come now to the Department of Chemistry, so we have about 300 students ranging from the undergraduate to the postdoctoral level. We have 10 academic staff. And myself, I lead the computational chemistry group. So you might see some of the computers that we have here, but these are not the computers that we really use for doing the computations. We really use these as terminals to connect to high performance computing facilities, right? I may tell you that when I joined the university some 20 years back, almost now, there was no computational chemistry, right? So I initiated the whole thing at like teaching level, and then I moved on to research and so on, and we have a full-fledged group, right? Now, if you see in terms of, I will not go into it, this is a timeline with respect to the computational chemistry group when I started in the year 2000, right? And now, if I'm not taking it for this year, so I take it till the end of December 2020. So we have 1 postdoctoral student, 2 research assistants, 8 MPhil PhD students graduated, 5 MPhil PhD students currently working, 3 MSc students, and 5 BSc students. At that time, we were almost 230 publications, right? So I think this gives you an idea about the background of the group, right? And what we are really, and what we have done, and most probably what is the nature of things that are really going on. Now, I think now let me come to the purpose of the talk that I have today, right? So I'll be talking a bit about computational chemistry. Then I will make a reference to the solid state, the research that are really going on in the group, our future plans, and of course, summary. And indeed, if you have questions, it will be my pleasure to address. Now, again, as I say, I really did not know the participants who are with us today, the knowledge that they have in the subject. But I've tried to keep my talk like broad, right? Such that it really catches attention of young scientists. And of course, if in future you think that I should give a more specialized lecture to those who really understand the subject in itself, it will be my pleasure. Now, what is computational chemistry? Now, you may realize that, for example, right, chemistry is a science subject. Now, if chemistry is a science subject, you cannot do science without practicals, without experiments. You're bound to do science with experiments and practice. So this is chemistry. And chemistry, don't forget, is a science subject, and therefore the laboratory has a role to play. So this is my picture here, where you have a picture of the laboratory. And to anyone that you really show this picture, most probably the word chemistry will come straight away. But then, what is computational chemistry? Now, this is the equation. This is the equation that really makes everyone like trying to get away from the subject. But allow me to give you a perspective of this equation. So if you have really done your physical chemistry, or you may be also from the science background, you might be knowing that there is something which is known as the Schrödinger equation. So this is the red equation. And this is the equation which, like I'm saying so many times, the students, they keep on saying it's difficult, we don't understand, and so on and so on. Well, it might be a perceptive of your own, but then if you realize that this equation can lead to many things, that is really, it's very difficult for you to really imagine that things can be predicted from that. Now, allow me then to go back. Now, you may be knowing that, for example, you have your hydrogen atom. So if you have your hydrogen atom, you do have only one electron. That's very good. So you have your hydrogen atom, you have one electron, and I can tell you that it is possible for you to solve the Schrödinger equation exactly for this system of one electron, for you to obtain the electronic energy. And of course, then you will get the wave function. But I don't know whether this comes to your mind, but then the moment that you go to the next atom, I'm taking helium, where you now have two electrons. Forget it, you will never be able to solve the Schrödinger equation. It's very strange. You can do it exactly for one electron system. You cannot do it exactly to the simplest non-one electron system that you go. I'm referring to helium. Now imagine that, why you can't do it. For those who really understand, it's because you have the additional electron-electron interaction, which makes this Schrödinger equation basically impossible to solve exactly. And of course, now as you increase the number of electrons, it will become more difficult. You will never be able to solve exactly. But you see, the human nature has always been to work hard, to try to be able to do something. No doubt that you cannot solve the Schrödinger equation exactly, but that doesn't prevent you from obtaining an approximate solution. How to get the approximate solution? Now you have to solve this equation numerically. Basically, this is done by an iterative procedure, which I will not go into detail. And now, the methods for solving this equation numerically, they're really known for many years. Hartree-Fock, MP2, and so on, DFT, and so on, and so on. But then now, what has really happened over, I can say, the past 20 years, right, is that now you have powerful computers which can be used to do this sort of iteration and therefore help to solve this equation numerically through an iterative method very fast. Now, this is computational chemistry. So what is computational chemistry on its own? Computational chemistry methods, they really attempt to solve the Schrödinger equation numerically using methods which are basically known. For example, I refer to the Hartree-Fock method, the MP2 method, and the DFT method. I will not go into the detail about the differences between these methods, but of course, these are known. So then, and computational chemistry is very useful. You will find that it really meets the criteria of green chemistry. Of course, you have lots of these computers that you should know how to really dispose. But then it has many applications. Applications in electronic structures of existing and novel molecule complexes and clusters. Thermodynamic spectroscopic kinetic parameters of molecular species. Global warming potential, global warming species and reactions in the atmosphere. Reaction mechanisms. Solar dyes and their efficiencies. Drugs and their applications. Interdisciplinary fields such as astrochemistry and biochemistry and so on. So the list goes on. Well, I'm not going to these topics today, but these are just to give you an idea. And you see, the field has really progressed and it's getting into the other applications to the humanity. These applications are well recognized to such an extent that the Nobel Prize was awarded, for example, in 2013 to 3 computational chemists. And then, of course, you might be knowing, in 1998, the Nobel Prize was also awarded to computational chemists for their work for developing this field. And I can tell you, you may realize that this whole thing now, right, has given us the opportunity, has really given us the opportunity, right, to use computational chemistry methods to solve problems which might be of fundamentals in chemistry, in science, but it can also be interdisciplinary. And this is what makes it really interesting. Now, what I will do now, after have given you an overview of the subject, I will try to relate it a bit to the research that we are doing and make you realize that you have to be very careful. You have to be very careful to really see what you are doing, what you want to achieve, and what type of science you want to do. Now, we have a research program, for example, right? So we have a research program, for example, in the direction graphite, graphene, silicene, what is next? Everyone might be knowing about graphite. So you might be using your pencil, or you might be using your lead in your pencil, which is basically not that wooden one, but I'm talking about the other one where you keep on having a small lead at the end. But then there's a fundamental question: why do you use pencil? Why it is soft and slippery? I hope that you really appreciate that you have layers of carbon atoms which can really slide on each other. But then what is graphene? It's just one layer. Now come to your concept of your nanotechnology. And of course, the one layer has really different properties that are really being used in the industry compared to graphite. And what is silicene? Graphene consists of one layer of carbon atoms, but silicene, instead of carbon now, you do have silicon. Now, we have been interested in the functionalization of fullerene and graphene. Why? What can we achieve from that? How computational chemistry methods can be used? And what is the concept of solid state science being involved? Now, this is your fullerene. I'm referring to the C60, right? So you may refer to this field as either solid state or nanotechnology, depends on how you're looking at it, right? But then the Nobel Prize was awarded in 1996 for the discovery of fullerenes and, of course, its applications, right? But we are interested now, like I said, to try to move to other components. I mentioned about the graphite, I mentioned about the graphene, right? But then now, of course, you might be knowing that, for example, the graphene, the Nobel Prize was awarded in physics in 2010 for the groundbreaking experiments for this two-dimensional material. But now, how do you functionalize these materials? Here, I'm talking about hydrogenation, fluorination, going into the field of organometallic chemistry, and even organic chemistry. Now, this is an example now of a fundamentals of the functionalization. So you might be knowing about your cycloaddition reaction, where we have an alkene, being added to a 1,3 dipolar compound. And now here you're having ethene being added to butadiene in the simulated video that you have. But what I want to share with you is that, for example, this is a proposed transition state where the alkene is being added to the butadiene. And this is not a video which has been, like, I should use the word man-made, but it's a video which has been generated from the calculation, namely the intrinsic reaction coordinates, which gives you an idea how the two reactants are really joining. And this gives you important information. For example, both the carbon-carbon bonds, they are formed to the same extent. So this will be a synchronous addition. Unlike that, one may be formed and then the other one forms separately. So you see, you really get a picture of what is really going on in the transition state. But remember now, this type of calculation you can do in the gas phase. Now, this is your 1,3 dipolar, which is added to your dipolarophile, leading to your cyclic product, right? But now you can go for the functionalization. Once you have done the addition of ethene, you can add it to the fullerene. Like I said, it's limited to the gas phase calculation, but later how we can extend to solid phase, I will come to that. So this is what we did, where we have different possibilities of adding the compound to the fullerene. And there are different possibilities where you can add it to the different positions of the fullerene. And of course, you can have several of these possibilities, which I will really not go into the detail. So once you do that, then you're able to have an idea, right, in terms of the interactions between the compound being added to the C60, in terms of the activation barrier, in terms of the relative stability of the compound. And now these results can be used as precursors to those experimentalists in their quest to synthesize these compounds, which ultimately can be done. For example, here, we observed when we have the substituted nitrile with FCNO, abnormally we get a lower activation energy and a high stability ultimately, which ultimately should make it very prone to be synthesized and possibly has some applications, right? So ultimately, this was done, right? And atypically, we observe fluorine to have a very low activation barrier for this reaction and a thermal stability. So this was published many years back, almost now 20 years, right? And you can still observe, you can still find that the functionalization of fullerene or graphene and so on, still being a major component of research. Now, in addition now, you find that, for example, I've talked about the functionalization to the fullerene. You can have the functionalization to graphene, right? Where now you can have modeling to match with the actual solid phase, right? Now, for example, you can add it to ethene, you can add it to benzene, and so on and so on. So you increase the size of the ring such that the results that you get really go to a sort of convergence. Because remember that it might be difficult to really to model the actual graphene as such in terms of the size. But now there are possibilities which I really come after I really give this one, right? So for example, you can add your compound to the model that you consider in terms of the center and the corner and the edge, right? And you get some interesting, you can get some interesting compounds that are really getting some modification with respect to the structure of the graphene. So if you see this one, there is a sort of bending that keeps on going on. And this can have an effect on the properties of the material. So these are just pictures, like for example, again, this is another simulation. You can really see now that the two bonds, they are not formed to the same extent. And the bending in terms of the structure that happens when the cycloaddition takes place. And again, as I said, so this is not a type of a video which has been generated like from some sort of animation and so on, but actually generated from the calculation. And what we observe here is the carbon-carbon bond is formed first, and then the oxygen-carbon bond forms later. It's an asynchronous addition. So we have other things in mind now, what we are currently doing. We are really considering other possibilities, right, with respect to the fullerene, right? And then try to see whenever we may have a second addition. So we have done the calculation for one addition, we look for the other addition. Now the other one, like I said, again, to go for the novel 2D materials. Again, like I said, I refer back to the graphene, right, where it is known to have special characteristics, right? Now, you might be knowing that it is used in batteries, composites, and so on and so on. I don't want to list one by one the different applications, but then be careful. We are in group 4. We know carbon, but now how about going to the other atoms? Silicon, germanium, and so on and so on, right? So in fact, we have a paper which was published in 2007, where the group from Liu Yan Wen reported on the silicon analog of graphene and coined the word silicene, right? So now this is silicene, where now you have substituted the carbon by silicon, right? One atypical observation that you can see here, the graphene is flat, whereas the silicene is not, right? So now he is in fact the father of the silicene, coining the word, right? And he visited the group some years where he's collaborating with us in trying to have other parameters, other derivated structures from the silicene, right? Now, like I said, the whole thing started from carbon, right? When in 2004, they reported the isolation of graphene. In 2007, silicene was coined. 2009, fabrication of silicene nanoribbons. And now, in 2015, there was the first demonstration of silicene in transistor. So this is the structure of the silicene being not a flat one. But then how about others? How about other 2D materials, right? Now, I'm talking here of going down the group. You find that they have interesting properties which are worth to be considered, right? Now, I refer here, for example, to some papers where these are really reported in literature about having other 2D materials, right? Now, these are some papers which you can really go into, going even to the germanium and the tin, right? Now, but don't forget that carbon is next to boron, right? A neighbor to boron. But what about having other 2D materials in terms of these elements? For example, the borofin. You may be having, for example, others such as aluminum, right? Where now you have aluminium atom, and then you have even the indium. Now, so in fact, now, you find that the boron, aluminium, and the indium, they have been reported. But to our knowledge, there is no report on the gallium and thallium. So these are the calculations that have been going on in our group. So the calculations are ongoing, and we should be able to publish the results soon. So I have not included the results because we have not yet published the results. But this gives you an idea with how things can really be done. Right. So the last part, I hope I'm keeping with time, is trying to, because I've realized that there are lots of research going on in southern part of India, treatment of wastewater using some adsorbents, right? So we have, for example, the need, right, to go for treatment of wastewater so that these can be recycled, can be reused, right? And of course, this meets the Sustainable Development Goals of the United Nations, right? Now, how can chemistry, how can computational chemistry really help ultimately in treatment of wastewater? So you might be having the biodegradation, the ozonation, the electrosorption, the adsorption, and so on, right? But then you have now other possibilities. The nanotechnology, solid particles, which might be used for the treatment of wastewater, right? Now, this, we did some one paper which was published some years back, where we've looked at the effective adsorption of pyridine on mesophorous silica derived from de-oiled mustard cake. The experimental was done in India, and we did the computational study. Again, now you have a suitable modeling that you have to really do with respect to the possibilities to match the solid phase calculation. You should have a suitable model, right, to really match the adsorbent. Again, I will not go into the detail, but if you want to have additional information, you can really go to the papers or even have further discussion with it, right? Now, this is another one where we have used the palladium decorated zinc oxide expanded graphite electrode for the removal of 4-nitrophenol, where there has been a joint experimental of computational studies. But then you will see that this is, again, this is technical, but if you really want to have idea, you can go to the, but now come to the vital point. So you might be wondering then, what is the difference between these calculations and what really goes on for solid phase calculation? So I strongly recommend that those who are really in this field or you are really interested, we have been using now most for our solid phase calculation, the quantum expression, right? Which can be used. Of course, it has to be, your system has to really fit into this one where you really have a sort of periodic system where you can use the quantum espresso for the solid phase. And basically, this is an open source, it's free, you can use, but of course, it all depends on the computing power that you really have. And the last one, which is a really a common mistake from everyone, and I recommend here that you have to be very, 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 very careful, right? So I find that so many scientists, they are synthesizing organic compounds as crystals, and then doing some sort of computational calculation, and then trying to compare the X-ray structure with the gas phase calculation. I think there is something wrong here. There is something wrong, right? Because remember that, for example, so this is one paper where we've just published, and we raised this issue, right, to create the awareness. Now, for example, you will have the synthesis of organic compounds, you will generate the crystals, you will use X-ray to obtain the structural parameters, and so on and so on. Now, allow me to tell you, of course, you may be having a wrong experimental procedure in using your X-ray, but I don't think there is any better method to analyze your crystal with X-ray then there is nothing better. Right. So why are you trying? Why do you have any doubt in your X-ray data and trying to use computational chemistry methods in the gas phase to go for certain comparison? What sense does it make? Right. Now, I can tell you, for example, when a crystal is generated, right, it happens that the structure adopts itself in terms of several other the molecular interactions, the solvent that is grown, and so on and so on. But then when you're doing a calculation in the gas phase, you have complete freedom. You don't expect the structure to really match with what you're having in the solid phase, right? So you have to be very careful. So of course, then you will come and tell me it happens that you'll come and tell me, no, okay, it is reported like this. Yes, but when others are doing mistake, but that doesn't mean that you should follow their mistake. You should understand what you are doing. Right. Now you will tell me that this has been published in X journal, in Y journal. Yes, I agree with you. I'm not here to contest what's happening, but I can tell you I've read papers in journal with impact factors 5, and there are so many mistakes even in the science, right? But it's not my job to raise this issue. It's not my job to argue with the authors, to argue with the editor. It's your business, right? So you have to see really what you're doing, what you really want to achieve, and what professional honesty being involved in the research. So at the end then, I would like to summarize. I hope that I've given you an idea about computational chemistry methods. You have to be very careful, right? Whenever you are referring to the solid phase calculation, it's not that ab initio calculation that you are doing trying to solve the Schrödinger equation. So I have to be very careful to interpret the results. I've given you an idea about our research and how sometimes there might be a paradigm that you should really try to understand. Now, future objectives are to collaborate with experimentalists and the industry, more of applied research, go for the country needs, and of course, communication to the public, right? You're invited to collaborate with us. We have so many collaborators across the world, right? And if you're really interested to visit my group, but now sometimes due to this pandemic issue, there are so many problems being involved, you can visit this website for possible grant availability, right? So I hope that with these, I've been able to share with you my views, what I really think about the nature of the subject, which again, I've tried to do it in a broad aspect. So I need to go for certain acknowledgements. I'd like to thank Professor Saktivel for inviting me, the members of the organizing committee, and all the participants and other speakers who are really joining us today. And I think yesterday also for sharing their presentations. I need to thank the University of Mauritius, the University of Johannesburg, the Tertiary Education Commission, the Mauritius Research Council, Grid Facility for Computing, and of course, all members of the computational chemistry. So I hope that I've kept with time. That's all from me. Thank you for your attention. And thus now, it will be my pleasure to address questions that you may have.
Dr. Deepa, is it? Dr. Deepa, you are muted. Can you unmute? I think she has some issue. Anyway, okay, audience, you may have, we have a.
Sir, Sunny sir, you have to ask. He has to. I think he has muted.
No, madam is a co-host. Actually, she can unmute. Yeah.
Hello, sir.
Yeah. Fine. Yeah, the session is open now. Deepa madam, can you coordinate?
Yes, sir. Yeah. If there are any questions, you can either ask or you can put in the chat box.
Sir.
Yes.
Sir, good morning, sir. Salvam, sir. Bhagya here.
No, now let's question session.
Sir, line.
Sir, Ramsam sir, I have doubt. What kind of algorithm we can use for the, if you want to study the solid surface? Because especially like kind of zeolite kind of materials and those things, how we can.
Yes, so like I explained, the actual type of solid phase calculation really depends on the system that you have, right? Now, for example, the one which I gave, like quantum espresso, it is more like if there is a repetition in the system, it's periodic bound, right? For example, for graphene, or if you have a unit cell being repeated and so on and so on, right? But if your system does not have, you have no possibility, you have no choice but to go for certain type of modeling in terms of the interacting structures, right? And then use your pure ab initio method, which is basically gas phase calculation, and try to see whether you can get some results which can really match with what is really happening with respect to the experimental findings.
Thank you, sir.
Good morning, sir.
Yes.
This is Gangadhar.
Yes, sir. I have a question. So these adsorption studies we generally do in the liquid phase, right?
Yes.
And modeling goes with the actual real interaction of the molecules alone, right? So where we eliminate this interaction of water with that molecule when you do computational aspects.
Very good, right? So precisely, this is what I said, right? But again, like I'm saying now, so when you have the adsorption, so it again depends what is the nature of your absorbent, right? So if your absorbent is periodic bound, it is repeated, then you can try to go for the actual solid phase calculation, and it is now possible to include the solvent. But then when you include the solvent, at this stage, to my knowledge, it is mostly to pure solvent. But you may realize when you're working with, for example, wastewater, the solvent, it's not actually pure water, but it's a medium that has its own characteristics. And it's not, remember that it's not possible for you to model each and everything.
Yes.
It's impossible. How can you?
Yes.
Right.
Yes.
But then you have to see, you have to work out based on literature, based on your experimental findings, based on your knowledge, based on your insights, based on your innovations, how best you can really improve your modeling to really match what you're getting experimentally. You will never be able, it's almost impossible to really mimic the actual experimental the actual experimental medium or nature of interactions 100%. This is not possible.
Okay, sir. Thank you. We
Sir,
can just give you a validation. That's all.
Yes, of course.
Okay. Thank you, sir.
Sir, there is a question in the chat box. Is it correct to optimize the structure using one functional and derive its properties like URI?
Because yes. So thank you. I can comment on that. So I was referring to the gas phase calculation for optimizing the geometrical structure and so on and so on. Like I said, there is nothing wrong in doing this, right? But then it makes really no sense to compare it with the actual solid phase. But basically for me, I see nothing wrong. If you have the X-ray, you have the structure. I think that this is the best structure which is available for that particular crystal. So you can use the structure of the crystal as such to go ahead for other derived properties. Because remember that, for example, in UV and IR, I don't know whether you'll be doing it in the solid state or this will be in particularly UV in a solvent. So ultimately, you will have to dissolve your compound in a solvent. And thus, right, I see no reason that why this doing that single point calculation from the X-ray structure might not be correct. But I don't know whether the use of another functional might be good. It might be good for you to stick to one functional throughout your calculation, throughout your studies.
Okay, sir. Thank you. So, are there any other questions from the audience? Sir, I have a question.
Yes.
Sir, for this big materials, is this nowadays people are using for biomolecules QMMM based methods, this dynamics for the bulkier part and then for the active part, this QM region. But since this kind of a sheet materials are all the part, it is important. So this kind of methods having any applicability there?
No. So remember that I've talked about the ab initio and a bit getting into the solid phase, but I've not talked about the modeling, the dynamics. This is another part of the subject in itself, right? So we have collaborators who are really doing that, but this is something completely different.
Uh,
There are no more questions. I think we can
yeah.
conclude the session.
Thank you, Dr. Deepak, for sharing the session. Thank you, Professor Ramasamy sir, for accepting our invitation and sharing your valuable research work. Thank you for us.
It's
So,
my pleasure. It's my pleasure. Thank you for the invitation. Thank you for all the participants, and I hope that you have a good interactive sessions
Yes.
for your research.
Yes, thank you. And now we will move on to the next session. Next section will be shared by Professor M. Swaminathan sir, and we have eminent professor, Professor Selvam sir. Sir, welcome sir for the webinar.
Thank you.
Dana, are you there?
Yes, sir.
Yeah, please.
Okay, sir. This session will be shared by Professor M. Swaminathan, President, ISCUS. He has a teaching experience of 42 years. He is professor at Annamalai University. He has published more than 200 research articles. His research focuses on material chemistry and photocatalysis. He is a fellow of Royal Society of Chemistry. I welcome sir to chair the session.
Thank you for the introduction. So it's my pleasure. Hello, is it audible?
Yes, sir, you are audible, sir. Yes, sir.
Okay. So thank you for giving me an opportunity to chair this session. I'm having great pleasure in introducing Professor P. Selvam. And Professor P. Parasuraman Selvan is currently the head National Center for Catalysis Research, IIT Madras, Chennai. And professor in the Department of Chemistry, IIT Madras, Chennai. And he is also an adjunct faculty, School of Chemical Engineering and Analytical Science, the University of Manchester, UK, and the Department of Chemical and Process Engineering, University of Surrey, UK. Earlier, Professor Selvam was in IIT Bombay as a faculty, and also was in Tohoku University, Sendai, Japan. He was also a visiting associate professor in the School of Chemical Engineering and the University of Queensland, Brisbane, Australia, and an eminent international visitor, School of Science, Health, Western Sydney University, Australia. So prior to this, Professor Selvam was a research associate in the Department of Condensed Matter Physics and Laboratory X-ray Crystallography, University of Geneva, Switzerland. And Professor Selvam's research work mainly involves in the development of novel synthetic procedures for the preparation of ordered nanoporous zeolite materials such as silica, alumina, titania, carbon, and metallosilicates and metalloaluminates and a variety of other metal oxides including zirconia and niobium, etc. In addition, Professor Selvam is also involved in the development of nanozeolites, European zeolite size and shape controlled nanomaterials as well as supported metal catalyst systems. Professor Selvam research interests also include nanostructured materials, heterogeneous catalysis for green chemical routes, environmental remediation processes, and energy conversion, and also storage cell and lithium-ion batteries. Professor Selvam major contribution includes in the design and development of novel heterogeneous catalysts for a variety of industry important organic transformations that have received an overwhelming response both from industry and academia. Several industrial consultancies and sponsored projects that he has brought into the institute has helped him to build a strong and vibrant catalysis research group at IIT Madras. Professor Selvam had several visiting adjunct faculty positions in various universities, institutes, both in India and abroad. He has also been bestowed with several national and international awards and honors. So to mention the few honors and recognitions, he is a member, Empowerment and Equality Opportunity for Excellence in Science, Chemical Sciences, DST 2016 to 18. He is also a member, Higher Secondary Textbook Chemistry Writing Committee, State Council of Educational Research and Training, SERT Chennai 2017. He is also a member, Program Advisory Committee member, Physical Chemistry DST 2012 to 2015. And he is an associate editor of Advanced Porous Materials, American Scientific Publishers 2013 onwards. He is a recipient of this Reverend Senior Annamma Philip Endowment Lecture, Stella Mary College, Chennai 2012, and also a recipient of Professor L. Lakshmi Narasimhan Endowment Lecture, AM Saint College, Chennai 2010. So he has many more awards. So with this, I have a great pleasure introducing Professor P. Selvam, and I request him to, deliver his talk. Thank you very much.
Yeah. Thank you, Professor Swaminathan, for your kind words and the elaborate introduction. Thank you very much. It is my pleasure to be part of with you in this task. I also would like to thank Professor Saktivel and ISKAS for inviting me for this solid state meeting. So thank you very much, all of you. And I'm not going to share, I'm not going to share my research experience. I'm going to see how solid state chemistry helps in understanding the science in total. So the basis of solid state chemistry is very important for our day-to-day understanding and all other events. So I'll just start with this, just share my slides. Let me check. Do I share that? Can you hear me now?
Yeah.
Yes, sir.
Just a minute. I'm just sharing my slides. How do I share? Okay, yes. Can you see the slide?
Yes, sir. Slide
Okay.
15.
Yeah, thank you very much. Once again, I thank Professor Swaminathan, Saktivel, and ISKAS for giving me an opportunity to share some of my thoughts on solid state chemistry. Solid state chemistry. So chemistry is important. Chemistry is a central science. Mathematics is mother of all sciences. You know that, okay, largely our engineers practice that one, and then without maths, nothing can happen. So that's why mother of all sciences. Chemistry is the central science. Without chemistry, nothing happens. So there is mathematicians, so they live in an imaginary world. Whereas the chemists or chemical engineers or the scientists, so they live in a real world wherein we talk about the realistic materials and then connect mathematics. So this is what all about. This is what the solid state chemistry does. Solid state chemistry is the simplest of the subject, but unfortunately what happens in our country, it is given least preference. Okay, so it's the easiest thing to understand because solid state chemistry, most of the things are asymmetries to start with. It's easy to follow, but unfortunately all our the chemistry curriculum in this country, so our teachers or chemistry practitioners, they start the lowest symmetry ones, basically the organic, inorganic complexes, compounds, and so on, not the materials. They are called nowadays a fashion to call materials chemistry, but still they think the materials are the molecular, they talk about molecular materials, not the non-molecular materials. Non-molecular materials are large amount of materials, and which is today, day-to-day our life, except the health science, all other things are non-molecular materials, basically solid state materials. Unfortunately, none of us but many of us don't know many of these basic things. That's what I'm going to bring out. But I'm going to take an example. The standard, one of the best authors in this subject for chemistry, solid state chemistry, A.R. West. He has given in one of this preface. I'm going to take some of this one, and you can read that one in a solid state chemistry by A.R. West textbook. So in the preface, he has given, wonderfully he has given, and this is what I'm going to look into that one, look at that one. Okay, what is important for solid state, this one? Basically, we are a chemist or a physicist or a scientist, for example, scientist. It's important to look at that materials. Materials can be classified amorphous and crystalline. We'll come to that shortly. All the materials, what is important at most, it's structure. Structure means crystal structure, but unfortunately we deal with largely molecular structure because we are satisfied with this one, and then okay, we carried away with that one, and everything is focused on life sciences. That's why we are probably, that's how India's the global the leader in the population, right? We focus everything on the life science. Go to anywhere, any place, it's only life science, organic molecules, inorganic compounds. That's all. We stop with that one. Solid state materials, we think it is a physicist subject or material science subject. It is nothing but chemistry and physics of materials are important. As I said earlier, chemistry is a central science. The chemists are the people who discovered all these materials, exploited by other people. Okay. So at most the structure is important. Structure, bonding, properties, and applications. So this is what any given material, we need to understand that. Okay. Unfortunately, what we do is we go reverse way. We start everything with an application, right? Without even understanding any of this. At the most, we deal with the bonding because molecular compounds we deal most of the time, and then okay, we talk about bonding. But the structure means crystal structure. We need to understand that one. Solid state chemistry gives elegantly in a simple way to understand these structures at the atomic level, at the molecular level, or even at the nano level. So we can understand all these structures. So this is what I picked up from the A.R. West, Solid State Chemistry and its application. This is the first textbook on solid state chemistry. See, nowadays, we used to check only solid state physics books, standard book, solid state physics by Kittel, or many others were there, Ashcraft and so on. But it's easier. Solid state chemistry by Anthony R. West. He has put it in a simplest way. One can read like a storybook if you understand the basic concepts. So the chemistry, as I said, chemistry is a central science. The next aspect is your solid state chemistry. Unfortunately, we are not giving any importance, although it is everywhere we include. You go to the 10th standard textbook or 12th standard textbook, state board or central board, you have a chapter on solid state chemistry. But I don't know how far we understand, neither the teachers nor the students. Or that's why people keep saying that you leave it in your choice, or you concentrate on all of those things. So solid state chemistry, and then it goes to the materials chemistry, material science, and engineering. So solid state chemistry is at most important. So just a few sentences. I'm going to read this one. Chemistry is an ever evolving subject. It's true. Even today, there is always this one is like discoveries, inventions, or you have there something new always evolves from chemistry. So otherwise nothing happens. Traditionally, there have been 3 branches of chemistry, which we are known: organic, inorganic, physical chemistry. And with some arguments in favor of analytical chemistry, sometimes it comes. Some departments we have analytical chemistry, or some universities we do have, very few universities. And that is a debate. People think that we can practice it in organic or inorganic chemistry and so on. But an alternative, fairly a new classification favored by this author, even by me, the new classification divides chemistry into 2 broad areas. Molecular, this is what I said, okay, molecular, which includes liquids and gases, largely your organic, inorganic compounds, and non-molecular, it's a solid state. Okay, so molecular and non-molecular solid state. So this is what the solid state largely ignored. Okay, so these are the things. Okay, for example, okay, you can see these are many substances. The way in which we think about, make, analyze, and use molecular, non-molecular substances are completely different, as shown by a comparison of one simple substance in each category. Toluene, for example, molecular. Aluminum oxide is non-molecular. So if you take these 2, you will understand why, which is how it is important in those things. let me see. There are two other textbooks. I just want to show if there are students, number of students are there. So, or even for others also. This is the standard textbook, another textbook, Solid State Chemistry by Smart and Moore, which is even simpler. One can read it without even any help. But of course, you need to know the basic concepts. It's like a physical chemistry concept. If you don't know the concept, it is nothing will happen. It's like a blind man touching the elephant. Something will happen, but so that's how you keep mugging things and then vomiting. So this is what is happening. The best book, this one is Structural Inorganic Chemistry, A.F. Wells. This is one of the oldest books, even in the 70s. This is published, and then even today it is one of the most popular books. Name any crystal structure, you will find out, and it runs over 1,000 pages. So, as a chemist, you should have gone through this book, or if you're not, please check this book. It is available all over the world, all over any library. You will find that. If the book is not there, then okay, then see that library, or the institute or university, or not the same way what I was telling you. People are not shown any interest on the molecular, this one, crystal structure or structures. Okay, just I'm not going to deal with, just to show this one, the toluene I said aluminum oxide. See the formula and then the defects. Because what happens is the defects are important in solid state materials, which responsible for many of the properties, exotic properties or new properties. All these defects, the defects are very, very small concentration, either missing or extra added entities, okay, which is important. It's only possible for solid state materials, whereas in the molecular materials, it is not possible, not allowed, because it is composition is fixed, and then okay, we cannot change anything. Like defects or structure and its determination, properties and applications. You can look into that one. A good account of this is given, the comparison of the chemistry of molecular and non-molecular solids. Okay, so other, just to show this, and I said, okay, largely the organic, inorganic materials are confined to the healthcare, but whereas if you see this one, many of these materials, ferrites, laser, thermistors, light emitting diodes, optical fibers, semiconductors, piezoelectric materials, ceramics, superconductors, composite carbides. Many of these are solid state materials which we use day to day, all our convenient or comforts or many other things. We use this one. Today, you see this on any of these appliances, you will have any one of these materials. It's all originated from solid state chemistry and the structure. Okay. So many of these compounds, again, you can see this one, physical properties. Typically, for example, microwave, we use everywhere. Even in the lab, we use today microwave, right? At home, we use computer memories, sensors, modulators, batteries, semiconductors, magnets, electrolytes, solid electrolytes, and so on, hard disks. Everywhere you have this solid state material. Unfortunately, our understanding, particularly the chemist, you ask a simplest question, I don't know even here how many people can answer the simplest, the crystal structure possible, right? So it is important, the bond distances, bond angles are derived from the crystal structure data, because without knowing crystal structure data, today you give this one, okay, so you just give a command in the computer, so it gives you all this information without knowing. You don't need, anybody can get this information, right? But unfortunately, what happens is that will not lead to the progress. If you know the subject and then understand that one, you can cross this one. Look at this one, beautiful colors of these gemstones. How do they originate? Why is there all this one? These are all solid state materials. You see this in alumina, silica, basically silica and alumina. In that a small amount of impurities we had, you get wonderful colors. These are the gemstones. What we go to your shops, particularly the Asian country, people are fascinated by these things, right? It's available. I mean, it's even naturally occurring in the case in African countries or many other countries, but one can make artificially these gemstones by just small amount of impurities in a crystalline solids like alumina or silica, right? But if you understand that one, how much of defects I have to put, how much of where to put, which site I have to put, all these things are important, which gives you the crystal structure. Many of the properties we can understand if you understand the crystal structure, or reason it out if you understand the crystal structure, otherwise it is impossible. Okay. So all these things, how do we understand the crystal structure? You can see this from the naturally occurring or the minerals or many of these structures, which is basic structures are given in this one. Major inorganic structure types relevant to this one. This is also picked up from A.R. West book. You can see all the structures in that one, or the A.F. Wells. Okay, so you can see this one. So you can see some of the familiar one: garnet, diamond, right, corundum, perovskite, pyrochlore, rock salt, spinel, and all these structures. It's very, very simple if you do methodically, if you follow that. Unfortunately, none of the textbooks will give you this detail, number one. Number two, we are some kind of, this one, solid-state chemistry means in this country it is alien, or there are some few groups practice it in certain aspects, that's all. Beyond that, nothing happens. And then, even in none of the universities, we have this one compulsory course. But whereas in IITs, we started, this is some time ago, couple of decades back. So one MSc, at least in MSc level, one compulsory course on solid-state chemistry, so that you understand everything and related to all other things like your organic, inorganic compounds or complexes and so on. So fairly simple because this is a very large number of structures are there. So to make it simple, I put it here in another slide. You can see this on all the minerals on the left-hand side: antifluorite, cesium chloride, fluorite, nickel arsenide, perovskite, rock salt, or halite correctly, rutile, sphalerite, spinel, wurtzite. These are all, at least you should know undergraduate level. Rest of the world, they study on undergraduate level, irrespective of what you are, right? Whether you're an engineer, scientist, or engineer, or chemist, or physicist, or material scientist, or even medicine people. So this is a compulsory, the basic structure. Even if you go look into this one, except few, all others you can see even school textbooks. We don't know what we understand all these things, which is again, we go sometimes it's a pass fail, sometimes we just simply people just write something. Okay, I'm going to show you. Look at this one. This is the elementary one. You can see on the top I have given something, and then bottom I have given something. So you have to understand this one, atoms, because these are all basically in the geometry, the maths geometry. That's why I said the maths geometry. It's geometrically, we can have the crystal structures or the crystal systems. We can be with 3 parameters, 3 side and 3 angles, we can generate 7 crystal systems. Hypothetically, we can generate, or mathematically, it is proved that, okay, only 7 possible crystal system can exist with this A, B, C, alpha, beta, gamma, 3 parameters and 3 angles. And with that, the simplest being on the topmost, right, topmost left-hand side, simple cube. Okay, the simple cube, we don't know we have any example for that one. Likewise, the next one is a body-centered cube. And then on the other side, the last top corner is face-centered cube, right? We don't know how many of you may know, even the whatever the level, how many of you know the correct example of this one, right? That is where it's important. We don't learn. If you ask somebody, they'll say all kind of examples for this one, right? So likewise, on the bottom, you can see this one, that if I take the top corner, left-hand side corner, in that only corners are occupied. Here I put extra atoms. This is one crystal structure, below that another crystal structure. These are all basic structures, very basic structures. You should understand at the school level, not even at the undergraduate level. School level, you should have understood all these things. If you understand this one, then we can go to the next level. Just giving this one. This is, I'm going to show you why it is important. Here, extra I put on the edges, edge centers, I put red atoms. Likewise here, the second one, the corners and the body centers, the positions are called, okay, basically the position, there are 4 positions I'm going to deal with them. To start with, corners, edge center, body center, and the face center. In a cuboid, you can have corners, simply the vertices, the mathematicians say the vertices, edges, body center, and face center. So you can play with this one in a systematic way. So if you symmetry has to be conserved, that's all. That's the only thing, is symmetry has to be conserved. If you have the symmetry, then okay, we can place all these things and then we can get the structure, generate the structures in numerous. Hypothetically, we can generate, and then we do have examples. The mathematician do hypothetically, and then okay, the chemist will find out whether we do have an example for that one. Indeed, most of it, we do have example, right? So you can see here, this one, the top one, I have given this one. The corners and the body centered same atom, and whereas in the bottom, I change to a green color, the brown one to a green color. This is another structure. This is one structure. This is another structure. Loosely, if I ask anybody, they'll say this is also body center. This is also a body center. Okay. So that is where, see, you start with your basic understanding is wrong, everything will go wrong. The mathematics, we say that when the first step is wrong, every step is going to be wrong. Here also same. This is also mathematics only, geometry, that right? The third one is corners and the face centers. Sorry, corners and the face centers. Here also I changed that one. The face center selectively I changed. This is another structure. So this is the very basis of the crystal structure. If you don't know the correct example, we cannot proceed any further. Whatever our understanding on chemistry is all absurd. So nothing you can look into this. And people, so many people think that they solve the crystal structure. You ask anyone, they may not be knowing any of these things. I can bet on that one. Okay. So that is the level of our education in here. Okay, not only that, okay, we have put an atom as odd uniform spheres. We can put in the corner, I can put in the face center or in the body center. Not necessarily this one, I can also put as a molecule, atoms, ions, molecules, or even a cluster. You can see the below that one, a cluster coming, or polyhedra. This is a polyhedra, and which is even extended to the biochemistry or biology, right? You can see this one, the all biological molecule. Also, one can understand through the crystal structure. That's how when you solve a structure, the proteins or the biomolecules, you get a Nobel Prize, got many a times, right? So the understanding should be that the chemists are the better people to even to do the biosciences, right? If you understand the chemistry at the atomic level or the molecular level or the cluster level, you can understand many things, you can modify, you can discover, you can invent many of those things. Your basics are clear. So this is another example. Typically, you see this one on the right hand side, the blue one, I've just replaced by a cluster. All right. So this is a polyhedra. What we call is a polyhedra, which is simple, nothing. The inorganic chemistry first lesson is VSPR, valence electron pair repulsion 3, molecular geometry. We study the molecular geometry, the shapes and sizes, the same thing. We need to extend it to this one. And then, okay, you can see here, which is a 3 connected. It is one typical type of a polyhedra, icosahedron. The icosahedron is very important polyhedra because most of the virus or the biomolecules will have this kind of geometry. That is why they're all highly active. Okay, it is impossible to control it. Even the COVID-19, which has a similar kind of this one structures, right? So if you understand that, we can tackle the problem. If you don't understand that one, it's like a trial and error method. We keep doing that one. Okay. The next on the left-hand side, it's a Buckminster fullerene. It's a carbon 60, C60, which is, if I truncate this one, this is what I get. Truncate this icosahedron, I get this geometry. I don't know how many of you know this one. We study in mathematics truncation. What is the purpose of truncation? Because it generates different kind of surfaces. This is a 3 connected one. This is a 6 and 5 connected one. This is a 6 and 5 connected one. If I just truncate it, you get this automatically. If you know your mathematics knowledge is good, then you will realize it. This is again school mathematics. Okay, so you can do that one, and then you can understand that one. So this is what Buckminster fullerene 6 and 5 connected one, and then this arranges in a particular fashion. So these are all molecular solids. So you can see this one, which is a one molecule. C60 is one molecule and held by weak van der Waals forces. In fact, whether molecular solid or non-molecular solid, it has to, the information you have to get the crystal structure. Molecular solids, we can sufficiently cool it to low temperature, that will crystallize. Then you can get all this information. They organize like this at the very low temperature, right? So this is what they do. The foot and mouth virus on the left-hand side, you can see the grass picture is like this. And then if you look at that very carefully at the atomic level resolution, so you get this icosahedron, right? So not only that, in inorganic chemistry, we see this heteropolyacid, homopolyacids. The heteropolyacids are good catalysts. So the complex structures, it's a very complex structure. Unfortunately, people don't understand that one. Simply they do something and then try to get this activity. So you can see this on 12 tungsten phosphoric acid and with a proton. So this is a solid acid. So it's a good solid acid. So we need to know this one. If you know this solid state background, we can understand that one. This is as a one complex anion, complex cation. In terms of complex anion, complex cation, we can understand complex anion, the coordination geometry or coordination polyhedron, then complex cation, coordination polyhedra. If you understand that one, you can understand the structure of those things. So it is at the basic level, it's a gross. If I take as one unit, this one, the complex anion as a big open circle, and then complex cation as a small this working. This organizes a particular fashion. But I have said the corners and the edge centers. Then we can understand that one. How do I alter, modify all these things? We can understand. If you don't know this crystal chemistry, then nothing will can happen here. You just simply add something. Okay, it's a phosphorus there. People look at the down the period, down the column or across the period. Okay, they keep substituting like that one. Periodic properties, right? So this is important. Another one, look at this one. This is again I have taken from the AR West. Crystal structure can be viewed more than one way. Normal view and alternate view. Many a times we don't even know this one. See on the top left-hand side corner. Left-hand side corner, you see this, it's both one and the same structure. By translation and rotation, I can modify that one with the same dimension. This is what it is. An example of how a crystal structure can appear very different, depending on which aspect are emphasized. Is shown in this figure. This is the composition. You look at this one: calcium, copper 3, titanium 4, oxygen 12, in which two diagrams highlight either titanium octahedra and or the TiO6 octahedra or copper O4 square planar units. That means two possibilities of the coordination polyhedra. One representation I can show this octahedra, the other representation I show the square planar. Okay, so we need to understand that one to translate one side to the other side or rotation. That's why we do the group theory. And unfortunately, I don't know how many of this one now group theory they teach well. So that's also an issue. Group theory at the smaller molecular level, we understand it. This is extended. So after that, we need to extend that one. But unfortunately, again, we have issues in this one. So look at this one and the same structures. In some textbooks will be given on the left-hand side, and some textbooks they may give on the right-hand side. But you may get confused whether which one is correct, which one is wrong. But both are correct. Both are correct depending on what we want. If I want to use, say for example, the planar, this one, so I use this one. If I want to use the octahedron for explaining certain properties, I use this kind of geometry. Like that, you can see even at the bottom, there are one and the same structure on the left-hand side, the bottom left-hand side, and the pink one on this one. It is an octahedra in the corner, octahedra in this one. Okay, in one lecture, you cannot understand any of these things. I'm just giving how ignorant we are, that's all. Including me, I was like that when my student days. Because it was, even those days also it was taught in that same fashion. It continues. Of course, today it is little better. Here and there you find some people. So otherwise, it's difficult to understand that. When you go outside the country, you will realize the importance of all these things. Right? Another structure I'm going to show. On the left-hand side, this is a fluoride structure. This is one view, then another view. You see this one, how different these two are. One and the same crystal structure, right? One and the same crystal structure on the left-hand side corner and left-hand side bottom corner. And it's only a translated one. It's a translated structure, and then we need the properties. Only then we can realize the properties. We can understand the properties if I translated this one. See, that's why, as I said earlier, again, the group theory is taught in the master's level, because we need to understand this translation rotation in the molecules or the structures, extended one. Okay, so we need to look at just showing that okay, these are the complexities, or it's not complexities because we don't understand it in a systematic way. So that's why we have the complexity. The other one, simple one, cesium chloride. I can translate this one. You can see at the bottom. So the corners and the edge, this one, body center, I can use this way or that way. Unfortunately, what happens, our teachers tell cesium is the largest one, it should be in the body center. It is not that. You can put a cesium also at the corner. That's because there are other concepts involved. By and large, it's okay, larger size, fit in the larger. It is not this case because its coordination is important. The coordination 8 and 8 in this case. So if the coordination of cesium is 8, fluorine is 8, so one can interchange it. Then if you interchange it, it gives the same dimension. For example, if I interchange also, I get A parameter the same. It's a cubic structure, A equal to the same. If I have a corner of a cesium, if I have a corner of this fluorine, right? So it's like that. So we need to understand that one. So many things, sodium chloride also I can show you that. Okay, not necessary that sodium smaller should be here and then the larger should be here. It's coordination important. So that's why I said, again, when you look into that one, the crystal structure, bonding, properties, application, when you go into the other 4 entities, which is important, are the crystal structure, the oxidation state, coordination, and the composition. As a chemist, we need to know all these things. Each of them will give you valuable information. Each of them, we have a technique, and then we need to look into that one. Those techniques, what are the techniques? That is why we get experimental methods in chemistry. All the experimental methods we learn, because depending on what we want, we can adapt. But unfortunately, these two, the most important courses, group theory and the experimental in chemistry, nowadays it's taught, it's not given importance. It may be taught, it's not given importance to what it used to be, because these two are the important courses if you are a chemist, right? Okay, likewise, I'm just going to know, you will be at class. If I show all these things in one class, if I show all these things, these are all very simple structures. Simple structure at the school level, you are supposed to know all these things, right? And it's only the positions, whatever I said, you see there's a corner, edge center, body center, and the face centers, right? So something like that. So only you can have, with that you can understand so many structures. Unfortunately, again, we are not interested in any of those things. That's why we are like this. Right. Okay. So I just wanted to give you some complexities in solid state chemistry. That's why we are all afraid of solid state chemistry, including me at one point of time. I don't know, because it was not taught well, and then I don't know. So you think we can deviate, but unfortunately, 1 or 2 good teachers were there. They showed something, and then it picked up some interest, and then you find out at the end it is the subject which is important for everybody, not necessarily for the chemist. It is for the science, the basic science, it's important, the crystal structure. So solids, coming back to the solids, because I leave the gases and liquids to the organic, inorganic chemists, the solid state chemists, the solids, we have, you can see this an argon gas, randomly, the structure of matter, you can see argon randomly oriented. Liquids, for example, water, too, reasonably okay because of the hydrogen bonding. And solids, we have 2 classes, amorphous and crystalline. The left-hand side, short range order we have. You can see this one, SiO4 units, silica, this one. Locally ordered, and then it is a long range, it is not ordered because I cannot connect this yellow ones in a perfectly repeated way. But whereas on the right-hand side, you can see the blue ones, it is repeating. So this is the crystalline solids, right? This is how, so we can understand many things through crystalline solids. Right, crystalline solids are important, so that's how we start with the crystalline solid. Today, with the powerfulness, the imaging technique, we can even visualize. You can see this one, the barium titanate of a compound. I can see this one, barium, titanium, and oxygen at the atomic level resolution. The image, I can see this one, and then accordingly, I can look into this one. But for that, one need to have a prior knowledge of what are this arrangement of atoms in the space lattice or crystal lattice. Okay, so it's important. So like in the previous slide, solids can be classified crystalline and amorphous. Okay. The basically crystalline solids are periodic arrangement of atoms, definite repetitive pattern, right? Whereas non-crystalline or amorphous material also called non-crystalline, some textbooks. So amorphous or non-crystalline materials, random arrangement of atoms, locally ordered, and long range order will be missing. Okay. So typically in a layman type of this one, okay, you can see on the left-hand side, see perfectly the space management. You can say space management. Today, if you go to the supermarkets or everywhere it is arranged, and you can look into this one, we know that what is the structure. I don't know how many of you even looked into that. It looks nice, that's all, right? There are a lot of crystal chemistry in that one. On the right-hand side, you see this one. I cannot get anything on that one. It's amorphous. Just the laborer, you ask a laborer, collect something and just put it in somewhere. So you will throw it like this. Whereas person wouldn't, wants to manage the space management, he will do it like this, or even for other purpose, we do that one. So the crystalline solids, amorphous solids, okay, so you can see in the bottom schematic, crystalline solid, repetitive, and amorphous solid or non-crystalline material. So it's this one, non-repetitive structure. This is the basic lesson to start with. Okay. Crystalline materials can be classified into various ways, various properties, like for example, magnetic, electrical, dielectric, or crystal structure, or even bonding. Okay. Here in this case, I have shown bonding. Okay. So molecular structure, molecular solids, or this hydrogen bonding, or the van der Waals bonding, including ice as an example. Ionic solid, sodium chloride, and atomic solids. This can be further classified into covalent and covalent solid or metallic solids. Typically metallic solid copper, and covalent solid your diamond. Okay. So all these are all certain crystal structure, and then okay, why they have this kind of properties. If you understand the crystal structure, we can understand it. So this is only what we know. We mug up everything: molecular solid, ionic solid, or atomic solid, or covalent, or this one metallic or ionic or van der Waals. This is what we know, but we don't know any of the examples. If I even ask, no one can answer that one. I can tell you that. No one can give you the correct answer. Okay, so hydrogen bonded. You can see this hydrogen bonded water. So typically it is hydrogen bonded. So weak van der Waals forces, ionic bonding, electrostatic, and metallic one, and then covalent sharing of electrons. Even here, the same thing, whatever we study extended to the solids. Okay. You can also classify it. There are the structure of matter, or the structures, not necessarily the three forms of this one. There are more forms, like liquid crystals. We have quasi crystals, and also bosons and condensate. There are other forms of the materials can be classified. Okay. So here I'm introducing another, this one, liquid crystal. In the past, the liquid crystal display units, polymers, they are all block polymers. So they exhibit properties between the amorphous and the crystalline solids, right? So this will be important. Another one important is crystalline materials. Okay, you can have single crystal and polycrystalline materials. Single crystal largely used for the structure solving, and of course some electronics or optical properties. The single crystals are important, and polycrystalline, by and large, it is used for all other applications. Polycrystalline material, it's a powdered material, small. The single crystal, you break it smaller and smaller entities, it becomes polycrystalline. That's what it's called, polycrystalline. Single crystal or polycrystalline, monocrystal or polycrystal, right? So this is a powder sample. This is like any other crystals with a definite shapes. Okay, so this is you can see on the bottom one, I have given a bigger single crystal, which is without any breakage. If I break that one, smaller crystals, even this, they're all still in a crystal nature, but they exhibit properties like that. Okay, so liquid crystals on the one side to the left, it's a liquids randomly ordered, and the liquid crystals, what we call mesophases, or it is in between the properties of your liquid and crystalline. But this was used before your LEDs display units. This was most popular, the LCDs, liquid crystal mesophases. This is polymeric based materials, right? Another important recent discovery, it was not recent discovery, it was in the 80s, it was debated, 70s, 80s, 90s, it was debated, and then largely what we call a quasi-crystals. Quasi-crystals, it's completely changed the crystallographic theory, because five-fold symmetry, if you at all you read properly the group theory, so five-fold symmetry is not possible. But if the quasi-crystals today, it showed that okay, it is any kind of symmetry we can have materials. The quasi-crystals exhibits. Only thing is what happens, all the theories are written based on the 2D view, based on 2D views. But whereas this quasi-crystals in 2D, 2 dimension, it will not satisfy that one. In 3-dimensional, this one, it will satisfy that one. So we'll shortly see this one. This is an important material. And unfortunately, again, because of these are all mostly alloys, it's not, the chemist never dealt with this one. That's why a lot of issues came. And once they understood that one, then okay, now it is solved. And then this has got the Nobel Prize in the 2011 for the discovery of this one. Because this is a Don Chashman from Israel. When he was a student in the, his professor did not accept that one. He was thrown out of the lab. You can see this one. He was thrown out, literally was thrown out of the lab for, he was kept on insisting that this is the, this one, okay, symmetry it comes. Because if you can see in this one, the picture on the right-hand side, the spot for the center next to the second one, so you will count 10 spots, 10 spots not allowed, because that will be a 5-fold symmetry. 5 and 5, if I staggered way place it, okay, you get a 10 spots, but 10 is not allowed. But they thought it is a kind of a artifact, or it is not properly done, and so on, right? But this is a composition: zinc, magnesium, holmium. See, with this one, because you have to melt it in the chemistry labs, you may not have the facility, so that's why the metallurgist or material science people, they do it, or physicists, all melting techniques they have. So it was quasi crystal. The quasi crystal, I'll just quickly see this one. What is the difference between the quasi crystal and the conventional crystal? The quasi crystal violate theorem of crystallography. Why? You see this one, 5-fold symmetry, the 5-fold, this one, okay, pentagon. If I connect the pentagon, so there is always generating a space. You can see this yellow space, whereas it's a triangle or a square or rectangle or hexagon. If I connect it, so without any space, it repeats. That is what the symmetry is conserved here. But whereas here in 2 dimensions, it is not conserved. But whereas in 3 dimensions, it will conserve the symmetry. So that's why it is accepted. Today, it is realized also, it is the right one. Okay, so that's why Nobel Prize has been given. And then this has gone into a couple of decades to really understand that one. Okay. Okay, I'll just show this one, kind of this one. Okay, so this is how, see, the space filling model. So when you look into this one, a lot of space is there. If I take a pentagon, regular pentagon, and if I do it in a 3 dimension, this is what, okay, this is your dodecahedron, the dodecahedron or icosahedron. If I connect it, you can see this one, there is no empty space, okay, no white spots here. That means it can connect. Only thing is, it is not as smooth as this one. It's a rough surface. And again, in mathematics, what we know, this is the thin rhombus and thick rhombus. Anyone of you studied that one, at least in my school days or in my college days, I studied this one, thin rhombus, thick rhombus, and the Penrose tiling, which is constructed based on that. Even today, you see all your tiles to home or in the platforms or pavements, everywhere you can see this one, the tiling. What do we call the tiling? It is largely due to the Penrose, the mathematician, who proved that one, okay, it is kind of a structure which is one can generate it. So it is based on this Don Sachsman and the other people have generated this one, thin rhombus and thick rhombus. If you connect it, you can get the geometry is something like your icosahedron or dodecahedron. Okay, this is a simple this one. So that's how it is shown. You can see this one, the pentagon, and then the rhomboid, the 10 and 5 rhombus, okay, or this is 72 and 36. You connect it, you get this beautifully connected, all kinds of this geometry that I don't know how many of you have seen the kaleidoscope. You just break the glass beads and put it into some look view at that one, you will see all kinds of geometries, which is nothing but the quasi crystal type of this one. So again, it is a very simple geometry, and then coordination geometry, polyhedra, the VSPR, what we study in the undergraduate or school, the same thing extended to this one. Okay, so basically it is the Greek philosophers long ago. They have shown matter consists of the 5 entities, namely tetrahedron, cube, octahedron, icosahedron, and dodecahedron. With these 5 entities, we can understand anything and everything. That is the science. Unfortunately, in our part, we don't want science. All we believe. We live largely on beliefs. So that's why it goes. We have 5 entities in different way, right? So there is always, for anything and everything, you have a scientific reason for that one. If you understand it, well and good. If you don't understand, that's why we are the countries with all kinds of difficulties they face. So again, look at this one, generate these quasi crystals, thin rhombus, thick rhombus, whatever way you connect it, you get beautifully, you can connect it. All kinds of structures we generated, right? Okay, what is the use of this one? Is it anything? Why I'm insisting of this one? This is material which is as slippery as the Teflon coating, which are the non-stick utensil people coated the organics, right? It is as good as this one. Plus, this is robust because it's inorganic material. It will not peel off. It is also, the materials are quite safe, not carcinogenic. Whereas the organics always carcinogenic. So it is better. So the cookwares, it is the commercial name, it has come. CyberKnox. There are many other companies today, they make the coating of this one. You will see this one wherever this one, okay, specialized the cookwares. Okay, so that is one of the commercial applications. There are many other applications. This is the immediate application. And because it's non-sticky, one can coat that one and it will not peel off and quite safe. All this based on this common coordination polyhedra. Again, for 12 atoms, we study in your group theory or in your undergraduate or in your school, the coordination polyhedra, starting from 2 to 12. So you see that bent geometry, linear geometry, trigonal planar, trimodal, tetragonal, square planar, and so on, right? So you have this one. You should know this one, the coordination polyhedra. If you don't know this one, again, you cannot understand any of this nanochemistry or nanotechnology. People in this country, again, without even this one, see, as I said earlier, you choose the right material, you make it, it will work. But the precision important, accuracy is important. We will not get anything out. We will not reach anywhere near to that one. So with this knowledge only, we need to go into that one. Okay. This is what I was said. This is simply a mathematics, school mathematics. You can see this in what they call it, a platonic solids, the 5 entities, and which has the vertices, edges, and faces. This is are all very well documented and then well known in this one. So these are the 5 entities which is given, which is a dual of regular polyhedra, which is important truncation, or we get many of this when you miniaturize it. When you go to the nano level, you get all these kind of entities. So wherein you can get the what we call it a regular polyhedra. This is what the regular polyhedra, which is important particularly in catalysis, heterogeneous catalysis. One particular kind of a facet, what we call one particular phase of facet. It's a cube. It is a tetrahedron, for example, 3 connected, cube 4 connected, and this dodecahedron 5 connected, icosahedron 3 connected. Okay, so the selectivity will be at most. So that's why nano is a wonderful subject. It is gaining a lot of importance in catalysis. This is not known new to catalysis people. It is known decades. Unfortunately, only catalysis people today, they view all these things because the imaging technique has come today. In the past, indirectly, we used to derive this information. So this is the molecular geometry to your nano, this one. This is what, okay, you can see the octahedron. If I truncate it, I get a truncated octahedra, which is 4 and 6 connected. If I further truncate it, you get a 4 and 3 connected cube octahedron, and then further truncated, I get a cube. You need to know this one. This is simply a mathematics. If you don't know this one, you cannot do any chemistry, particularly nanochemistry, right? So all these things are happening like that one, right? So all these things come from basic mathematics knowledge. That's why mathematics is a mother of all sciences, and chemists are basically scientists. Anybody you need to know, even a commoner layman. So you need to understand mathematics, even to count his notes, right? So it's important mathematics. If you say that, okay, without mathematics, it was a fashion at some point of time in this country that, okay, without mathematics, you can do science. It is ridiculous. Okay, so you can see that one. Okay. So not only that, in biology, as I said earlier, you can see this on the foot and mouth virus. I said, go into the detail. See this one. Complexity, this is at the atomic level, at molecular. If you look into the right-hand side corner, this is how the molecular looks like. It aggregates into a certain geometry, and then that geometry is responsible for your activities, right? Which comes from your basic chemistry and mathematics. Sorry. Right? I can show many of those viruses, tobacco virus, mosaic virus. You can see this one, icosahedron geometry, and then there is another animal virus. You can see everywhere this, because what is important is how the atoms are, ions, molecule arrange in that one. Depending on that one, we can look into those all other issues. So look at this one, another, all this common virus. You see this one, you go and put vaccine for all these things without even understanding why it is like that, and then how one can avoid all these things, right? So many of these viruses, you go take any biochemistry book, you will see this one, but not to this details. They give all kinds of geometries, and then we connect it to your chemistry or the geometry, then you will understand it. Even dodecahedron, the molecule, C20, H20 molecules, I don't know how many of the organic chemists, they know this geometry correctly, right? There one, okay, you can see this one, the HIV virus. Okay, the carbon nanotube was people used because this is a matching, because the shape of this virus and the carbon nanotubes. quite matching well, and then it can interact easily, and then that's how it can be treated. So again, the geometry is important. What I'm trying to say is the geometry is important. And then if you understand the geometry, then we can do this. The geometry you can understand only through crystal structure. If you don't know the crystal structure, we can understand. So essence is the tetrahedron, cube, and then you can see here octahedron. This we come across routinely, dodecahedron and the icosahedron. These are the 5 entities called the regular solids, regular polyhedra. And then you can see in that one, I've given the first row is the regular polyhedra. The second row, if you're truncated, you get all those things, truncated one, all those truncated one. You get in reality, you get the second row only. If I go to the lab and prepare it, I get the second row. First row is the enzymes or the biomolecules. They have this kind of geometry. That's why we try to mimic that one, because it is not easy to get like that synthetic analogs, right? We try to make that one. So that is what all about it. But we need to understand the chemistry and the mathematics of that one. How do I reach those things, right? So the third one is a deformed one. This is a truncated. Second row is a truncated one. The third one is a deformed. You take a cube and press it, you get a rhombic. This one, okay. Likewise, you get all those trigonal, bipyramidal, pentagonal, bipyramidal. All are distorted one, not this one. Okay, fine. So we need to understand this all comes in the basic chemistry. Unfortunately, we ignore from the school and the college. And then we all come to the beyond master, and then we go beyond everything. Now we also go and teach also after that, right? Okay, again, we need to quickly a couple of I think another 10 minutes I have, so I will just quickly say a few things. Then representation, polyhedral, for example, the representation can be polyhedra can be represented. You can see that the atomic ball and spoke model, what we call as atomic level, this one, a tetrahedron. You can see this one in the polyhedral model. You can see this one, the tetrahedra connected, and then you can have a tetrahedron, this object, and then it is one and the same. You need to understand it. Or even the space filling model on the right hand side corner, it's a space filling model, what we call a space filling model. In reality, it happens like this. So we need to know all 3 views. Okay, we need to understand for the one and the same compound, same polyhedra, same coordination entity. So we need to understand this one. This also is important, right? So you can see this one. Okay, the beauty of this solid state, this one, okay, the polyhedra, this is an dodecahedron, and then so everywhere, since it's a structural beauty, people create all this monuments, structures, and things all over the world. You can see this. This is one particular crystal structure based on this one. This crystal structure is a cristobalite. And then it's a tetrahedra connected corner sharing tetrahedra. Tetrahedra, the sharing can be corner sharing, edge sharing, face sharing, and all these things. Again, it is, if you think it is difficult, it is going to be difficult because we are not exposed to all these things. That's why we keep ignoring that one. Unfortunately, the opportunities are only in this. Okay, we cannot keep doing all through our life, everybody to doing life science for everything, right? So again, this is the policy of the individual countries or individual institutes and so on. Okay, so it has to come like that. So to come to the point, crystals are important. So we should know what are the crystals, what defines the crystals. It is a periodic arrangement. This one can be understood in terms of these 4 entities: crystal systems, Bravais lattices, symmetry, and space group. Everything is familiar to that. Unfortunately, again, we don't know any of those things. Crystal systems, 7 crystal systems, 14 Bravais lattices, 32 point groups, 230 space group. Because this itself is a big subject, but it is not all that. If it start in the very methodically from the early stages onwards, it's easier, and then there's a lot of implication on this. So these are all 3-dimensional lattices. Definition of unit cell we should know. 7 crystal systems. This is what I said. 14 Bravais lattices, lattice plane, Miller indices. All these things are important. You can see a crystal here. It can come as an octahedron or a cube or truncated ones. If you look into the microscope, all these things we need to understand with the basic crystallography. I'm not taking any of this one, but I'm just giving you the crystalline solids, extended one of them unit cell. What is the smallest, simplest repeating unit? You take that, we understand everything. Okay, 1 unit cell, there is crystalline substance. No, it will not exist, right? It is you need to have a critical mass to have a crystalline nature, right? amorphous crystalline solids. I'll just keep all those things in terms of the lattice points. Lattice, imaginary, as I said earlier, mathematics work on the imaginary. They use the terminology lattice, which is without any this one entities. This is just it's like a grid, okay? And then the lattice point, we identify a position with the symmetry. That's the lattice point. What we do is chemists, we put atoms, ions, and molecules in those positions, generate the structure. That's all, okay? It is the imaginary, the lattice. In that, okay, we put atoms, ion, molecules, we generate structure. So in other words, lattice plus the, what they call this as a chemist, we call it as a this one basis, and the physics they call a motive. Okay, there are terminologies. Always the physicists and chemists, they like your quantum chemistry, quantum physics, solid state chemistry, one and the same. But the way they treat it only different. That's all. So otherwise, it's a motive or the basis we use. Lattice plus basis, you give the crystal structure. Okay, so it is defined in terms of the 3 parameters A, B, C, alpha, beta, gamma, and then you generate all the structures. So the 7 crystal system starting from the cubic to triclinic. Okay, so you can keep setting the conditions. You can go from the cubic to the triclinic or vice versa. We can do that one. So here the tetragonal, hexagonal, trigonal, a special case, all other things here also we can see this. This can be further divided into 4 different types of lattices and so on. Any textbooks will give you all these things. You are supposed to know at the master's level or even undergraduate level. So the Bravais lattices, okay, it is not 28, 7 times 4, but it is 14 Bravais lattices. Something will be missing, which will be interconverted because of the symmetry consideration or the definition of the unit cell, because smallest and simplest repeating unit cell and so on. Okay, lastly, that if you look into this, your periodic table, always on the left-hand side corner, it is given, the first one is on the left-hand side small box in that crystal structure. We conveniently avoid, or even in any inorganic textbook, if you take that one of the elements, see the, from starting from hydrogen to your all other elements, you have this one. In terms of groups, they treat that one even there. The first property will be crystal structure, but unfortunately, we ignore all these things, this one, but it's utmost important. So what is important in a crystal structure? You need to know the coordinates of the atom. That is how we generate the structure, coordinates. Back corner of the origin, if I take that one with respect to that, how many atoms are there? We have to give the coordinates, identifying the coordinates. If you find a new compound, we have to give the coordinates, all the exercises only for the coordinates. The number of atoms per unit cell we need to know. The relationship between the lattice parameter and the atomic radius of that this one. And distance to the nearest neighbor, next to nearest neighbor, or a number of this one, density, all these things. There are several other things you can get. All of them are important in this part, right? Like for example, primitive lattice, body-centered lattice, face-centered lattice, the base center, what we call it, a base-centered lattice or end-centered lattice. These are the 4 different lattices. All the compounds will crystallize one of these lattices only. Okay, so likewise, so we can get many other things. Let me skip. So the last point which we, so as I said, the importance of crystal structure, what are the difficulties and things like that. But if you want to understand that, the basic description of the crystal structure, very simple, the position of the lattice points or the position of the atoms, ions, and molecules in the crystal systems, right? Okay, crystals, right? Or the geometry, a cuboid. In other words, the cuboid. The position of the, if I know the 4, what we call a 4 standard position, corner, face-centered, base, body-centered, and the edge center. If I know these 4 positions, I can generate numerous structures, and then I can understand that one. So this is the methodical way. Once this is complete, we can also use the voids, because atom has odd uniform spheres. If I pack it, it generates voids, and then in that voids, I can put this one. So we can generate structures like this, or polyhedral model, as I guess given you that, okay, now this virus as well as this carbon 60, C60 Buckminster fullerene. So we can understand in terms of the polyhedra also, because if it is a complex one, we have to understand, or the heteropoly acid, complex anion or complex cation, we need to understand the coordination based on the coordination geometry, or combination of any of these things. More complex structures, we can have combination of this position, voids, and polyhedra, and finally packing of spheres. We need to understand in this one. None of the textbooks will treat like this. That is one of the problem, because it is depends on largely, because chemists, the organic, inorganic, physical chemists, or solid state chemists, we treat this one, and then each one of them they treat on their own way, on their convenience. But the best way is in terms of description, in terms of the crystal structure, what I have given in this slide. If anybody describes like this, then one can understand, even it is not all that difficult. Okay, so I think its time is up because I keep going on, but there are many things. But what is important in solid state chemistry is these are the things important. Crystal structure is utmost important. We need to understand the crystal structure in terms of the coordinate of the atoms. If I know the coordinate, I can generate the crystal structure. Number two, I need to know this coordination polyhedras, and then I need to know the composition, correct composition and oxidation state. Then we can understand the crystal chemistry, or for that matter, anything. The way I said, the Greek philosopher, we can understand this chemistry, physics, or the science in general. Unfortunately, again, because it's difficult for me also in one class or this one to convince that it is important, because you all will be convinced because you are not come across any of these things, and you will not continue also because difficulties also there. There are many other difficulties. Solid state material to work on a solid in the research level, you don't have the facilities. Even to start with the X-ray diffraction, which is important, powder diffraction, you may not find it anywhere, many places. Okay, so that is the other difficulty. That is because intrinsic difficulty of the individual institutions or the country. People should think what is important. That's why the people called as a thresh or all everything. No? But people should realize this one because largely this is important. That's why we are not everything, even everything we import, when we curb it afterwards, right? Including the polythene bags, right? So it's important to understand crystal chemistry, whether you are a organic chemist or inorganic chemist or physical chemist or even analytical chemist. It's important. The solid state chemistry is the simplest way we can understand the crystal structure, and then you can extend it. That's why it's a first course. When you go to the rest of the world, the first course is the solid state chemistry or solid state materials or materials chemistry, because it is important. Unfortunately, we don't do that way here. Okay, I think Sakti, will I stop here? I think it's time. If I have a question, I can answer the question.
Sure. Yeah. Professor Swaminathan.
Or Professor Swaminathan. I think
Hello.
Yes.
So is it audible?
Yes, sir. Yes, sir. Yes, sir.
So we had a very interesting lecture by Professor V. Selvam, basically, stressing the importance of solid state materials and details of solid state chemistry, and especially the basics of solid state materials. And he has stressed about that, about the 5 entities and also the shapes of viruses. And the thing is, and he should, we now realize that, one who is working in that solid state should first, understand all these things, and then he has to go for that research and other works. So it's a very nice lecture. Thank you very much. And also the only that, difficulty is, as he said, the characterization techniques, which are very costlier, and everybody has to depend on the other places and all these things. Okay. Anybody, any interactions, any questions, please? Hello?
Yes, I can hear.
Sunny, can you unmute everybody so that... Yes, anybody wants, they can please unmute yourself.
Any clarification, any doubts, or general question also, not necessarily related to this one?
Or put a chat box so that we can ask. Sunny, can you unmute? Sir, 1 minute, sir. I will tell the coordinator to unmute.
Yeah, many people are not able to.
Yeah, just a second, sir. Sunny, are you there? Can you able to unmute? Can you unmute everybody? Can you unmute quickly?
Now they can unmute themselves.
Yeah, it is unmuted. Participant, can you please unmute yourself? Can you ask?
And any questions or clarifications you can ask now.
Sir.
Yes, please.
I am Bhavisha from Central University of Kerala.
Yes.
I have a doubt that besides XPS, what are the technique to find out the metal oxidation state of perovskite oxide?
For anything, so the oxidation state, the ultimate technique is oxidation state. It's the XPS for surface, for bulk, what we call as XANES, X-ray absorption near edge spectroscopy. So you take a physical chemistry by Atkins. The last couple of chapters they deal with this one. So some of these techniques, all the techniques. So XPS and this one, okay, XANES, XNES, it's called XANES, X-ray absorption, XANES, X-ray absorption near edge technique for the bulk sample, XPS for the surface. This is the direct technique. This is the direct technique to get this one.
Thank you, sir.
Any other participant?
What is the participant level? What a participant, most of them are research
PhD
students.
scholars and some MS, our MSc students and some MSc students also there.
So mostly PhD students, right?
Yeah.
Okay. Tell me.
Hello, sir.
Yes.
Sir, I want to know about the metal oxides. If I will go into the see the geometry or metal oxide, I will going to the mix the more than 2 metal oxide together. So how I will getting the information whether it is a form or not?
Yeah, X-ray diffraction. You will just do this one. See, each one of the metal oxides will have their own. Say, for example, simple example, if I take a magnesium oxide and aluminum oxide, if I mix it, okay, magnesium oxide, because the crystal structure is different, aluminum oxide crystal structure is different, it will give 2 different patterns. If I heat it, it will form a spinel structure, MgAl2O4, that will have a different structure, that will give you another pattern. So what happens when it is completely formed, it will give one particular structure alone, because these two will disappear. Okay. So the example is there in the AR West book as well as the Smart and Moore. So you can check that one, how you get the mixed oxides into a single phase oxides.
Okay. Thank you, sir.
So this is the direct method to characterize it. Easy method also.
Okay. Thank you, sir.
Sir, I have one small doubt, sir. Normally, in the catalyst point of view, always we look into that mostly the catalytic active species is either the center, active center, which is having a defect sites or which is in the exposed sites. That's mostly catalytic point of view is active sites. But often we go with the preparation of the perfect systems, perfect crystallinity, perfect. What is the how we have to approach for the reaching the best system?
You think it is a perfect, but it is not perfect. When you look into the microscope, TEM, for example, and you go to the atomic level resolution, you will not find that kind of this one. Something will be always distorted or missing, and kind of things will be there. Number one. It is also not necessary that you need to have always a defect, because surface is always a defect. The surface coordination is unsaturated. That is also considered as a defect, because surface is any surface, 100 surface, 110 surface, 111 surface. For example, on FCC metal, if I take that one, surface is under-coordinated. Bulk coordination is 12. The surface coordination is 7, 8, 9. So that is also a defect. It's not that a defect is always it is missing atom or extra atom. Surface is under-coordinated.
But so, the defects are very advantageous, no? Right?
Defects are advantageous. Defects are advantageous. That is okay, no? So that is extra thing. After that, okay, say for example, if I have a copper, I just add a little bit of nickel on that one. Okay, so in the same plane, nickel can go, but that distorts the local structure. So that is a defect. So, and consequently, electronic properties will change. So thereby you get a better activity.
But every time the preparation method differs. I mean, the same method if you are using, we get the different, na, sometimes.
That is the skill. That is the skill. That is why, you know, Even today, Johnson Matthey sells the your platinum and carbon catalyst all over the world. Just a very simple one, platinum and carbon. Anybody can make it, but people go for only for Johnson Matthey. Likewise, TiO2, Degussa or this one, because it's known, but because they have mastered it, particularly with the defects. So that they will not disclose it. The method also they will not disclose it correctly. They will say this method, okay, na? Lastly. So that is up to the individuals, because these are all money making this one. So people wants to make more money. So it's simple. The best example is platinum and carbon. Platinum and carbon, it's see, I have seen that even the Johnson method, it's only one person control. Even only one person last 20-30 years he is the only person making it in small quantities. So 500 gram or 1 kg scale only is making, right? And now they are selling it everywhere.
Oh,
and you
right.
buy the same platinum carbon on different vendors, it may not be as efficient as the Johnson method sample, right? It is again
we cannot prepare that also, no, by training and other things. By
yeah, we can prepare it and then market it. There are big things are there. You may have a better catalyst also, but who is going to market this one? And then this is also a strategy. All kinds of things. If they find that yours is better, they'll come and buy from you everything, including the patent.
So marketing is more important.
Yes, marketing is more important. Which we know for many of those things. See, many company die, many company is merged. All these things because of the marketing issues. Okay.
Sir,
So,
good afternoon,
any more questions? I mean,
sir, good afternoon.
hello?
Sir.
Yes.
Sir,
Please
I'd like
go
to
ahead.
know that answer for that unit cell system. You showed a slide on that unit cells. And at the bottom, again, see similar appearance, but you said they are not exactly the same.
Correct.
So I like to know the answer for that.
So one is, say, for a simple case I take, the body-centered case I take. Body-centered is, the right example is tungsten.
Okay, sir.
Body-centered cube. Many of you may say alpha iron or many other examples. That is not the right example. The right example is tungsten. Below which I just change another color, which is cesium chloride. It is not a body-centered cube. No more it's a body-centered cube, because there is another one is come. It's a primitive lattice, because two different elements or two different ions. Okay.
Okay.
It's not one and the same. Body-centered means by definition, corners on the body center identical atoms.
Okay, sir.
Identical ion, that one. Likewise, on the right hand side I have given copper. Copper is the right example, face-centered cube. People say gold, silver, all these things, but copper is the right example. And then below which I put the face-centered alone, I changed it. The face-centered alone changes copper 3 gold. This is an alloy, copper 3 gold. So total number, if I calculate 3 plus 1, 4, that also 4. But that is a face-centered lattice. This is a primitive lattice. So that's why I said these two are different. This is, you should not call it a face-centered cube. Likewise, sodium chloride also people call sodium face-centered cube. It is not a face-centered cube, face-centered lattice.
Okay, sir.
So these are the things, basic things we need to understand it clearly. If you understand wrongly, it goes to this one. That's what I said. Even today, go and ask a professor.
No, sir. This even 12th standard books. Some books also they are giving it as FCC only.
Correct. Because our professors only write.
No, even if we say people don't accept, sir, it is given in the book. That's what they say.
Because see, textbook is your
reference material.
Textbook. You are bringing it a textbook, no?
Yes, sir.
So when you give it in a textbook, people won't accept it because they want mark, not a subject. See, we live on marks.
Yeah.
Right. See, yesterday also I introduced this one MSc students. No, people don't understand many of these things because we all pass today. Everybody gets over 90%. Right.
Okay,
you ask one simple question. This one, okay, nobody will answer.
So one more question, sir.
Tell me.
Truncated structures you are showing,
Yes.
right?
Yes.
Can we reach that mathematically, sir?
Mathematically only we can reach first. After that only this one in reality.
Okay. No. What is the relation that connects that, sir?
No, mathematically, see, they want to evolve this one. connected. See, when I take an object, I truncate it in a regular fashion.
Yes,
See,
sir.
1/4, 1/2, right?
Yes,
I
sir.
truncate it.
Yeah.
So when I take a cube, if I truncated the corners, you get a triangular.
Yes.
Okay.
Yes, sir.
So you get a 3 and 4 or 3 and 6 connected one. So two different surfaces, the atom arrangement will be different in that.
Okay.
If I see the atom arrangement, if I take a cube, that arrangement will be different. If I truncate it, because you are viewing another angle, right? When I truncate it, it is you just 45 degrees we can truncate, 30 degrees we can truncate, we can 60 degrees we can truncate, right?
Yes, sir.
So the exposed atom will be different. That's what, when you go to the reality, the atom arrangement will be different in that phase than the other phase. So your activity will be different.
Okay. Okay.
So all this, the three things I said, regular polyhedra, truncated polyhedra, and the deformed polyhedra or distorted polyhedra. This is possible, mathematically proved.
Okay.
We have written theories, corollaries, all these things. Okay. So
Yeah.
what we are trying to find out is whether we have anything matching to that one.
Yeah.
So that's what we are trying, mimicking. In other words, we are trying to mimic that one. The
Okay.
chemists, we try to mimic whether I can create that kind of structures. So today it is possible, everything is possible at the nano level. Yes, we do have example, nano level. We do have example for any of those things.
Okay.
I have shown there.
Okay.
Hmm.
Okay, sir. Thank you, sir.
Okay, thank you very much.
Sir, good afternoon, sir. I am Raman. Sir, I am asking a general question, sir. Some people say that getting even a single crystal, it may not give perfect geometry. Is it true, sir? What is your opinion, sir?
Correct. This is what the theory is. Solids at only 0 Kelvin only, it is perfect.
Yes.
Okay, anything at 0 Kelvin only is perfect. You just start eating, you start with the defects. It's always defect. Without defect, nothing happens. Only thing is the amount of defect varies, that's all. The amount of defects varies. So, which is, for example, sodium chloride. If I take a sodium chloride, there's a defect, Schottky defect. But when you increase the temperature, very high temperature, only it will conduct. Otherwise, it will not conduct ionic conductivity. Why sodium chloride is not exhibiting ionic conductivity under normal condition? Because the defects are limited, and then it will not migrate to one place to other place. But whereas if I cool it sufficiently low temperature, only 0 Kelvin, perfect solids. That's what they were the third law, thermodynamics, right?
Thank you, sir. Thank you, sir. Thank you very much.
Okay.
Yes.
So shall I conclude? I mean, any
sir.
more questions? Okay. Thank you very much, sir. We have a very, very nice lecture, all details about the solid state chemistry, and particularly, I mean, stressing the importance of understanding the solid state chemistry. Thank you very much, sir. Thank you very much for your interesting lecture. Thank you.
Thank you, Professor Swaminathan, Professor Saktivel, and ISCAS for giving me an opportunity to express my view on this subject. Thank you again.
Thank you, sir. Thank you, sir. So you have shown that what one should do before starting the chemistry or even the science, that you have shown that it is very important for especially for us as well as all the audience. Today we had three eminent speakers, keynote lectures. One is by Professor Selvam sir. He has shown about the fundamental aspects of solid state chemistry. Then we had a Professor Ajay Veenu. He talked about what is the current scenario, what is the contribution of the solid state chemistry in the current scenario. He talked about, and then Professor Ramasamy, he expressed about that how the theoretical study is helpful for the solid state chemistry. So we had a very good session today, and thank you, Professor Swaminathan sir, for sharing the session. Thank you once again, sir, Selvam sir, for your accepting our invitation and sharing your wonderful motivating talk, sir. Thank you, sir.
Yeah, thank you very much. Thank you. All the best, all of you.
Yeah.
Thank you, sir. Thank you very much, sir.
And dear participants, the oral session, oral session will start at 1:50 p.m. So all of you, those who are having oral presentation, please join sharply using the same Zoom ID by 1:50. And evening we have the again two eminent speakers. One is from industry, that is Dr. Vijay Sangar from Reliance Industry. He is going to talk about how scanning imaging methods are important to understand the solid state chemistry. Then next is Dr. M.E. Reddy. He is going to join from Canada. So all of you, please join back sharply at 1:50 for oral presentation and 3:50 for the keynote lectures.
Okay, thank you for the opportunity to give the chair session. Thank you very much. See you.
Sure, sir.
Sir, I request everybody to fill the attendance form. So 2 attendance form will be there for morning session and afternoon session.
Sir, Swaminathan sir.
So please fill now the
5 o'clock validity function. We have Swaminathan sir.
Okay. Hello.
5 o'clock there is a validity function, sir.
Sure. I'll be there at 5 o'clock. No.
Yeah, sure. Okay, sir. Thank you.
Thank you.
All of you. Okay. Sunny.
Hello. Yes, sir.
Sunny, 1:50 we can start recording. Now we can pause.
Sir, recording. I have paused the recording. YouTube live will be active. We can start at 1:50 or whenever you wish. You can just.
We can start at 1:50. 1:50. Yeah.
We'll be starting at 1:50. No, sure, sir.
Thank you. Dana, are you there?
Sir, myself present.
Nimishava?
Yes, sir. Dana will join, sir. Meanwhile.
Okay, no problem, no problem. Just another 5 minutes.
Okay, sir.
First presenter is ready.
I think Bhavisha is coordinating, sir.
Sujit,
I'll ask her.
Sujit is ready, sir. I'm ready. From
Okay.
PPS, sir.
Yeah, fine. Wait. Raman sir, you have the list of the candidates. Raman sir?
Yes, sir. Yes, sir. I am
You have
having
the
the
list of the-
yes, sir, yes. Starting from OP 15 to OP 22.
Yes.
OP 22. Yes, sir. Yes, sir.
Just Dr. Ravi is having lunch. Just
Okay, okay, no, okay, yeah, no.
So strictly time 8 minutes. All the oral presenter, you should presentation should be within 8 minutes and 2 minutes for the question and answer.
Hello, sir.
Hello, sir.
Sir, shall I share the screen? Shall I check whether it's working or not?
Okay, sir. Yeah. So you just contact the administrator. Yes, sir. Yes, yes.
Okay.
Yes, yes.
He can try. Sujit, try.
Okay, sir. Thank you.
Dr. Ravi Kumar has joined. Good afternoon, one and all. Sujit, can you just find Sujit? Sujit?
Yes, sir.
Yeah,
Okay.
stop presenting.
Yes.
Okay, good afternoon, one and all. Welcome back to the second session of today's national webinar. Today we have this session we have the 6 oral presenter. There are total 8, but 2 of them may be absent. So total 6 oral presenter is there. And Dr. Ravi Kumar and from our Central University and Dr. Raman from VHNSN College will be the panel judge for the evaluator. So I welcome you, both of you. And Nimisha, can you proceed?
Yes, sir. Good afternoon. We are moving to the OP session. So here there are 2 judges, Dr. Ravi Kumar Kanarpati and Dr. N. Raman. A brief profile about the judges. Dr. N. Raman, Associate Professor Chemistry, VHNSN College, Tamil Nadu. He has completed his PhD from School of Chemistry, Madurai Kamaraj University. He has been a teaching faculty in VHNS College, Tamil Nadu since 1991. He has been the recipient of Best Teacher Award of the year 2011, awarded by Chemical Research Society of India, and has also been the recipient of Professor C.N.R. Rao Best Scientist Award, which was awarded by Post Science Society established under TNSRO. He is also the recipient of several other awards. He specialized in bioinorganic chemistry, chemical biology, and biochemistry. He has more than 200 publications in peer-reviewed journals and has guided more than 25 research scholars and more than 70 MPhil students. The next judge is Ravi Kumar Kanarpati. He joined the department as assistant professor in 2013. He was a recipient of DST Young Scientist Award in 2013. His main research focuses on harvesting the solar energy, material synthesis, photovoltaic and optoelectronic devices, and nanomaterials, especially for developing new efficient sensitizers for dye-sensitized solar cells. He has published over 20 research articles in peer-reviewed journals and is also the reviewer of leading scientific journals of various publishers like ACS, RSC, Elsevier. On behalf of the organizing committee, I welcome both of the judges for the oral presentation. And I request the candidates to present within the restricted time limit of 8 minutes. I now request Dana and Bhavisha to take over the candidates for the presentation.
Okay. First we have S. Sujit. Sujit, please.
May talk 1 minute.
Wait. Let Dana, let Dr. Ravi Kumar and Judge Dr. Raman.
Raman sir, good afternoon. Nice to meet you.
Good afternoon, sir. Good afternoon, sir. And I am very happy to associate with you.
Yeah, thank you.
Thank you very much.
I think there are some guidelines already disclosed, but then it is our duty. I think we can speak out those guidelines for the benefit of the presenters, especially the student presenters. With your permission, I can read out the guidelines, especially the instructions. Dear students who are going to give the presentation, you should restrict the time to 8 minutes for the presentation, and you should give 2 minutes for the judges and also the audience to interact with you. And please remember, when you are presenting, you should the evaluation is based on 4 elements. One is the content, what the research work that you have carried out, and the clarity of the presentation is the another criteria. And then the time limit, whether you are restricting the time limit or not, that is another parameter, because this conference is very, very highly demanded conference. We don't want to extend and then kill the time of the other session. So we wanted to maintain the time. And also the question, how you are answering, basically how the understanding levels will be judged based on the questions by judges as well as the participants. So these are the 4 elements on which the presentation will be evaluated, and then the best 2 presentations will be picked up from this session, if I'm correct. Right, sir? Satyawal, sir?
Yeah, correct. Yeah, yes.
Now you can proceed, please.
Sir, first we have OP15, S. Sujit. Sujit, please.
Sir, I will share my screen. So my slide is visible?
Yes, yes. Yes, sir. Yes, sir.
It's visible now, sir?
Yes, yes. Your slide is visible.
So you want me to on the camera, sir?
Yeah, that is better, please. And also just to change the slide also, just to change the slide.
Move the slide, Sujit.
Yes, sir.
No, in the full screen mode itself. Yeah.
Go to the next slide.
Sometimes it may trouble you. That's why we are asking.
Yeah. Thank you, sir. Thank you for the guidance.
Yeah.
Sir, shall I start, sir, now?
Yeah.
I'm Sujit from Bangalore. I'm currently working under Dr. Ganapati V. Shanbhag. Today's title that I'll be discussing is presenting is the transformation of biodioride furfural alcohol to yield alkyl lignets over zeolite catalyst. So world is running behind the energy, and biomass is considered as one among them. And the feed stock that which you have taken is that furfural alcohol, and it can be produced from furfural to furfural hydrogenation to furfural alcohol. And furfural alcohol has got series of applications where it is used in solvents, etc. Resins. Why furfural alcohol to alcoholysis of furfural alcohol to alkyl lignets is very important, because this furfural means furfural alcohol to alkyl lignets, that is alkyl lignate, has got a series of applications, and synthesizing alkyl lignets from route 1 is, that is levulinic acid esterification to butyl lignets. It is highly expensive and it is commercially practiced right now. But route 2 is more feasible because it is more economical because of high reactivity of this. But here the challenge here is that conversion of this intermediate compound, that is alkoxy methylfuran, is one of the important step here, and it should undergo ring opening reactions and to yield furfural alkyl lignets. This is the general reaction mechanism scheme where I said that alcohol ether formation followed by the ring opening reaction, it should yield alkyl lignets. Here the general application of alkyl lignets is they are used in as a food additives, fuel additives, and the intermediate also has got a very good application in food additives and flavoring industries, and it has got several applications in a chemical as a chemical intermediates and plasticizing agents. So coming to the literature survey, we found that many catalysts has been reported, and these are the best catalysts that have been reported, has been screened down here. One or the other way, this has got one of the other drawbacks. So it has been highlighted over here that high catalyst loading, high reactant mold ratio, recyclability issue, and difficult synthesis procedure. On this account, we wanted to know the zeolite has been also reported, but it is not studied heavily. So zeolite has got various of advantages. So in this regard, we synthesized ZSM-5 by using tetrapropyl ammonium borate as a structure directing agent, and the XRD pattern matches with the reported. And we also procured some other SAR ratios from 23 to 120, and we did XRF, and we found these are the SAR ratio of it. We did other modification for the best catalyst, and that is for desilication, dealumination, metal ion exchange, and phosphate modification. Here, base treatment, acid treatment, and copper ion, copper nitrate, and zinc nitrate, and ammonium dihydrogen phosphate. And all these three methods has been calcined under 550 for 5 hours, and except for phosphate modification. And we did the characterizations along with other conventional acid catalysts, that is Y-zeolite, beta-zeolite, and modernite. And these three catalysts been synthesized in their lab, and it matches with the report. And even after the modification of ZSM-5 SAR95, the structure has been retained. So going down to ammonia TPD, the ammonia TPD profile also says that it has got the same as per the report, and followed for same thing goes for the other conventional report. And where you have the for ZSM-5, we know that typically that we can moderate acid site dominates, followed by the strong acid sites. So we did the physicochemical property for surface area, pore volume, and acidity, and all these values matches with the reports. And when we did modifications for SAR95, which gave the very good activity, the acidity decreased and over the modifications, and basically the strong acid sites has been decreased from the TPD profile, which we can see here. From B, C, D, E, the strong acid sites of 95 has been decreased. So in this regard, we did scanning electron microscopy and the spherical-like morphology. And this is the batch mode, what we carried out the catalytic reaction. And these are the catalytic activity studied. These are as follows. Heading to the catalytic activity study, we did screen that Amberlist 15, ZSM-5, and modernite, and so on. We found that Amberlist 15 ZSM-5 gave a very good activity, but the selectivity for Amberlist 15 was high compared to ZSM-5. It was very interesting, and then we carried out the recyclability study for the Amberlist 15. Over the 4 cycle, and the catalyst, the selectivity for this catalyst decreased. This is mainly attributed to the thermal poor thermal stability, and which cannot be regenerated. We tried other methods also by washing with solvent, and basically this Amberlist 15 they bulged. So heading the next best catalyst is the SAR, that is ZSM-5. So we did vary the SAR silica alumina ratio from 22 to 160, and we found that SAR95 was very good. And this can be attributed to the low SAR ratio. They didn't. They showed very poor solubility mainly because of oligomerization, which gave a lot of side products. And for SAR 120 above 100, they didn't perform very well. That is because of poor low acid density. So we got this alkanic pot. Further, we went for the several modification, and nevertheless that unmodified SAR95 only gave the best, and that can be attributed to the pyridine FTR, and also from ammonia TPD, where we found that the strong acids and sites only, bronchial acid sites only worked for this reaction, and that can be also seen in the convince when we screened that ALSB15 and sulfated zirconia. So this was clearly evident for us, and we further went for the reaction conditions, and we found that the best condition where we did number of recycles, the activity remained same, and only the 2% marginal decrease in the 2% of the selectivity of beta aluminates. So we confirmed, we did the reaction for 24 hours, and as the BMF selectivity that decreased, the beta aluminate selectivity increased over up to 85%. Then the conversion was stable throughout the reaction, and we did the different substrate studies: methanol, ethanol, propanol, and butanol. And for beta aluminates, the yield was more than 60. With this, we compared our results with the reported literature, and we found that our catalyst overcame all the other drawbacks, and this found to be very good. So this can be the summary and the conclusion of this work is that because of the inherent property of ZSM5, that is micropore structure, high surface area, and strong bronchial resistance, nominal amount of acid size and thermal stability, which gave a very good activity for this thing. And other things are that under optimum condition, which we obtained is 95% conversion and 85% selectivity. This can be attributed to the moderate acid site spacing. And upon post modification showed very good conversion, but less efficiency compared to the strong unmodified catalyst. So according to the Green principle, our catalyst performed best, and it's the best candidate for transformation for this particular conversion, that is perfluorol alcohol to beta aluminates. Thank you, sir.
Thank you, Mr. Sujit, for your presentation. What is the expanded form of PETH ZSM5? What type?
MFI framework, sir.
What does it mean? Whether it has any significance or?
Mobile were the first person to. Sir, Mobile were the first person to synthesize this thing. Zeolite, mobile people, sir.
What about whether you are using whether your catalyst, how many times it can be used?
We can use up to four recycles, sir. We studied up to four recycles. Four recycles.
What happens to the then after four times? Catalyst.
Fourth time we didn't check, sir. Up to four cycle we did it, and the selectivity and this thing didn't vary because we checked the XRD also. The structure has not varied, and we checked the acidity also. There is only like 2% or 3% decrease in the acidity.
Okay.
The structure is very stable, sir. That is why Zeolite 8095 was very good.
Whether you purchased this, I mean the catalyst, or you preferred this?
Yes, sir. SR, 1 second, sir. Here it is there. This is the last one. 160 we synthesized it. The other things we were purchased from Nankai.
Okay. Sir, okay, sir.
Any other questions, sir?
Yeah. So can you just suggest some names, some characterization techniques, how to characterize zeolites, especially from XRD?
Well, sir, question was not clear, sir. Can you see me? What I have to suggest?
See, why did you take the zeolite?
Okay.
Yeah. Okay. The reason it is what is the reason? Can I? May I know?
Sir, zeolite has been reported in this, for this reaction, it has been reported, but it was not well thoroughly studied. It was compared. So we were interested to know why this, like other conventional systems along with the ZSM5, why this catalyst is very good. Because the zeolites can be modified into many aspects, and for this reaction, perfluorol alcohol will undergo resinification or polymerization. So that will give very.
That's where my point is. I think if you know how your process is different from the reported process.
Our process, sir.
Yeah, in which way it is different? And if I'm correct, there are several reports using zeolites and then conversion of this perfluorol to the levulinic acid or acid derivatives or value added products in general.
Sir, can you speak a bit loudly, sir? Your voice is kind of a little low.
Hello.
Yes,
sir. Am I audible? How your
you're audible now. You're audible now.
How your process is different from the reported literature?
Okay.
Because
okay.
there
if we
are
take the
several
reported,
reports.
sir, people have used a lot of ionic liquids, MOF, and this thing. But zeolite is already like well known. It's well practiced synthesis method. So and it is also commercially available. So based on this, this catalyst synthesis part will be not that tedious. And apart from that, we already know like how the zeolites are. It's been studied from last 50 years or like more than that. So based on this, we can easily understand the reaction, and we can bring the very good scientific inputs out of it. And also these zeolites, they withstand many vigorous conditions, sir. In this reaction, we found that recyclability is one of the main issues.
Okay, so in your case, but you have done only up to the 4 cycles, right?
Yes. For batch
How
reaction,
can you
4
claim
cycle
that?
is
Yeah,
more
how
than.
can you? Yeah.
For batch reaction, no, sir, 4 cycle is what we have done. I think even for 5th cycle also, there will be no much decrease in the activity.
Okay.
We can guarantee, because when we did that spent catalyst characterization and even that TGDTA studies for the spent catalyst, the weight loss was very low, and even that XRD pattern also revealed the same pattern. There was no change in structure.
Okay. All right. We don't have time. Already we crossed 2 minutes.
Okay, sir.
May I know last thing, whether this work is published or not?
Yes, sir. This work is published in the Molecular Catalysis.
Okay. And then any one question from audience, please.
Yes.
Anyone can just open up your name or chat box. Any question is there? I think there are many requests.
No questions. No questions.
Shall we proceed for next, sir?
Yes, sir.
Thank you so much, sir. Thanks for the organizers for giving me this platform. Thank you, sir.
Okay. Thank you, Sujit.
Thank you, sir.
Thank you.
Thank you, sir. Thank you, judges. Bye.
So,
yeah.
Next we have OP16, Dr. R. Selvin Josephus. Selvin, sir, please.
Can I share the screen?
Yes, sir.
Dr. Ravi, you can proceed with the once it's complete, you can proceed. You don't need to wait for me.
Yeah.
Fine.
Can I start?
Yes. Yes.
Okay, good afternoon. I am Dr. Selvin Josephus from Maruvanis College, Tirunelveli. My topic is about fissile synthesis and structural characterization studies of zinc oxide nanorods via thermal decomposition method. A small introduction about zinc oxide nanoparticles. Normally, zinc oxide nanoparticles are used for solar cells, photocatalysts, electrical equipments, and gas sensors, etc. One of the important advantages of using nanorods, nanowires, nanobelts, nanotubes for field emission in their high aspect ratio. Zinc oxide is a N-type semiconductor with a band gap of around 3.4 eV and a large excitation binding energy of 60 MeV and an excellent thermal stability. This is the structure of hexagonal Woodside zinc oxide. Next, I am going to discuss about the synthesis of zinc oxide. So, zinc oxide may be synthesized by many methods. One of the methods I have chosen for this study is thermal decomposition method. For the preparation, I have taken 10 grams of zinc acetate dihydrate and ground it well for 1 hour and annealed in an alumina crucible at about 350 degrees Celsius for 3 hours in a muffled furnace. After the heat treatment was completed, cooled at room temperature, the product obtained was zinc oxide. And the zinc oxide was subjected to various characterization studies. One of the important studies about X-ray powder diffraction study. This is the XRD pattern of zinc oxide nanorod. It is shown in the figure. So X-ray diffraction peaks were identified to match the hexagonal zinc oxide crystalline with Woodside structure. And all the values, all the peaks present in the zinc oxide material matches well with the JCPDS card number. And next, I am going to discuss about the infrared spectroscopy. The stretching frequency around 530 centimeter inverse corresponds to zinc oxide material. This helps the characterization of the zinc oxide material of the formation of nanorod shaped zinc oxide particles. Next, I am going to discuss about field emission scanning electron microscopy. So this is the FE sum of the zinc oxide material. Here, the aspect ratio of zinc oxide nanorod arises, that is the surface ratio is about 290 nanometer and 69 nanometer to exhibit the Bohr emission properties. The surface aspect ratio of zinc oxide nanoray is about 3.2. Here that the results, that is surface aspect results, shows that the optimum density and the surface aspect ratio of zinc oxide nanorod have high efficiency of field emissions, and it confirms that the nanorods, the FE sum image clearly indicate the nanorod and created a strong dependency as the aspect ratio and the density. And next, I am going to discuss about EDAX, that is energy dispersive X-ray spectroscopy. So like elemental composition and the distribution of nanoparticles through the spectrum of zinc oxide, there is a purity of the zinc oxide material can be obtained by this redox analysis conformist. And next I'm going to discuss about the optical properties. And in this UV visible spectroscopy, zinc oxide material 350 degrees Celsius was scanned, and the absorption band occurred at 395 nanometer. It is similar to that of the bulk zinc oxide material. The blue shift denotes the decrease in the size of the particle and increase in the band gap energy. The band gap energy value was calculated, that is by 1240 divided by lambda. So the lambda value is 395. So the band gap value of zinc oxide is 3.14 eV. And considering the large surface area resulting from rod-like zinc oxide particles, it exhibits a good photocatalytic ability for dye degradation. Next, we made an attempt for thermal studies. The thermal decomposition studies were carried out for the zinc oxide material. It was decomposed up to 800 degrees Celsius, and the weight loss was good agreement and estimated theoretically. And the TGA data in the same plot shows that no prominent peak was associated with exo and endothermic nature of the thermal weight loss reactions occurred during the TGA experiments. And finally, photocatalytic activity, that is about that photocatalytic activity was studied using the photocatalytic dye degradation of methylene blue for zinc oxide samples were investigated at various time intervals of 0, 15, 30, and 45 minutes and 1 hour time intervals. And we have the concentration of 10 milligram per liter. The lowest degradation was noted for 45 minutes here, 0.04 absorbance, and the highest degradation was noted for 60 minutes degradation. The degradation efficiency is decreasing with further increase in radiation time. Conclusion: zinc oxide nanorods were prepared by thermal decomposition method. The crystal structure was identified by powder XRD. The results of X-ray pattern shows that all the peaks can be well defined to zincate phase of zinc oxide. FESM image shows that zinc oxide nanoparticles assembled in one-dimensional order to form the nano rod-like confirms the formation of nanorods. The band gap value of zinc oxide is investigated by absorption spectrum. Thermal decomposition studies were identified by TGA studies. Finally, photocatalytic applications, the degradation of methylene blue dye in presence of sunlight. Thank you.
Thank you, sir, for your presentation. Nice presentation. Why do you choose this zinc oxide for the nano rod preparations?
Actually, there are so many methods are there. Normally,
Yes,
nano rods hydrothermal method is preferred, but here it's very simple and cheap method.
What is the purpose of choosing zinc oxide? There are so many
zinc
oxides.
oxide, that is for the application-oriented studies of photocatalytic as well as paint, mainly for paints. Paint applications I wish to study.
For photo degradation purpose, you are using a methylene blue.
Yeah.
Dye.
Yeah.
Why not to choose other dyes? Whether you have used other dyes?
Yeah.
Other type of dye.
Yeah.
Whether
Normally
it is applicable to other dye?
Yeah, we can. It is applicable to other dyes also.
But most of the people they are choosing a methylene blue for the photo degradation. Why? Is there any specific reasons for choosing the methylene blue dye?
Yes, sir. Actually, when you are doing in methylene blue dye, you are getting more type of application source, and the results are more accuracy.
In environmental perspective, is there any harm to the environment? Whether
environmental aspect also is good.
Aspects. What is the effect of your methylene blue? Is there any environmental harm to
water pollution side?
What is the size of the the nanoparticle?
Here it is, I think nano rods, we cannot say the size, but maybe around very small size.
Whether it is in the range of nano range or micro range. But that is why I am asking whether
less than 30 nanometer.
30. Okay, thank you. Thanks. Okay, sir.
Yes, sir.
Yes.
Thank you. Mr. Selvin, I have few queries.
Okay.
I think similar to the queries raised by Raman sir.
Okay.
See, in methylene blue, you have used it and then you have tried to establish the photocatalytic activity of the zinc oxide nanoparticles.
Yeah.
But then I don't see any spectrum for that data. You are only showing some numbers. So do you have a spectrum?
Yeah, it is carried out in UV visible spectrometer.
Yeah.
Actually, we carried out direct sunlight. We carried out. The samples were kept in direct sunlight, and we have.
I understand. How did you do that? So here you are showing only. I don't see the spectrum. I want to see when you add the photocatalytic activity to the methylene blue, what is happening to the methylene blue?
I think, sir, you are asking about the color change of the samples, sir.
Yeah.
Yeah, okay. Not shown. I have not specified in the slide.
Okay. So what will happen after the photocatalytic activity? What will happen to the methylene blue? Is it a biodegradable and is it environmentally friendly?
Environmentally friendly only.
How can you say? Did you characterize any the byproducts after the photocatalytic activity?
No, because I have referred literatures. So on the literatures.
Okay. Yeah. Can you cite? Okay. If you have referred, you just spell out what are the byproducts after the photocatalytic activity.
Yes, sir. I'm not here.
If you have already referred the literature, what is the byproduct after the photocatalytic activity? Okay, all right. And the other question that I have is that, did you try that? You say that your method is somewhat unique or a new method for preparation of zinc oxide nano rods. Have you tried really any other parameter to change the variation of the aspect ratio of the nanoparticles and their subsequent application in the catalytic activity?
No, actually, we tried it about only one temperature, only 50 degrees Celsius for 3 hours.
Okay. So you just prepared at one temperature and one shot you got the results.
Yeah. It's about a small project work. That is why I stopped this step.
So you are basically PhD student or?
Yeah, I'm an assistant professor in a college.
Okay. All right.
The students have carried out this work.
Okay.
Unfortunately.
Okay, right. Thank you. And maybe audience, please, if you have any questions, please post or you can let us know. We can enable. We have 1 or 2 questions, time for 1 or 2 questions. All right. I think if there are no questions, so let us move to the next person. Thank you, Dr. Selvin, for presenting nice work. And the next person is Anil Singh. I hope that Anil Singh is in the audience. Can you start sharing your presentation? Yeah. Please keep it in the full screen.
Yes.
Anil Singh Purohit, right?
It's not changing.
Okay.
Keep it in the full screen.
Yeah, F5.
There it is. Yes. Now it's good.
Move the slide to next slide. Yeah, good. Yeah, you can start. Thank you.
You see, you can start. I think there is there any problem? So is there any?
Anil, if you have any problem, you can chat audio. If there is any problem, type it in the chat box so that we can come back again to you. We can go to the next person. Headset is not working. Okay, all right, Anil, you take just maybe after some time when it is ready, you will let us know in the chat box. We will come back. I hope that next person is ready. Sunesh.
Yes, sir.
Sunesh. Are you available?
Yes, sir.
Anil, Mr. Anil, can you just zoom out? Leave the stop sharing the presentation.
Bhavisha, can you talk to Anil too? Bhavisha or Dana?
Yes, sir.
Okay, just to talk to them and
OP80. OP80. Yes.
Yeah.
Sir,
yes,
is it
sir,
visible?
Yes.
Yeah, it is visible.
Yes.
Audible, sir?
Yeah, you are audible.
Shall I start, sir?
Yeah, yes, sir. Just to say one or two words about where you are from and what you are doing.
Yes, sir.
Yeah.
Good
Thank you.
evening. I am Sunish Assam, PhD research scholar, Department of Chemistry, St. John's College, Anjan. The topic of my research, presentation is solar hydrogen production in direct sunlight, a comparative study between TiO2 and metal ion doped TiO2 nanocomposite thin films. First of all, introduction. And now a huge energy crisis demand new alternative energy sources. So TiO2 based solar hydrogen evolution is a best alternative. In this figure, it can be seen that TiO2 can absorb sunlight, and electrons and holes can be produced. So using these electrons, this TiO2 is enabled for producing hydrogen from water. This is possible only because its band position of the conduction band position of TiO2 is higher than the redox potential of H2 bar H plus. That is why it can produce hydrogen from water. But the one disadvantage of TiO2 is its large band gap, that is 3.2 electron volts. So it can absorb only visible UV radiation. But sunlight consists of about 5% of UV radiation. Next one disadvantage is the fast recombination of electrons and holes. So many strategies are developed in the recent years for improving the photocatalytic activity of TiO2. Some of them are depicted in the figure. That is, to improve the photocatalytic activity of TiO2, these materials can be used. First one, noble metal loading or non-noble metal loading, non-metal deposition, non-metal doping, using low band gap semiconductor incorporation, utilization of carbonaceous material, and dye sensitization. And here I use this low band gap semiconductor for improving the photocatalytic activity of TiO2. This is because low band gap semiconductor can form effective heterojunction with the TiO2, and so the electrons and holes can be effectively separated. Here we use oxides of iron and cerium as low band gap semiconductor. This is due to the following facts. Formation of effective heterojunction of this Fe oxide and Ce oxide with the TiO2 that I already mentioned. Then tunable redox properties of these materials and the ability to absorb visible light. So my objectives of the work are synthesis of TiO2, Fe doped TiO2, Ce doped TiO2 samples. Next one, characterization of synthesized samples by powder XRD and UV visible measurements. And then comparison of the photocatalytic activity of sample in the form of thin film. Mainly the activity in solar hydrogen evolution in direct sunlight. Synthesis of photocatalyst. And first of all, the schematic representation is already in figure. And first of all, the synthesis of Ce doped and Fe doped TiO2 is I am going to explain. First, we have to take a mixture of titanium isopropyl oxide and metal ion source, and it is treated with the glacial acetic acid dropwise and then followed by water in dropwise. Both are under magnetic stirring. Then we get a titanium tetrahydroxide colloidal form. This is again treated with a nitric acid and polyethylene oxide along with the formamide. Both are under ice cold condition at 30 minutes under magnetic stirring. So we get titanium gel. And this titanium gel is kept for 24 hours at 60 degrees Celsius. So we get a hydrogel. And this hydrogel is again subjected to solvent exchange using isopropanol and N-hexane. And it is kept for 48 hours at 60 degrees Celsius. Then we get a dry gel. And this dry gel is again calcined at 500 degrees Celsius for 5 hours. So that we get iron or cerium doped TiO2. For convenience, iron doped TiO2 is represented as TiFe and cerium doped TiO2 is represented as TiC. And to get bare TiO2, for getting only pure TiO2, in the first step, we have to exclude the metal ion source. That is why only using the titanium isopropoxide initially, the last product is bare TiO2. And next characterization, first one powder XRD. Powder XRD pattern is in the figure. Here it can be seen that the broadened peaks indicate nanocrystalline nature of the material. And by identifying the peak positions, it can be seen that all peaks corresponds to anatase phase of TiO2. And in all figures, the peak positions and nature of peaks are similar. there is no peak corresponding to cerium or iron, which indicate that cerium or iron is present in minute amount and it is highly dispersed. And next, UV visible measurements. Using the data of UV visible measurements, the UV visible absorption spectra and Kubel-Kommung plot is drawn. And in UV visible absorption spectra, it can be seen that the absorption of TiO2 is very poor above 400 nanometer. That is, it is only UV active. But TiCe sample and TiFe sample can absorb above 400 nanometer. That is, it can extend its absorption above 400 means it is visible and UV active. And it is also identified from this Kubel-Kommung plot. Here the band gaps are shown in figure. TiO2 has 3.19 band gap, so it is UV active. But TiC and TiFe samples, there is a narrowing of band gap. And the band gap is lowest in the case of TiFe, that is 2.51. So it has a wide range of absorption. And next, the comparative study of photocatalytic hydrogen evolution activity. The photocatalytic activity is studied. All the samples are prepared in thin film form. That is, powdered form of sample is dispersed in ethanol and it is drop casted to a glass plate. And for water splitting, a mixture of 25% methanol water mixture is used. That is, methanol is used as sacrificial reagent. And all catalysts are studied under direct sunlight. And the results are shown in figure. Here it can be seen that for TiO2, there is comparatively low hydrogen production activity, that is 780. But the activity of TiFe and TiCe samples are much higher, and the highest activity is shown by TiFe, that is 1330. And this value is in micromole per gram in 5 hours. Okay. Then the highest activity of TiFe samples is due to its wide range of absorption and narrowing of band gap, and it can effectively form heterojunction with the TiO2. And so my conclusions are TiO2, Fe doped TiO2 and Ce doped TiO2 nanocomposites were synthesized by salt gel method. Powder XRD patterns indicate anatase phase of TiO2 and highly dispersed nature of cerium and iron. UV visible measurement reveals that iron or cerium doped TiO2 can extend the absorption in the visible region. Photocatalytic activity of the samples in the form of thin film was compared via hydrogen evolution under direct sunlight. The comparatively low rate of hydrogen evolution activity resulted from where TiO2 is due to its large band gap and hence can absorb only mainly UV light. Doping with the Fe or Ce ions can improve the photocatalytic activity of TiO2. The highest rate of solar hydrogen evolution is exhibited by narrow band gap Fe doped sample, which can extend its absorption in the visible region. And my acknowledgements, thanks to Dr. C.S. Gopinath, NCL Pune, and Dr. Thomas Matthews, St. John's College, Anchal, and Mr. Sivaraj S.R., Research Scholar, St. John's College, Anchal. Thank you. Thank you, sir.
Very good presentation, sir. Sir, kindly go to the schematic diagram. I mean, the scheme.
Yes, sir. Yes, sir.
Yes. Scheme.
Scheme, sir.
Yes. Yes. Here in the case of you are preparing Fe or Ce doped TiO2. Where does your in this scheme? Where does your Fe or Ce? There is no. That material is not found during your pathway.
Fe or Ce doped TiO2, sir.
Yeah, you are getting Fe, iron or
Ce doped TiO2 and TiO2.
Now you are not any incorporations of this any iron or cerium material.
Yes, sir. Yes, sir.
You are starting from titanium hydroxide. Titanium hydroxide.
Sir, in the first step, metal ion salts is used. That is for iron nitrate, monohydrate, and for cerium nitrate, hexahydrate are used. Sir.
Oh yes. Thank you. Then how do you say that is your titanium is replaced? I mean, your oxygen is replaced, whether it is replaced or oxygen is present or replaced?
Oxygen is already present, sir. And Fe when doped, it is in the form of Fe3+.
How do you say your cerium or iron is incorporated? Only from XRD?
No, sir. In the UV visible spectra, there is a narrowing of band gap. I only used in the figure. It is shown that for preparing only TaO2,
is colorless.
we avoid this metal ion source. But
Yes,
when I use this metal ion source, that is iron source is used, we get a TaFe sample. That is Fe doped TaO2. There is a narrowing of band gap in the UV visible spectra, sir. Also, when I use cerium nitrate, we get a cerium doped TaO2, and there is a narrowing of band gap, and there is a difference between these two materials in the band gap. That is here, sir.
Yes, cerium is 4+ and iron is 3+, right? How to account for the oxidation states?
My detailed structural characterizations are in progress, sir.
Okay, thank you, sir. Thank you, sir.
Then why you can't?
Hello.
Sir.
Can you go to your XRD?
Sir.
XRD.
Powder XRD.
Super XRD. Sir, Colin.
We are making sound.
Here you have mentioned that there is no appreciable changes in the XRD, but then
Sir, the peak height reduces, but there is no peak corresponding to cerium or iron. That I mentioned, sir.
No. It is not a new peak, but then there is a lot of information available from your XRD. There is a
yes, sir. There is a reduction of that.
What is the unit? Have you tried to calculate the initial parameters? Because have you tried to calculate unit cell parameter?
Unit cell
parameter.
It is obtained from JCPDS, sir. This peak positions, that is 2 theta values.
No, not. I'm asking about ABC value.
ABC, this 101.
No. Is it a Q? What is a titanium? What is a phase? What is a geometry?
TaO2. Sir, anatase phase.
Yeah, anatase phase. What is the geometry? Yeah. So, see, this is you are mentioning 101, 004, and 20. It's corresponding. What is a crystal space? I mean, what is a crystal phase? If you look into the crystal phase corresponding AB value, because you can see that, especially you see that 105 and 211 peak. There is a clear doublet in the TiO2. But then when you look into that titanium, when you dope with the iron and cerium, there is one is overlapping, other one is there is a shift, 2 theta value shift is there, and you have line broadening. These are all like what I am correlating with whatever Dr. Raman sir asked. What is the evidence? So these are all evidence, but you have to show with the help of unit cell parameter. Then only it will be one can. This is a suggestion.
Sir, I just identified the 2 theta values.
No.
And from
Unit cell parameter, you don't need to worry.
Identified that it is anatase phase.
What is the crystal lattice? You find out. Then you can find out. You have 2 theta value, and you know the plane.
Yes,
then you can find out ABC. Okay. Then
no,
the
sir,
ABC.
This value I identified, and this 101,004 all are taken from literature.
Yes, we can take from the literature only. What I'm saying is from there you can. What is the 2 theta value? 2 theta value is this is your own XRD, isn't it?
Yes, sir.
Yeah, from the 2 theta value you can find out the HKL value, ABC value. We can find out. Once you find out, you can tell the answer for whatever Raman sir said, that there is a shift in 2 theta value. Why it is? Because it is a titanium 4+, iron in 3+. And what is the ionic radius? Based on the ionic radius, there will be a shift in the 2 theta value. That can be, you can find out from the ABC value, you can calculate. If you have XRD, you can calculate. This is what my suggestion. Okay.
Oh, okay, sir. Thank you, sir.
Sunesh, I think what I understand is that you have tried to prepare the iron and then cerium doped TiO2 nanoparticles,
Yes, sir.
right? The characterization techniques, I also feel that these are not sufficient to claim that the iron and cerium are basically doped. What you are showing, initially you are answering the UV visible spectroscopy data, and also you are saying XRD. So none of these details actually what you have presented may not be sufficient. So we suggest you to just do little more analysis on the elemental part.
More detailed structural characterizations are in progress, sir.
So what are the details?
This is actually prepared for synthesis is based for aerogel. That is mesoporous aerogel. That is the base for the synthesis.
You mentioned. Please listen.
But not mentioned here because that data are not get it.
Listen. What we are suggesting is that the question when you communicate to the publication also, these are the questions generally they ask us. You are claiming that you have prepared something, but then that something is not supported with the characterization. That is what everybody observed. Okay. So you can go for EDAX analysis and then talk about elemental thing or XPS.
EDAX, photoluminescence, nitrogen adsorption, desorption, XPS analysis are under progress, sir.
Yeah, and also there is some problem in the UV visible absorption also. Can you go? Can you go back there?
Yes, sir.
Can you go back? Yeah.
Yes,
See, you are claiming that there is a broadening after doping, right? And
yes, sir.
That is what you are claiming, that there is that is because of the low band gap, right? After doping,
the low band gap.
Yeah. But then you see that the recording UV visible spectrum of TiFe itself, there is some problem. And why there is it is starting at 800 nanometer, it is starting at very high absorbance, whereas the other two are starting at the zero absorbance. Do you have any explanation for that?
Zero absorbance nodes, sir. By adjusting this to 10 to 0, sir.
You understand what
this TiO2 cannot absorb above 400 nanometer. Its absorption is very poor, sir, because of the large band gap.
Okay.
But in the case of cerium also, there is band gap is 2.88.
That is fine. I am not talking about those numbers. I am not talking about those numbers. You see, both of these TiO2 and TiCe, both of them have started at 800 nanometer, almost at zero.
Oh, sir.
Do you agree?
Sir.
Whereas the green color curve, which is responsible, it is starting at some value. Do you know what is the reason for this?
Sir, iron has basically band gap of 2.2 to 2.4 range, sir. And when this is incorporated in this, the band gap of the resulting composite is 2.51.
Check data.
So it has a wide range of absorption, sir.
Check your data. This is not the right way to represent the absorption spectrum, and we suggest you please correct it. Basically, it should come to zero, and you have to basically this is because of the scattering effect. You have to nullify, and because if you don't nullify and simply take it that as your value and calculate this band gap, that will result some arbitrary values, errors in your calculations. You got it? This has to be corrected. This is because of the scattering. There is the spectrum actually gone up. That has to be brought down first before going further into the calculation of the band gap.
Sir.
Okay, please.
Sir. Sure, sir.
Any other question from the audience?
Sir, have you tried for good afternoon? Have you tried for that material, whatever you synthesized for any organic transformations?
No, sir. It is only used for hydrogen production.
Okay. Perfural, it can reduce, you are saying in the starting side. Did you try for another any organic molecules?
Oh, sir. Yes, sir. Sure, sir.
Okay, okay.
Thank you,
Good,
sir.
your nice presentation.
Yes.
Thank you, sir.
Yeah, nice presentation, Sunesh. Thank you very much. And let us move to next person.
Thank you,
Shashikala.
sir. Thank you very much for valuable information from judges. Thank you very much.
Thank you, sir.
All right, thank you.
Sir, OP 17, Anil is ready.
Okay, fine. Let him present then.
Hello.
Yes, sir.
Sir, can
Yes.
you hear me?
Yes, sir. Yes. Yes. Yes.
Good afternoon, sir. Myself, Anil. I'm carrying out my PhD at Loyola College, Chennai, and carrying out my work at NCCR, IIT Madras, Chennai. I'm going to talk about furfural hydrogenation in aqueous medium over nickel titanium catalyst and the role of titania phase on the activity and selectivity of hydrogenation products. So this is my content, introduction, synthesis, characterization, catalytic activity, and conclusions. As we know, the normal day news nowadays, what we find is farmers are burning their leftover residues. And this may not only lead to the atmospheric pollution, but also to the ground pollution, where you kill the microorganism, soil erosion will take place, soil hardening will take place, and this overall effect will have on the climate change and ecological imbalance. Because even a small insect is important in making the complete cycle of the ecology. So the another possible way is like we can use this leftover residue by catalytic transformation. We can convert it to a chemical and fuels. So we know that the non-edible biomass is lignocellulose, and one of the major part is the hemicellulose, which is consists of C5 polymeric carbohydrates. And from this we can obtain the monomeric feedstock like xylose, furfural, and xylose is obtained by hydrolysis, and further dehydration we get the furfural. This furfural is an initial stage of feedstock chemical which can be hydrogenated to further compounds which have industrial level, like furfural alcohol for resin making, for tetrahydrofurfural alcohol as a green solvent, cyclopentanol, pentanol in perfume and flavor industry they are using. And this biomass feedstock chemical and their products are mostly water soluble, and the water being green solvent and using it for the reaction seems to be better. And most of these hydrogenation reaction are taking place either on the platinum catalyst or on the non-noble metal like nickel, copper, and cobalt catalyst, because they can activate the hydrogen dissociation. Whereas the support among various support, the titania is found to be stable in the hydrothermal condition, and it has the mild acidic strength. So here in my work, I have used titania. So my work is to see what happens when we vary the support from anatase to butyl. And this is the pathway possible. One pathway from furfural alcohol, it goes to the cyclopentanol, another will go to the tetrahydrofurfural alcohol. So the synthesis of the support, the anatase support and the mixed phase support, I have taken commercial one, whereas the butyl support I have synthesized using titanium hydroperoxide, using salt gel and hydrothermal method. In the both the case, the initial preparation is same, but the stirring was kept in salt gel for 7 days, and further drying and calcination have taken that has given a rod shape butyl titania. In hydrothermal method, instead of stirring for 7 days, I have done stirring for 2 hours. Once the solution becomes clear, I have sealed it in autoclave and heated at 180 degrees Celsius for 12 hours. And then further I have washed it, dried, and then calcined. We got again the rod shape butyl titania. So I have taken all these supports and I have done a wetness incipient impregnation method. In this, I have first taken the aqueous nickel acetate tetrahydrate solution. At 60 degree, I have raised the temperature, then I added support, then slowly I have evaporated at 60 degree, at 100 degree, it is overnight dried, then calcine and reduce at 450 degree for 6 hours. So to get 58% nickel titania. And hydrogenation I have carried out in the aqueous phase using 0.1 gram catalyst and 5.2 millimole fullerene. It is about 0.5 gram fullerene. And here I have pressurized with hydrogen gas, and then after heating to desired temperature, we have kept the stirring 500 rpm constant, and then the reaction was carried out for 4 hours, and products were analyzed using GC and GCMS. So the first characterization is the XRD, and here we can see the labeling, the ATA, ATH from the bottom. They are the pure anatase. The ATS, the sigma aldis, ATH is home cat. P25 generally it is a mixture of anatase and rutile. ART is also a mixture of anatase and rutile. Whereas RTH hydrothermal, RTS salt gel are pure rutile. We can see the reflection at 44.5 in figure 1b. For the up to P25, we can see the clear nickel nanoparticle peak is there. But for the rutile, when the rutile phase is higher, we see the 210 peak of the rutile is overlapping with the peak of the nickel. So it shows there is a formation of a nickel nanoparticle. Whereas the other peaks of the nickel, because of the low concentration, we are not able to see due to the XRD limits. The same image clearly shows that the anatase supports are fine particle and they have got agglomerated, whereas from the P25, both the mixed phase titania, whereas the pure rutile, there is no agglomeration and they are the larger particle. So it seems like their morphology is based upon the synthesis method they are adopted. For example, P25, it's a commercial. They have synthesized using titanium chloride hydrolysis in the flame of hydrogen and oxygen. The same way, the other commercial supports would have also been synthesized. So morphology is governed by the synthesis method. And we can see clearly from the nickel mapping that the nickel have dispersed all over the support. And here we have nitrogen adsorption desorption isotherm, which shows type 4 isotherm with hysteresis of type 3. And we can see the bottom two isotherms, which shows the mesoporous character, but the lower, the loop has extended to the lower part, indicating the pores of lower about 10 nanometers are present, and still higher lobes are also present as the P by P naught goes to 1. Whereas on all other like P25 ART, which is another mixed phase, on pure rutile, we will see most of the larger macro pores are present. These pores are nothing but the voids in between the particle. In the case of mixed phase and on the pure rutile, we have the larger particles, so voids are bigger. Whereas in the case of anatase, we have the smaller voids. And the same thing we see reflection in the physiochemical properties, where we have larger pore volume because of smaller voids, whereas BD surface area of also anatase is higher compared to the rutile. We see with the formation of rutile in all the cases, we see always the rutile crystallized size are also found higher. And here I given the anatase rutile ratio A:R. And we see P25 is 82:18, ART, another sigma altitude was 48:52. These are the nickel nanoparticles at TEM images, and we see the particles on anatase are found to be smaller when compared to that on the rutile. Here, the main thing what we are seeing is though the rutile have a smaller surface area, but due to the strong interaction with the support, they have got dispersed, but still because the surface area is lower, they found slightly higher particle size nickel. Whereas the ART shows still higher particle surface are higher, so nickel particle are also found to be higher, about 14 nanometer we can see. So it means the textural property along with the phase properties are important. Here we see the nickel oxide TPR scan from 250 to 650 at 10 degrees Celsius per minute. And what we see is in the pure anatase, the bottom two shows the pure anatase, the reduction of the nickel takes place at the lower temperature, and with the presence of rutile, we see the peak of the nickel reduction, nickel oxide reduction has shifted to the higher temperature. This shows that nickel is interacting strongly with the support. And the inside we will see in the case of pure anatase that we find the peak above 600. This peaks maybe because the anatase is amorphous, and once it try to reach a 600 to 700, there will be a transition possible between from anatase to rutile. Not only that, due to the impregnation method, due to the more amorphous nature of the anatase, there may be a formation of a slightly nickel titanate, which may not be detected in XRD. And this small peak would have appeared because of this. These peaks are not present either in the mixed phase or in the case of rutile. So this shows the rutile phase, even present in a smaller amount, have the impact on the catalyst. When we see their acidic site, here acidic site are divided into weak, medium, and strong. And what we see is in the case of pure anatase, we see the weaker acid site are more compared to the stronger acid site. Whereas in the case of anatase, we see most of the acid sites seems to be having the stronger acid site compared to the weak. We find the medium, we confirm the presence of there is a medium peaks from the RTS sample where it shows the middle one more peak, additional peak. So this and overall, we find the because of the higher surface area, the anatase have higher acidity compared to the rutile or mixed phase. And the same thing I have explained, I have shown here. I was able to do about the 3 of the sample XPS, and I'm showing here when nickel 2p3/2 peaks shows for the pure rutile at 851.4 electron volt, whereas on the P25 it shows sorry, it is not 452.6, it is 851.6 electron volt. This implies that there may be there can be a 2 possibility. One can be the size effect and another can be the reduced support effect. The size effect comes from the stronger binding of the pore hole in the smaller particle. Because of that, what happen is the binding energy will be shifting to the higher value if the anatase is more as in support. Another way we can explain the same thing is, for example, when we consider a metal and nickel atom, we see the ionization energy. Its ionization energy will be about minus 7.6.
Time over, ma'am. Kindly go to the conclusion part.
Yes, sir. So their activities of the rutile phases are also higher compared to the anatase. And we see the role of water compared to isopropanol is also there, because water with higher polarity polarizes the carbonyl group and activate it. We see the rutile and mixed phases have lower leaching and turnover frequency also higher. So the overall conclusion say like the presence of higher like a density of the nickel in the case of the rutile phases, they will be able to transfer charge to the pi star of even the CC and CO bond. So they may lead to the higher deep hydrogenated product. These deep hydrogenated product are absent when we take pure anatase. So this was the main point, and we also found the beneficial role when a proton is available at the bronchial acid site in the presence of water. Then only we get a ring rearrangement product of furfuryl alcohol to cyclopentanone, whereas in the absence of that, only tetrahydrofurfuryl alcohol can form. So this this study can help for a biomass upgradation. So I'd like to thank Professor B. Viswanathan, NCCR, Professor K. R. Krishnamurthy, NCCR, my guide M. Jacob, Loyola College, and for providing facility to Professor P. Selvam, Head NCCR. I also like to thank DST India for funding NCCR IIT Madras, and I'll also pay my gratitude to Department of Chemistry School of Physical Science, Center New Kerala, and Association of Chemistry Teachers. Thank you.
Thank you, madam, for your nice presentation. During the preparation, you have the preparation takes nearly 7 days.
Yes, sir.
Yes. Suppose, have you checked the completion of the reaction? Completion after
Yes, sir.
7 days? Yes. 7
Yes,
days.
sir. Each day I have taken some amount of the sample from the solution.
Yes, yes.
And I have dried it and then calcined it. And then I have checked the XRD. What I found, the NRTS was present, and slowly as the day progressed, we find the NRTS get consumed and convert into rutile phase. On the 7th, yes, sir.
Only you are getting the final product only after 7 days, right? Am I
Yes,
right?
sir. Yes, sir.
Yes. Then you are in the isopropanol
Yes,
and
sir.
water, in which medium that is your efficiency is maximum?
Yes, sir. In the presence of water.
What is the reason for this?
Sir, initially when we considered the furfural to furfuryl alcohol step, what we see is the carbonyl group get interaction with the water molecule, hydrogen bonding. This hydrogen bonding polarizes and initiate the hydrogenation. But when we see from furfuryl alcohol intermediate, either it has to go to cyclopentanone or it has to go to tetrahydrofurfuryl alcohol. If we want to go to cyclopentanone, it needs the acid side of the support where it can undergo ring rearrangement. I will show you the mechanism. 1 minute, sir. Okay, it's not here. Actually, what happens is cyclopentanone will form through pinacatally ring rearrangement. So in that ring rearrangement, we need the protonation of the furfuryl alcohol, that CH2OH, that water will leave and form as an carbocation as an intermediate, and further ring rearrangement take place. In absence of water, these bronchoacicides are not active, and because of that, they are freely available to get absorbed onto the surface of the nickel, and further hydrogenation will take place to tetrahydrofurfuryl alcohol.
Thank you, ma'am.
Thank you,
Yes, sir.
Anil, for your nice presentation and
Yes, sir.
presenting lot of data. And I have only one question because of the paucity of the time.
Yes, sir.
My question is that the same thing related to Raman sir.
Yes, sir.
You have waited for 7 days to get the rutile phase. What
Yes, sir.
happens? Suppose if you increase the temperature, let's say about 500 or 600 degrees centigrade, and then calcinate it for some time and then look at the data. Have you done that kind of analysis?
Yes, sir. Like
It is
what
well established, right, in the literature. Getting
Yes,
the
sir.
rutile phase is generally obtained at high elevated temperature. than
as we
literature.
as we cross 600 degrees Celsius, slowly the rutile phase start appearing. So what was my goal was to get the pure rutile phase. So what I done is I have taken the sample, I have dried it intermediate days, and then I have calcined it to the 450 for 6 hours, and still I see the presence of, because I am not going above 600, so it is only 450. So only calcination is taking place, complete hydrolysis and crystallization is only taking place, rather than the phase transition, which has to take place at 600. And if I take these intermediate days particles, like whatever samples, if I calcine above 600, surely the rutile phase would have increased, but the surface would have gone below 10 nanometer, 10 meter square.
Okay,
per
all
gram.
right. Okay, all right. Thank you very much. And sorry, audience, we don't have time. Already time has up. I think we can move to next person.
Sir, next is Ashwin, OP22.
Yeah.
Hello, sir.
Yeah, Ashwin, please.
Let me share my screen, sir. Can you, the screen is visible, sir?
Yes, sir. Yes, sir.
Yes, sir.
Yes, yes.
Good
Yes, sir.
afternoon. Let me start, sir.
Yes.
Good afternoon, everyone. Myself, Ashwin. I'm from Central University of Kerala, doing PhD under the supervision of Dr. A. Saktivel. Today, I'm going to present on a topic about ruthenium on alpha nickel hydroxide as a potential redox catalyst. The outline of the talk includes the importance of lignocellulose biomass, significance of nickel and ruthenium-based catalyst, objective of the present work, preparation of the catalyst and its systematic characterization, and catalytic application for the oxidation of cinnamyl alcohol and the hydroprocessing of anisole. In the view of glowing depletion of fossil fuels, much attention has been paid recently to the renewable energy sources. Lignocellulosic biomass can be used as an alternative for fossil fuels. It is subjected to pyrolysis for the production of bio-oil. Currently, scientific research is undertaking for the upgradation of pyrolysis oil for the production of transportation fuels through hydrogenation and hydrodeoxygenation. Products such as benzene and toluene from the lignin fractions are renewable energy resources which can replace the fossil fuels. Lignin model compounds such as phenol, eugenol, anisole, and cinnamyl alcohol can be used for the study of upgradation study. Hydrotalcite belongs to an anionic class where the positively charged layers are formed by edge sharing of the magnesium hydroxide and aluminum hydroxide octahedra. The charge balancing anions and water occupy the interlaced spaces. The general formula of the hydrotalcite is given below, where the M2 plus can be replaced by magnesium 2 plus, cobalt 2 plus, nickel 2 plus, and etc. And M3 plus can be replaced by aluminum 3 plus, iron 3 plus, and chromium 3 plus, etc. Anions can be carbonate and nitrate. In this work, we concentrated on ruthenium and nickel-based catalyst, where nickel is a very good hydrogenation catalyst. It is a high catalytic activity at room temperature. It's also a potential catalyst for various organic transformation, and it's abundant in nature. In the case of ruthenium, it is also an excellent hydrogenation catalyst. It's active at low temperature and pressure. And it's also coke resistant. The objective of the work includes the synthesis of ruthenium containing alpha nickel hydroxide and its systematic characterization. Explore the activity of the synthesized materials as a redox catalyst for the transformation of lignin model compounds. For the synthesis of nickel ruthenium hydrotalcate, aqueous solution of nickel nitrate is taken in a beaker to which ammonium carbonate and ammonium hydroxide is dissolved in water, added drop by drop at constant stirring. Then the precipitation takes place and it is kept for aging up to 18 hours and followed by filtration, washing, and dried at 80 degrees Celsius overnight. The alpha nickel hydroxide is obtained. For doping for weight percentage of ruthenium in the catalyst, a wet impregnation method is used. Ruthenium chloride dissolved in methanol added drop by drop into the catalyst. And for the dried and calcined, the calcined catalyst named as for RuNi 200, for RuNi 300, for RuNi 400 according to the calcination temperature. The reduced catalyst using NaBH4 is given as for RuNi 400R. Coming to the characterization, the XRD data of 200 degrees Celsius calcined catalyst shows 2 theta angle at 30 and 35 and 60 corresponding to the 012 plane and 110 plane of nickel hydroxide. And when it is calcined at 400 degrees Celsius, the calcined hydrotalcite materials converted to mixed metal oxides. And when we further reduced, the metallic mixed oxide is converted to metallic from the formation of ruthenium and nickel species. The nitrogen spectrum isotope of the 200 degree calcined catalyst and the reduced catalyst shows exhibit multi-layer adsorption in the range of 0.3 to 0.9, where it is a characteristic of type 4 isotherm. The type 4 isotherm with H4 hysteresis loop indicating the presence of narrow slit-like interparticle mesoporous nature. The surface area of 200 degree calcined catalyst is 86 and reduced catalyst is 13. Coming to that TPR profile of the catalyst, the alpha nickel hydroxide show a reduction peak at 378 degrees Celsius, which shows the reduction of nickel hydroxide into metallic nickel species. The 200 degree calcined catalyst exhibit a broad hydrogen consumption in the range of 200 to 300, The observed shift in the reduction temperature to a lower temperature and the broadness of the peak is due to the presence of ruthenium, which promotes the reducibility of the catalyst via hydrogen spillover mechanism. The reduced catalyst shows asymmetric peak in the range of 250 to 350 degrees Celsius and small peak at 200 to 250 degrees Celsius. The reduction temperature is lower than the alpha nickel hydroxide, indicates some metals in the catalyst is already reduced. Coming to the catalytic activity of cinnamyl alcohol oxidation, the best catalyst is found out at a 200 degree calcined catalyst, and the major product was formed cinnamaldehyde. We have studied that effect of temperature of the reaction, in which when the temperature increases, the conversion also increases, and found out the best conversion selectivity achieved at 90 degrees Celsius with 84% of selectivity. And we have also studied the effect of oxidants, where hydrogen peroxide, TBHP in water, TBHP in decane and cumene hydroperoxide, and atmospheric oxygen we have studied, among which the TBHP in decane shows better conversion. From the recyclability study, it is evident from the result that the catalytic activity increased during each cycle, with 90% of conversion on the fourth cycle. The catalytic activity on hydrotrating of anisole also studied, and the best catalyst was found at reduced catalyst. From here, the effect of temperature study also done, where the conversion increases up to steadily up to 175 degrees Celsius. The best activity is shown as 175 degrees Celsius with 90% of conversion. And the effect of pressure also studied in this reaction, from varying hydrogen pressure 10 bar to 25 bar, with increasing pressure also increase hydrotrating ability of the catalyst. And from the recyclability study, it is found that the gradual decrease in conversion evident after each cycle, and it may be due to the conversion of metallic species into oxide form. Coming to the conclusion, hydrotalcite type alpha nickel hydroxide was prepared using co-precipitation method, and layered structure was evident from powder excited data. The ruthenium was loaded by wet impregnation method, and the development of catalyst shows promising activity for the oxidation of cinnamyl alcohol and hydrotrating of anisole. The catalyst calcined at 200 degrees Celsius showed better activity for the oxidation of cinnamyl alcohol with 84% conversion, and the reduced catalyst shows 90% of conversion for anisole with the formation of toluene, cyclohexane, and benzene at 175 degrees Celsius at 20 bar pressure. Thank you.
Thank you,
Hello?
sir, for your thank you, sir, for your presentation. You have calcined up to 400 degrees centigrade. What will happen if you calcine furthermore? That is after 100 degrees. Have you checked?
No, sir. We calcined up to 400 degrees Celsius. 200, 300, and 4. After that, we didn't check, sir.
What will happen if you calcine after 400? You will start checking, right?
Not checked. We have to check, sir.
Okay. I mean, what are the oxidants? You have used so many oxidants, hydrogen peroxide and oxygen, I think. Huh?
Yes, sir.
What are the? Do you get the same product? Same
No,
product?
sir. It was no, sir. The product was same, sir. But
yes, the
conversion level
previously.
Yes. The conversion
But that-
level and the selectivity was decreased, sir.
What about the yield?
Yield was almost same, sir.
Same. Right. But what about the time duration?
Time duration 6 hours, sir.
6 hours. For all the oxidant.
Yes, sir.
Okay. Okay, sir.
This with respect, can I ask some question?
Yes, yes, with pleasure.
Yeah. You are talking about, I am again asking a similar question what Dr. Raman sir asked. What will happen if you calcine the hydrotalcite above 400 degrees centigrade?
Sir, further calcination, the structure, hydrotalcite structure is collapsed, sir. And
what is the
okay.
What is the expected
Yes, sir.
So what you are expecting after if the structure collapse, then what is going to happen? Hydrotol say structure is going to collapse, then what is the structure you are going to get it?
And it will be a mixed metal oxide, sir.
So
And
what
it
kind of
may
mixed metal
use,
oxide? What kind of mixed metal oxide you will
from
get?
Here we use nickel and ruthenium. So ruthenium oxide and nickel oxide will be mostly formed, sir. And
Is there
may
any characteristic
increase
feature of
the-
any mixed oxide? My question is there any, you said that mixed metal oxides. So what is the characteristic feature of that mixed metal oxide?
It may be in spinal form, sir.
Okay, you read.
Okay. Catalyst. Yes, sir. Sure, I will.
Ashwin,
Yes, sir.
So one question. You mentioned the selectivity.
Yes, sir.
How did you check the selectivity? What do you mean by
Selective.
selectivity?
We used the GC for analyzing the reaction product, sir.
Okay.
From that, we calculate the area under the peak, sir. And we have using the reduction time, we have calculated that.
No,
how
I
the selectivity.
understand. What do you mean by basically the term? What is the meaning of selectivity? Is it the meaning that you have taken different alcohol, varieties of alcohol, and out of which the catalyst, is it the case that it has taken only the cinema, it has converted the cinnamal alcohol to the cinnamaldehyde?
Actually, the selectivity in this reaction, sir, it refers to the product formed from cinnamal alcohol, and number of product, it is number of product formed from the this reaction is used for selectivity. Like from the 100% selectivity.
Okay, you mean to say that, okay, you have a, let's say, so and so quantity of cinnamaldehyde alcohol, it is out of the taken, how much is converted into aldehyde? That is the selectivity in your case?
Yes, sir. Yes, sir.
Okay.
Yes,
Okay.
sir.
And then you're also mentioning two metals you are taking. What is the specific reason for that? Ruthenium and nickel you are taking in your study. What is
Yes,
the
sir.
specific reason for that?
Like for the case of hydrotalcite, sir, it's layered structure, and we can interchange the metal in the hydrotalcite, sir, and like 2+ ions and 3+ ions can be, metal ions can be incorporated in that structure, sir.
So
by
you know
using-
that ruthenium is very costly. Can you name some other metal which can be replaced with instead of ruthenium? With ruthenium.
Yes, sir. Iron can be replaced, sir.
Okay, so what is your specific interest in using ruthenium in that?
Ruthenium, like we have started a reaction using ruthenium, sir. And
Whether it is tried out or iron nickel combination?
iron nickel is in progress, sir. The I am analyzing the reaction, sir. The study is in progress, sir.
Okay, so this is another study that you are studying.
Yes, sir.
Okay, all right. Thank you for nice presentation. So audience, you have any questions? Maybe one question or two questions. Audience? All right, if there are no questions from the audience, let us move to the next person.
Next is last one, OP20, Chaitana.
Okay, right.
Sir, shall I share my slides?
Yes, yes, please.
I think someone else is sharing the slide. I'm not able to share, sir.
Sir, Ashwin didn't stop sharing the screen.
Ashwin. You can try now, Chetana.
Yes, sir. Now it's coming. Can you all see my slides?
Yes, yes.
Okay.
Yes, yes.
Is it fine, sir?
Yes, yes.
Okay. Good afternoon, everyone. I'm Chetana from Purna Prajna Research Institute, Bangalore. My title of my presentation is Efficient Chemiresistive Carbon Monoxide Sensor based on nanostructured tantalum oxide tin oxide composite. Basically, gas sensors are the devices which can detect harmful or toxic gases in any environment as a safety system. So such type of gas sensors we use in our day-to-day life in different areas. For example, for environmental monitoring, home safety, and so on in industries and all. However, we are mainly concerned about the toxicity of the gases. So here I have listed few toxic gases and their TLV limit, meaning they have something called the threshold limiting value. So above this concentration, exposure will lead to harmful effects on our health as well as to the environment. Therefore, the gas sensors are very much required for our day-to-day life. And based on the different working principle, there are different types of gas sensors available. For example, optical sensors, electrochemical, thermometric, and chemiresistive based sensors. We mainly work on chemiresistive based sensors. Now, coming to the drawback of conventional gas sensors, they lack with the long-term stability, selectivity, reaction towards humidity, high operating temperature, and failing to get reproducible results. And therefore, there is still scope for improvement in the field of gas sensing technology. And in this work, we mainly discuss about the carbon monoxide gas sensors. The motivation behind this work is when we look at the literature. So these are the recent reports on carbon monoxide sensors based on semiconducting metal oxides. So if you look at this report, there are different types of metal oxides have been reported. However, if you look at the concentration and the operating temperature, what they have reported is very high. All the reports are with the high operating temperature and high concentration limit, which is above TLV limit. So therefore, there is a strong need of developing a cost-effective carbon monoxide sensors which can operate at low operating temperature as well as which can detect very low concentration of the carbon monoxide gas, because we know carbon monoxide is a very toxic gas. It is also called as silent killer, because since it is a odorless harmful gas, we cannot even make out if there is any leakage. And since it has more affinity towards the heme group in the hemoglobin, so this will result in conversion of oxyhemoglobin into carboxyhemoglobin, which will lead to many fatal accidents. So therefore, it is very important to design sensors which can detect carbon monoxide gas at very low concentration and low operating temperature. So with this aim, in our work, we have synthesized tantalum oxide and tin oxide semiconducting nanocomposite material from hydrothermal method. And initially, we synthesized the individual metal oxides, and the powder XRD analysis confirmed that tin oxide crystallized in the tetragonal crystal system and tantalum crystallized in the orthorhombic crystal system. And further moving on to the powder XRD analysis of nanocomposite, here we have doped different weight percent of tantalum oxide on tin oxide to form the nanocomposite material. And from the XRD analysis, it was confirmed that the composite material had both peaks corresponding to SNO2 as well as Ta2O5, meaning there is a formation of nanocomposite material. And the preliminary gas sensing results showed us that 5-8% tantalum doped composite gave a better results compared to the other compositions as well as the individual metal oxides. So further we moved on with this composition. So here the HRTM, and from the HRTM analysis, we calculated the average particle size, and we confirmed that the particles are in the nanometer range. And also the HRTM images, we have calculated the d-spacing, and the plane d-spacing corresponding to 110 plane corresponds to tin oxide, and 001 plane corresponds to tantalum oxide, hence which confirms the presence of tantalum oxide in the composite. And also this was supported by elemental mapping analysis. And moving on to the XPS analysis, this gave us further proof of presence of tantalum oxide in the composite material because we found that the peaks corresponding to tin and tantalum in the XPS survey spectra. And then from the high resolution XPS spectra, we found that the tin is in +4 oxidation state and tantalum is in +5 oxidation in the composite material. And importantly, the oxygen vacancies are very important in gas sensing mechanism. They play a very important role. So we analyze the oxygen 1s spectra of the composite material as well as the individual tin oxide material. So as you can see here in the first image, the peak at 530.6 electron volt corresponding to the oxygen at the lattice and 531.5 electron volts corresponding to the oxygen vacancies. However, if you look at in the composite nano composite material, which has a broad and high intense peak corresponding to oxygen vacancies, as well as in addition to that, there is a peak at 533.3 electron volts, which is ascribed to oxygen chemisorped oxygen molecules on the material. So this says that the composite material has high ability to chemisorb oxygen molecules, and also they have high oxygen vacancies, which can be helpful in improving the gas sensing activity. And coming to the main part, we studied the gas sensing properties of this 5-8% doped tantalum oxide of tin oxide to detect the carbon monoxide gas. Here initially we tested for 10 ppm carbon monoxide gas and we using synthetic air as a carrier gas. And then interestingly, we have obtained good response to low ppm carbon monoxide at low operating temperature of 50 degrees Celsius. Also, this experiment was done at very low operating voltage of 1 volts. And we have obtained a very good reproducible results with the low response time and recovery time. And to compare with the other compositions, we have carried out experiments with other compositions as well as with the individual metal oxides. And we have found that the 5-8% tantalum oxide doped tin oxide was giving best results compared to the other composition and even the individual metal oxides. So this shows that the combination of two metal oxides or formation of two nanocomposites will thus help in improving the gas sensing properties of the materials. And then we wanted to study the minimum detectable limit of this material, and hence we carried out the measurements at different concentrations of carbon monoxide, and we have found that up to 5 ppm carbon monoxide could be detected using this material. And we have designed proposed a plausible gas sensing mechanism. So why the composite has given better results compared to the other individual oxide material. So we have found from the UV-DRS analysis, we have obtained the band gap of tin oxide and tantalum oxide, and based on which we have designed a band structure of this nanocomposite material. And as a typical gas sensing mechanism of semiconducting based materials, usually the oxygen molecules will be adsorbed on the sensor materials, and when a target gas exposed to this sensor material, that is in this case it is carbon monoxide, so it will capture oxygen anion molecules in the surface, and then the electrons are given back to the materials. So there will be increase in the conductivity of the material whenever there is a target gas is exposed to sensor material. And why this improvement is because of the presence of, there could be, when there is two metal oxides, there will be formation of NN homo junction in this case. So because of the presence of this junction, the electrons and holes will move each other so that to attain equilibrium, and there will be formation of donor-like surface state, and which induces more, it facilitates the charge transfer, meaning there will be more number of movement of charge carriers, and it will also reduce the charge recombination rate. So all these reasons, along with this, the improved oxygen vacancies will help in enhancing the gas sensing performance of this composite material compared to the individual metal oxides. So coming to the summary of my work, so we have synthesized the nanocomposite of tantalum oxide, tin oxide by hydrothermal method, and various characterizations were performed. And from the gas sensing study, we have found that 5-8% tantalum oxide doped with tin oxide has given a best results to sense low ppm of carbon monoxide gas at very low operating temperature of 50 degrees Celsius. And the improved oxygen vacancies as well as the improved charge transfer could be responsible for the improved enhanced performance of this material. Thank you.
Thank you, madam, for your nice presentation.
Thank you.
You are saying that your sensor is selective, whether it is selective only for carbon monoxide. How do you confirm this? It is a mixer.
Yes, sir. We have tried the measurements with the other gases also. For example, the methane, carbon dioxide, and hydrogen also. So this material did not respond to any other gases. So from that reason, we say that this material is selective to carbon monoxide gas.
So carbon monoxide, there is a tendency to form carbon dioxide. Whether there is any, so how do you say it is only carbon monoxide from the analysis or?
Yes, sir. So the moment the material is exposed to carbon monoxide, there will be change in the resistance of this material. So here in this slide I have given, so carbon monoxide will convert into carbon dioxide. So because of this reason itself, we get this curves here. So the moment I pass carbon monoxide, there will be decrease in the resistance.
Okay. Is there any purpose of using tantalum oxide for why do you choose the tantalum oxide for this purpose?
Initially the tin oxide is very well known for carbon monoxide sensing, and then from the literature reports we have found that the doping of tantalum, niobium, and vanadium, such elements will enhance the electronic properties of this material, and they'll induce special features with respect to the composite material.
Very nice.
And this material has been tried for photocatalytic applications. So there also they have explained based on the electronic properties. So that using that reason, we use this material for gas sensing studies also.
Sir, Ravi sir. Kumar sir.
Sir, any other questions?
Sir, can I ask a question? Maybe quick, one or two. Okay, Chetna, a quick question. You said that your system works better at 50 degrees Celsius. So what happens if you go down room temperature?
Room temperature, it did not work, sir. It did not give any change in the resistance.
You know what is the reason? Did you try to analyze that?
Yeah, actually, these oxygen anion species, so only at certain temperature it will form the oxygen. Usually, the oxygen molecules as such will adsorb on the sensor material. So only at certain temperature, they'll convert into oxygen anion species. And those anion species, it will react with the carbon monoxide molecules. So it needs some temperature, and also the adsorption energy also matters here. So there are certain conditions at which these gas molecules will adsorb on the surface of the material. So those could be the reasons.
Is there any way you can kind of push it and then make it work even at the room temperature? Is there anything you can think of?
Yeah, if we can do any modifications with respect to the materials, either like surface modification or any other modification, or by combining with any other materials like high conducting materials like with the polymer or something, so that may work at lower temperature than this probably.
Thank you. And one more question. So do you do this sensing in the presence of moisture, or it should be a dry condition?
This is in the presence of air, sir, like just like the ambient air. So under
So
air
you have water also. So there is no issue with the having water around. Okay.
Yes,
okay. Thank you, Jim. I'm done.
Thank you, sir.
Thank you. Thank you.
Thank you, sir.
now.
Hi. Can your material sense CO2? Are you able to hear me?
Yes, ma'am.
Hello. Can you able to sense CO2 with your material?
No, ma'am. It did not give any response to CO2.
Why? What could be the reason?
Yeah, as I said, maybe the adsorption energy, the affinity of the gas molecules towards the surface active sites, that may differ. Maybe because of that, only some gas molecules are it has more affinity, or the adsorption energies matches. So because of that reason, maybe only certain molecules adsorb on the sensor material.
But if you can see that tin oxide is a very good catalyst for reduction of CO2 electrically. Okay,
Yes,
it can produce a very good methanol, a very good material. Okay, only lead and tin can produce. So in that way, tin oxide has affinity. But why affinity towards CO2?
Yeah, tin oxide has, but when there is a formation of nanocomposite, there will be change in the properties. The entire there will be some special properties which is restricted to the composite material, other than the individual metal oxide. So, due to the changes in the properties induced in the composite material, I think that there are some changes in the activity also.
Yeah. Okay. Yeah, it's a good presentation.
Thank you, ma'am.
Good. Here some internet issue is there. So thank you very much. I think any other presentation is there, Dana? Is it the last one?
No, ma'am. No, ma'am. This is the last.
Okay. So I congratulate all the oral presenters. Today it was a very interesting oral presentation session. Really, we admired all the contributions from the researchers. So it was a very good presentation by all the presenters. Anyway, there is a committee that we are scrutinizing for a good oral presentation also, I hope. Maybe we will let you know all those things in the validative function. Now I think we have to move on to the next technical session. I think we are waiting for our next speaker, Dr. Vijay Shankar from Reliance Industries. Okay, so he will be joining. Please wait or stay on the line. Other people, let us wait some time so that he can join and we can start the next technical session. So you be online, okay?
So good afternoon, everybody. So stay another 10 minutes. We will start the next invited talk. Dr. Vijay Shankar is there. Raman sir. Raman sir, is correct? Sir. Raman sir. We thank Dr. Raman and Dr. Ravi for their valuable.
And we have discussed, sir. Okay.
Raman sir.
Yes, sir. Thank you, sir. We have discussed with the Professor Ravi Kumar sir, and I thank the organizers for having given me this golden opportunity to acting as a judge in this reputed webinar. So I once again I thank the organizer and the co-judge, Dr. Ravi Kumar sir. For his and also the audience, they are asked so many questions. So we are very much thankful to the audience also. They are very alert, and we find some difficulty in which in the conclusions because all the presenters they have nicely presented and answered. The interaction is also very good. I am getting because they can suppose whatever be the questions from different side, they were able to answer all the questions to the satisfactions of the the judges. So I thank the presenters also. Okay, thank you very much, sir. Thank you, sir.
Yeah.
Secure, sir, thank you very much.
Thank you, sir. We will have a next invited talk soon.
Okay.
Yes, sir.
Before that,
thank you, sir, for your valuable. Yes, sir. Yes, sir. Please, sir.
So before that, I'll send the
evaluation
report
actually, Dr.
to
Ravikumar will call you.
Yes, sir. Yes, sir. Yes, already
both of
called
you
me.
can decide.
Okay.
Yes, sir. Okay.
Thank you, sir.
Okay, sir. Okay.
Within a short, within a short period, we'll give within a short period, within short time, we will give the report to you. Okay, sir. Thank you.
Yeah. The next invited talk will be by Vijay Shankar. So we will start Zoom in maybe another 10 minutes. We'll start. All the participants be here. Dr. Vijay, how are you? Hello, Dr. Vijay. Okay,
Yeah,
I think.
hi, Shakti. Yeah, are you able to hear me? Yes, I'm fine. So I think you guys can have a bio break or tea break or something so that we can start the session as per your schedule. So it's good to see that we are all on schedule.
Yeah. 10 minutes we'll start. We also some network issue. We will be starting out within 10 minutes. Yeah.
Okay, sure. Take your time.
Sunny sir, please give co-host to chemistry and Vijay Balachandran. Sir, can you hear me?
Yes, ma'am, you are audible.
Yeah, please.
Co-host, chemistry and
Vijay Balachandran.
okay, ma'am, I'm doing that.
Yes.
Skip one.
You can talk. Okay. So, welcome, sir, Vijay Shankar.
Good evening. Are you able to hear me?
Yes, perfect. Actually, we lost connection in this building now. So we are connecting through Geo, all those things we are managing. Just check.
Okay.
So more, yeah.
So just prompt me when you are ready so that I can start sharing the screen.
Yeah. Just we'll start exactly by 4 p.m.
Okay, that sounds good.
3 minutes more. 3 or no, I think 55. Sorry, 3 minutes after 3:55. 5 minutes you will give so that Saktivel sir and Dean, everybody will join. Many people are joining.
So just help me out. I'm just sharing my screen. Let me know you guys can see. Okay.
Yeah, please. Good evening, Dr. Reddy. I'm Bhagyalakshmi here, co-convener.
Hope you are able to see my screen, right?
Yeah, it's perfect.
Okay.
Can you hear?
Yes, sir. We can hear you.
Okay, there is some connection in my office, so I have to come to my lab.
Sir, shall we start another 1 minute?
I think we can start. Nimisha? Who is Nimisha? Dana? Who is?
Sir.
Yeah.
Okay.
Proceed, because by the Dr. Vijay, are you fine? Vijay Shankar?
Yes,
Shall we
yes,
start?
I'm ready. Yeah.
What about Dr. Anyway, I welcome Dr. Reddy. Dr. Reddy, are you there?
Yeah, he joined, sir.
Yes, sir. Vanakkam, sir. Good morning to sir. Good afternoon for you. Okay, thank you.
Yeah, happy to see that. It is morning 6:30. Am I correct?
Yeah. Exactly. So it is good time.
Very good morning.
For us.
Very good
Thank
morning.
you.
Very happy to see you.
Okay, sir. Thank you, sir. Thank you, sir.
Yeah.
Thank you.
So we will be moving to the last technical session. So in this session, we have two. And Dr. Reddy from Canada, you see that how dedicated he is just got up maybe 1 hour before our time and he's getting ready. Thank you, Dr. Reddy, for joining the webinar. So let's move on to the technical session. Dana?
Yes, sir. Okay. Good evening, all. This session will be shared by Dr. A. Shaktivel, Head of the Department Chemistry, Central University of Kerala, and the convener of this webinar. Sir, please.
Thank you. And it is my great
Shakti, I think we lost you in the core connection.
Yeah. Maybe I will take my system there so that.
Yeah, maybe you can switch off your video to save your bandwidth.
Sorry, IIT Madras. And then he was spent 3 years in US in the City College of City University, New York. Then he is expertise in microstructural and soft nanomaterials, as well as bioassembly, organic and hydraulic cells. And he has a quite good R&D experience. He was before his PhD also, he was in R&D, Tide Water Oil Company. And for his credit, he has a 4 patent and a lot of corporate publications also. He has more than 20 corporate publications and book chapters. And he is expertise on electron microscopy. And we are very glad to have you, Dr. Vijay Shankar. Over to you, Dr. Vijay Shankar. With this introduction, brief introduction, I request Dr. Vijay Shankar to share your valuable scientific information to the audience.
Thank you, Dr. Shakti, and thank you all the people at peers in UK. And I feel it's my pleasure to interact with you all today in this wonderful session. And I wish you all a very safe stay and keep always your safe distancing and other sanitizing protocols. Okay, so I wish you all a very good health. So what I'm doing is like I've already shared the presentation on the screen. Just ping me if you are able to see my screen so that I can start my lecture.
Yeah, we are able to see. Can you go to the slideshow?
Thank you. Why? Because I know now data is the new life for us, but equally we need to save data because we are not that much fast. So I'll just open my video so that you can all see me. Hi everybody, and I'll just briefly show my face to you, and I will switch off the video to save the bandwidth so that you can focus on the content. So it's very good to see you all, and thanks once again for giving me this opportunity to interact with you. And especially like I'm very feeling very energized after hearing from a lot of young researchers as well as many students have given a very beautiful presentation. So it's wonderful to hear that. Okay, so maybe like I'll just close my video as of now, and then I'll join you back face to face once the talk is over, so that we can interact for any question session, right? And please feel free to interrupt me so that if I don't feel too much of electron optics and boring stuff to you. Okay, so please feel free to stop me at any point. So is it in a full screen for you?
Yes.
Okay. Yes. Okay, so I may sound a little odd man out for this session because everything the lectures I heard was very tight in scientific content and very hardcore. But since I moved away from this hardcore research, now I'm kind of doing applied research in a company corporate environment. So I may be sounding little on the tip of grass, but nevertheless I would try to satisfy your analytical like a craze on how to use electron microscopy for your research especially, because this at the end of the talk you will agree with me that electron microscopy is going to be one of a mandatory tool for you, because most of you are working in solid state chemistry, dealing with a lot of nanoparticles and nanochemistry, right? So I'm just going to give you a bird's eye view of what are the advances that has happened in using electron microscopes for materials characterization per se. I'm just giving you what are the developments that has happened ever since Ruska developed this beautiful technique in 1930s. Okay, and so this is how I have categorized my presentation. Just give me a minute. I'll just move this. Okay. So I'm just giving a very brief introduction to electron microscopy, since there are so many students, just for the educative purpose. I'm just going to show some basic things about electron microscopy. Especially I'm restricting my talk to transmission electron microscopy, because electron microscopy, you may definitely have the question of it deals with so many hyphenated techniques as well as scanning electron microscopy. But each and every one is a subject of its own, and it can be discussed in length, right? So I'm just restricting myself to the transmission electron microscopy, aka the TEM. Okay, I'm just then will briefly explain you about how far we have pushed the resolution. So then I'll summarize how best we can use this technique. So the basic question comes to why do I read really an electron microscope? So if you understand what is the various magnification techniques we use, of course, we all see with the human see with their own eyes, whose resolution cannot go beyond 100 microns or something. So anything beyond which, if you want to magnify, obviously we use the glass lenses to magnify things. So that's how the optical microscopes come. Then anything below 1 micron, if you want to see in a better detail, so we go for the scanning electron microscope, SEM. And there is a small overlap between the depth to which a scanning electron microscope can go of few hundreds of nanometers, but beyond which, if you want to look at the columnar atomic arrangement, then you need to obviously switch to TEM, which is transmission electron microscopy. So the basic name itself tells that one electron microscopy scans the sample, the another the electron beam travels through the sample. So that's why it's transmission EM. And any improvement in the resolution higher and higher, down 10 nanometer, you always say high resolution. Then some people say ultra high resolution. Then people say it's a nano TEM. Then people say it's a nanoscope. So it's all kind of jargons people put, anything down 10 nanometers. But nevertheless, the tool is the same, which is the TEM. So if we come through through the ages, at least from 1800s, ever since the magnification started with Abbe's refractive fundamentals, then Ernst Ruska then started around in 1950s about a 75 keV electron TEM, for which he was awarded the Nobel Prize that time. Then there was an exponential boom in that, and now around 2000, the most important milestone was achieved in TEM, which is called as the aberration correction. That I'll be explaining in a brief in coming slides. Now we have gone up to 4-dimensional STEM, 4D STEM. Then we have moved up to tychography. Right? There are so many things we have come across through the ages, and as of now, not only the electron optics improved, equally the technology in doing this and simplifying this, automating this, has equally grown, so that TEM is no more a kind of a fascinating tool for the rich institutes, but nevertheless it has become very affordable to even universities also to do a very quality research. So I think you will all agree with me in this point. Now TEM is even kind of a basic tool, like how we used to have the once in a while the UV spectrometer and the IR spectrometer, which is a basic tool. Now the electron microscope is also in that line. Okay. So to briefly tell what is the difference between peers, please excuse me, this is only for the purpose of the students who are the users or who want to get into using these tools. I'm just spending a couple of slides from here as an indicative purpose, right? So there are two techniques I told. One is the scanning electron microscopy and another one is the transmission electron microscopy. So above the specimen is mostly where the scanning electron microscopy is used, and below the specimen, if you have various detection systems, obviously you use the transmission electron microscopy. And there is one kind of overlapping or a kind of hybrid technique that is called as STEM, which is called as scanning TEM, right? So you do still in the transmission mode. That means you detect the signals in the transmission mode, well below the sample plane, but you do a raster scanning on your sample. Okay. Basically, most of the TEMs now, HRTMs, come with the STEM also in that, which is very, very useful. That I will be explaining you what is its application. So obviously, when high energy incident electrons interact with your sample, so many like interactions do happen. You get visible photons, you get backscatter electrons, you get OJ, you get secondary electrons, and so on and so forth. Whereas there are some electrons, when the sample is thin enough, it passes through the sample, it's diffracted, it is scattered, it is just passing through without anything, with zero loss, and you all have this kind of phenomenon. Other than this, there is one unique and very valuable signal you get is like high energy electrons when interacting with the sample creates X-rays for you, which tells what your material is made of, right? So normally microscopy tells how is your sample and what is present in your sample, and X-ray tells like what elements they are made of. Okay. So this is called as this technique of analyzing X-rays for knowing the chemical nature of your makeup of your sample is called as EDX. Okay, energy dispersive X-ray spectroscopy. Basically, it's a spectroscopy we do, and EDAX is a company who makes it. Okay, so don't mix up EDAX with EDX. Okay, either you say EDX or EDS. Okay, that's the technique, and EDAX is the company who makes the EDS, right? So I always used to say to kids here sometimes, like it's like the Vanaspati is the real name, but Dalda is the trade name. So, but many people go and ask in the shop, like, give me Dalda, right? So Dalda is a trade name. So like that, EDAX is a trade name, EDX is the technique. So how does the microscope looks inside? This is an explosion view. In SEM and TEM, you have the electron gun. The difference between TEM and SEM is TEM can go as high as 300 kilovolt, which can generate 300 kilo electron volt. Same way in case of SEM, it is restricted to maximum to 30 kilo electron volts, which is 10 orders down. Okay, but nevertheless, both are used side by side. That gives complementary information to you. So these electrons are pulled by an anode, and then various condensing electron optics focuses your sample, and there is a raster scan which scans your sample, right? That is what is in SEM. Then you get various signals, X-ray detectors, secondary detectors, backscatter detectors. So different detectors give you different signals. Whereas in case of TEM, which is on the right, you can see the sample is thin enough so that the beam passes through the sample, and you get various signals like I explained in the previous slide. So you have various detection system, and below you can still have a spectrometer where it can analyze various electrons based on their EVs. So that is called as electron energy loss spectroscopy, which is in short called as EVs. Okay. So this is how a basic construction of TEM and SEM, and this is the principle on which it works. So I told you a beautiful technique that is called as a STEM. Okay, so STEM is nothing but in case of TEM on the left, you see the small gray bar is nothing but your sample. So you always use a parallel. So whatsoever you do, change the focus and anything, your sample is still lit parallel. Whereas in the case of STEM, you always focus your beam on the sample here, and if I have a raster scanning here, you can have a XY scan on your sample. Okay, so this is the basic difference. So then I told in the in the beginning of 2000, there was the technique called as aberration correction that was involved. Now you can hear in India, many places, you can hear two types of microscopes, especially TEM. One is the corrected microscope, another one is the non-corrected microscope. Non-corrected microscopes are normally called as HRTEM, whereas corrected microscopes are specifically mentioned as CS-TEM. CS refers to spherical aberration correction. So that's how. To simply say what an aberration correction is, like this is a normal case. Whenever an electron is focused by various electromagnetic coils, not all the electrons can be focused in the same point. That means you still have at the nanometer angstrom level, a disk of confusion is there. So if you have some mechanism to focus this dispersed electron back again to the same point, so that you make as much as the 1:1 replica of the point specimen P on the screen D, then it becomes the aberration correction. So take it from me that to do this extra business, you have to shell out close to 3 to 4 crores. Okay, so that's the cost. So what is the advantage I do by shelling out this much money is like it gives a lot of information, especially people who are very much focused on to very ultra structures. Like for example, if you see on the right, there is one uncorrected HRTEM, and this is a corrected T. So this is aberration corrected. See how beautiful you can see the edge atoms very clearly here, right? So for this purpose, this is very, very useful for people who work at the very nanoscale, especially at the interfaces. So this is the advantage. So there is one more technique that is booming up now, which is somewhere in the close 2010, I think, if I'm right, which is a 4D STEM, or some people call it by tychography, or some people call it nano beam electron diffraction. There are so many names to it, but nevertheless, 4D STEM is very popular name that has been used widely. So it's nothing but doing electron diffraction in a scanning TEM, right? So 2x2 is 4D. That's what is 4D here. So it's what can we do with this? It's like it can give, by using 4D STEM, you can do virtual imaging, you can do orientational mapping, you can do strain mapping, and also you can do phase contrast imaging using the differential in the scattering. So to tell you briefly, like what exactly is the orientation or what exactly it can do, consider you are having a graphene sample. Okay, how many layers are there? Whether it is a normal graphene or it's a turbostatic graphene. So all this information you can get by doing electron diffraction, very similar to what you see in the XRD, right? XRD deals with the bulk sample, whereas electron diffraction, you can focus the spot in a particular pixel and get an electron diffraction. So you do a 2x2 raster scanning, and at each pixel you get an electron diffraction. Then computers build this, all the electron diffraction pattern, and then you can analyze. There are so many complex algorithms behind it, but nevertheless, it's a beautiful tool. So coming back to aberration correction, this is one more example for you. Normally when people do gold nanoparticles, platinum, palladium, all these metal nanoparticles, they always go for the TEM to see what is the plane, what is the orientation, shape, and size, and other things. But I really do not know what is the arrangement of atoms at the edges. So why should one worry about the edge atoms? Because it is the phases on these edges most of the catalytic reactions do occur. If the plane changes, the activity changes. The arrangement of the atomic column changes, then the mechanism changes, right? So to do this kind of intricate analysis, you always need to go to the finest resolution possible. So an uncorrected image and a corrected image, you can see by yourself what is the difference. And another STEM based application I would say is like, this is a particular sample where rhodium and iridium is supported on magnesium oxide, and STEM is such a beautiful technique where, based on the contrast between the two heavier elements, rhodium and iridium, you can find where exactly it is positioned. Okay, so I mean, this tells you like you can literally see a single atom. So it's a thrilling feeling if you see a single atom by your own eye. So this is a beautiful application of aberration correction to carbon. People who work in a lot of carbon, now it's an era of new energy materials. People invest a lot of time and energy, money in batteries and graphenes and graphite systems. So you can study all kind of what is the defects in your graphene structure, or what is the 7-5 fusion or the 6-6 fusion or something, this kind of stuff. Definitely you can study using this aberration correction technique. So the TEM, I think, has grown tremendously in the recent 10 years, I would say. After the invention of this single particle analysis, especially the cryo-EM, for which I think you might be remembering the Nobel Prize in 2017 was given for the cryo scientists. I think biologists stopped using XRD, I would say. I mean, I won't say it's an exaggeration, but nevertheless, now most of the protein crystal structures, and even including the so many mutations of the COVID virus you have seen up to the Delta and Delta plus, all these crystal structures down to 1.2 angstrom resolution is possible only through TEM, because not all these proteins can be crystallized so that it's suitable for XRD. So if you look back, then like, since the invention of aberration correction technique in 2000, people were happy to see somewhere below angstrom. So they call it a sub-angstrom resolution. And then in 2010, the direct electron detection systems came. Now almost all the electron detection systems are basically either uses a CCD or a CMOS camera, which is having a lot of decrease in the efficiency of detection because it requires a lot of electrons. Whereas the direct electron detectors, it can work in a very low dose, like even it can capture 1 or 2 electrons per pixel also. So that has been a boon to people who work in beam sensitive materials, especially people who are here who has handled zeolites and metal organic frameworks, which is a very challenging task for you to get the image in TEM. So for that, direct electron detection system was a boon for them. And then later in 2018, David Muller from the Cornell University at Ithaca, so he developed the electron microscope pixel array detector, which is what I was explaining as a 4D STEM, right? So that's how like we have moved. I don't say it's a move, it's a giant leap, I would say. So these are some specific examples that I have been using in a refinery environment here, which is a very very important catalyst, which is a hydrotreating catalyst, because whatever the gasoline and the diesel, whatever you get is full of sulfur, nitrogen. So to remove all these things, you need to do hydro denitrogenation, hydro desulfurization, and demetallization, everything. So for that, the catalyst is mainly the molybdenum sulfide nanoslabs supported on gamma aluminum. Okay, so this is how a typical TEM aberration corrected TEM image looks, and the number of slabs and the length of slabs define its catalytic activity, how efficiently it can do the desulfurization or denitrogenation. So the MPAD detector I was telling was applied to look at the local structure of molybdenum sulfide two-dimensional sheets. So on the left, you see there are 2 pictures, which is just a HRTM image of a molybdenum sulfide. Nothing is clear. Whereas if you use MPAD, which is a pixel array detector, you can even see the arrow here, white arrow points that one sulfur is missing actually. So this is a resolution up to which you can go by atom actually. And the beauty of this, it equally gives what is the crystalline orientation of the 2D materials too. So this is a very typical like a catalyst. We use the STEM technique, and especially this is called as the image. What you get looks like a negative of what you get in a TEM, right? So because this is done using a annular dark field detector. That means what you do is when you scan a small fine probe of electrons on your sample, it passes through your sample, and you have a ring-like detector that captures the highly deviated electrons only, leaving behind the bright central beam. So this gives a lot of information, very similar to the backscattered electrons. And this is one typical catalyst system where platinum and tin is supported on alumina, which is a very valuable dehydrogenation catalyst, especially if you want to make an alkane to terminal 1 alkene, which is used to make typical detergents, right, by Friedel-Crafts alkylation. So the size of the platinum and tin determines whether it should do dehydrogenation or it should go for CC bond cutting. So anything less than 2 nanometer is going to do the dehydrogenation, whereas anything beyond 5 nanometer is going to be like cutting the chains. So for example, if I'm putting a C10, then I'll maybe getting 2 C5s or C6 and C4. So the reaction is completely different. So the STEM is very, very useful for industrial applications like this. And coming to very famous samples like zeolites and MOF, it's beam sensitive in the thing like the high energy electron beams can do damage to your sample, like either by ionizing your sample so that the structure collapses, or it can do radiolytic damage so that it can break the bond. Ultimately, your structure collapses, and within a few milliseconds of exposure to the electron beam, it immediately becomes amorphous. So then how we should do this kind of samples? People so far have been working with a very low beam of electrons with a very shortest possible exposure time and with a very high speed camera, with a CMOS camera and better resolution. But nevertheless, the people were able to manage for zeolites, but definitely did not work for metal organic polymers, which is much more labile in this case. So at this juncture, then the direct electron detection system, which can work with a very low electron dose, came, and of course, like you have to shell out a few crores for it, but nevertheless, it gives you the value for which the sample is being investigated. So this is a typical structure of kind of UI 066 MOF. So just to expose it, it becomes amorphous. So I may be making a beautiful catalyst, but I'm not able to see it, right? So this gives a lot of kind of trauma inside the scientists, like why I'm not able to see this structure. So later, so many improvements came. This is one very beautiful example of how to visualize a MOF through the years. So if you see in 2005, this was the image of a MOF. But over the period in 2018, you see how beautiful the structure is. This is done through low dose direct electron detectors. And the same thing has been done in a STEM mode. You can see beautifully the arrangement of atoms. So the advantage of going to STEM-based 4D STEM or direct electron detection system is like if you want to see what exactly the local structure in your material, then XRD has a limitation because XRD always looks at a bulk, right? It can give you what crystal structure it is, what is the, I mean, to an extent, like it's a polymorph or something or other thing. But nevertheless, if you want to see the grain boundaries and other thing, you need to definitely go to TEM. This is one specific example where you can see that MIL 100 with iron doped on it. So here you can see beautifully the dislocations with a twin plane. And this is another system in which ZIF-8, where you can see how the crystal, the interconnected zone axes are flipped here, right? So this is the typical interface. So here you can see this. So to do all this intricate work, your detection system should be good, as well as your sample should be stable in the electron beam. Now it's a battery age, I told. So there are so much of like work being carried out. This is one typical example where you can literally create a nano battery inside a TEM, and you can study what happens when there is a charging and discharging happening. So this is the scale of 800 nanometers, you can see. So therefore, you can literally see how the lithium dendrite grows. This is a very dangerous thing. You might have heard that so many explosions do happen in the lithium batteries in your laptops and mobiles. So to address this kind of issues, you can even see in a live condition, and there are liquid cells available. You can literally like take a drop of your nano particle solution, put it in a specialized cell, just load it in a TM, and you can see how the particles grow, how the particles sinter, how the particle fuses together, what is the phase transformations, everything you can see in live condition using TEM. So to summarize, there have been a lot of technological advances, and especially with respect to the detection systems, it has created a revolution, I would say. And we just don't see a single atom, we are seeing beyond that right now. And materials characterization mandatorily requires this technique, and TEM is no more a kind of fancy equipment. Once again, I reiterate, it's a mandatory tool for us. And equally, by looking at all these beautiful images, beautiful publications, beautiful data coming out, equally we need to be keeping one thing in mind, that is my sample, is my material suited for this kind of imaging? That's up to us actually, because not all materials behave same in the electron microscope. But looking at only one data is not going to help equally. So we need to have parallel techniques like XRD, elemental analysis, bulk elemental analysis, which is always the fundamental. So putting together everything, it gives you the complete picture. And this has to be borne in mind when somebody goes for a lab to a commercialization scale. Okay. So this is like with a given time, I just told you like how valuable, how beautiful the tool is, and it's up to us how better we use the tool, and what is the length or what is the depth to which we get the information from the sample. And thank you all for your attention. Hope you got a feel of this technique, and any questions if you have specifically, feel free to ask. And thank you, Shakti, and thank you, CETA, PS organizers, once again.
Thank you, Dr. Vijay Shankar. A wonderful lecture by the introduction from the electron microscopic to and its applications. It is very crispy way and very elegantly presented. Thank you. Audience, now it's open for the questions. We can have a couple of questions, because audience are asking very less number of questions. So students participant also. Yes, anybody? Anybody? Vijay Shankar, I have a couple of questions.
Yes, please.
When you look at the TM, how to assign the plane? Like we will normally, for example, we like zeolite or anything, we will get a ED pattern. When you take the ED pattern, we always assign the plane in the ED pattern of the based on the TM image and XRD. How to is it the from the ED pattern, from the center, the first plane is, can we say that is a reflection of the first XRD reflection? Can we say, or how we have to assign?
Yes, you can in principle find it, but there is one thing we need to keep always in mind, that the forbidden transition in XRD are allowed in electron diffraction. So that's in a way kind of, I would say, it's an advantage for you. Whatever you miss out in XRD, you can see in ED basically.
Yeah.
Okay, so the easiest thing I would say is, like, you always go for an FFT pattern or an SAED pattern, get the image. Okay, almost all research institutes should have the ICTD databases with you, right? You should be dealing with PDF4.
Okay.
So just upload it. So PDF4 is able to recognize the spots, and it can identify the planes and reflections. And from that, we can definitely match with the ICTD.
Okay. So it is a PDF4 is a software kind of, is a.
Yes, of course. If you are having an XRD, powder XRD with you, you need to have PDF4 ICTD database. Otherwise, like, we don't have any repository to compare the diffraction powder files.
Okay. Fine. Any other question from the audience? And
one more question, sir. What is the minimum size by which we can use our electron microscope? Is there any limit?
Size means you want to see the size of information or the size of sample.
Nanometer size. I mean, nanometer size.
See, like I said, like any HLTM can go up to few nanometers for sure, very easily. But if you want to go to angstrom level, like
angstrom level,
then you need to obviously go for either a probe corrected TEM or an image corrected TEM. So basically, you need a corrected TEM for it.
Thank you, sir.
Sir, in case of alumina, you mixed with some metal. Hello. Good afternoon, sir. Yes.
Yeah.
Alumina, we mixed with some metal characterized. So
can you be a little louder? Can you be a little louder?
Yes, sir. Yes, sir. Alumina you used for metal doping. So in nano composites, if I kept molybdenum with alumina, can I dope? I can get the composites, nano composites for my organic applications. Can I use that? How to do that?
It depends. Are you doing the wet impregnation or you are doing hydrothermal?
Actually, we go for calcination. Some nanostructures I need to prepare, sir. Actually,
yeah, obviously, like you have to calcine after putting any metals on the support. But yes, how do you do? Whether you do it by wet impregnation or
yes, wetting. We are using solvent for
wet impregnation.
Yes, yes.
Yeah, you can definitely see, and there are two ways to see it. Your sample, when you see in a stem mode, I would say, normally for this kind of metal supported on oxides, I mean, we use stem predominantly. Okay, because of the Z contrast you get, it's easy for you to find the location of the heavy atoms. So you always go for a stem technique. I mean, if you are analyzing yourself or if you are going for any outsourcing, you can just tell the operator to go for a stem imaging. So there you can definitely see. And if you want to look at whether it's extra framework or it's in the framework, definitely you can go for a SAED at that spot.
No,
so from
I want just metal should be in some compound exactly. If I want to dope molybdenum in alumina, I need to take molybdenum sulfide, or I can take any.
No. Molybdenum the sulfide directly you cannot do. You need to have a precursor of molybdenum, right? So like ammonium molybdate or something you take, and then you have to generate, because molybdenum sulfide is a pyrophoric.
Okay.
So it's not stable in air.
Okay, sir. Okay, direct molybdenum can I use?
Direct molybdenum, no, you can't.
Okay, sir. Okay, thank you.
Hi.
Yes, madam.
I hope you remember me.
Yes, very much.
Yeah. And So maybe we will chat later. My
Yes.
question is, which technique you would prefer for academic side to characterize especially MOFs and ZIFs? STEM or TEM? Which one will be better?
See, if you want to see what is my crystal morphology, yes, definitely SEM will help for you. Okay. So if you have any polymorph or if you are expecting a typical crystal shape, yes, SEM will help you. See, SEM is basically something which gives you a surface topology and shapes and other things down to few hundreds of nanometers. But if I want to know really what is my pore size, arrangement and other things, obviously we need to go to a TEM. So, but doing a TEM for MOF is not a simple
all the things will be expensive, right? Already TEM samples, we submitted samples and we are waiting for more than 6 to 1 year to get the results. But if this advanced techniques,
take that much time, honestly speaking. There are now so many outsourcing available. You should get at least in a couple of weeks, you should get your sample. TEM, I think you should not. Like I said, like TEM is common now everywhere.
Yeah. Anyway, good to hear from you. It's very really interesting. Actually, it is two people, you yourself and Selvam sir. You have touched the actual academics today. Other
Very
people,
fundamental aspects. Fundamental aspects. Yeah, very fundamental.
Really
Very
interesting. Really interesting. It's like a refreshing.
Yes. So when there is no more question, we take an opportunity to thank Dr. Vijay Shankar for joining with us for the conference and delivering a wonderful insight of the electron microscopy. Thank you. We take opportunity to thank you. All of you.
Thank you so much. Thank you. And it's my pleasure to interact with you all. Please feel free to write to me if you need any help regarding any microscopy solutions or anything. I'm always happy to help you. Especially I tell this to the kids.
We will be behind you.
Please,
Nice presentation. Nice presentation.
Yeah, thank you so much. Thank you. So please do drop me. I think Dr. Shakti is having my email. If you have any doubts or if you want to know any techniques, how to do, I'm not getting this, I'm not getting that. So don't worry that your sample is bad. Okay, your sample is always good. Maybe your sample is not suited for a particular technique, and I can help you like how to get the things out of it. Okay, so always please feel free to reach out.
Thank you.
Shakti.
Yeah,
Thank you, everybody. Bye.
If time permit, you can join in validated function and Dr. Reddy's lecture. If time
Oh
permit.
yes, I'll be online. Yes.
Fine. Yeah.
Thank you, Balaji. Thank you.
Yeah. Prof. Swaminathan sir also joined, the president of ISCAS. Welcoming back, sir. And Dana.
Hello. Yes, sir. Yeah. Okay, sir. Now, last session will be shared by Dr. M. Bhagya Lakshmi, Assistant Professor, Department of Chemistry, Central University of Kerala, and the co-convener of this webinar. I welcome ma'am. Ma'am, please.
Thank you, Dana. Thank you. So this is the last technical session. I feel really honored to introduce.
Just 1 minute. Swaminathan sir, Dr. M.V. Reddy has joined. So you can say
Hello, sir. Vanakkam, sir. Vanakkam, sir. Vanakkam.
So he's from Canada and I think now around 7 o'clock. Fine. Okay, please carry on.
So good morning, Dr. M.V. Reddy from our webinar. So I would like to introduce Dr. M.V. Reddy to all the participants. He has received his PhD from University of Bordeaux, France, and he is currently now working as a senior researcher in Institute of Research Hydro-Quebec in Canada. And to talk about his credentials, it is very lengthy, so we can make it very that highlights on his contributions. So before before joining Canada, he was working in NUS also, and his main area of research is like on energy storage materials, composite materials, solar cells, electrocatalysis, photocatalysis, and especially he is working on the novel methods for synthesis of materials for this energy storage applications, and he has published more than 200 papers in the reputed journals. And you can see that most of the some around 65 papers have crossed over 15 or 16,000 citation. It is really, which is really fantastic. We can say that, and we can say our Dr. Reddy is editorial member in several journals like Material Research Bulletin, Journal of Energy Storage. Even I have published one paper in energy storage recently, and also the materials, nanoscience and nanotechnology, all those things. And he has also conducted and delivered lectures. It might be a preliminary lecture, keynote lecture, invited lecture in various conferences all over the world, like Malaysia, Indonesia, Europe, USA, Africa, Iran, Iraq, Bangladesh, Africa, many places. He was a very good motivator for the students. He has guided most of the BTech, MTech, and MSc, PhD students, and he has mentored many students for their project also. So to talk about his credentials in terms of honors, we can say that he has won our Outstanding Science Mentorship Award from Ministry of Education Singapore, and Inspiring Research Mentor Award from NUSHS. And he has also won several awards from Singapore Science and Engineering Fairs. And not only that, he has recently received prestigious Battery Materials Electrochemistry Award from Electrochemical Society of India, IISc Bangalore, I think during January 2021. So we can see that his credentials, and he's a life member in many organizations. And to talk about his contributions, you can see that he's one of the important members in like our Indian Electrochemical Society, India, and many other organizations are there. I think we can visit his website so that you can have a more detailed information on his credentials. So with this very small introduction, I would like to invite our Dr. M.B. Reddy for delivering his lecture to this recent advances in solid state chemistry. Sir, we are very much interested and keen to hear to you. Over to you, sir.
Okay, so again, thank you, Chairman, Professor Bhagyalakshmi, for your kind. I never expected to write this so much. Since you give me 30 minutes, so that I want to make the timings should be okay. Just I'll put my timer on. So basically, and again, I would like to thank Professor Shaktivel, and also first time I've seen that by visually the face with Professor Swaminathan. In fact, he's one of the world.
Welcome to the ISCAS conference.
Yes, sir. Thank you, sir. Thank you. Maybe you might have known G.V. Subbarao. In fact, I'm going to tell that history of what we, in fact, you see, like basically when I was in work with the National University of Singapore, I think there we made a tradition on solid state chemistry, in the sense that although physics department, you work in a lot of materials. I think also during my PhD is one of the well-known solid state chemistry lab. I think all people know that ICMCB. In fact, you see that one of the very interesting discourses happened in the area of the mainly hardcore solid state chemistry. So what I'm going to tell that in this presentation, importance of solid state chemistry, since I'm both specialist in material synthesis, solid state electrochemistry, since my another one is the energy storage, I think is very important. We have to know, in addition to the solid state chemistry, I think we need to know the electrochemistry. Again, I would like to thank all the chemistry teachers from Kerala. I think you people are doing excellent job. In fact, again, good attendance also. I can see that I think although the last presentation still is okay, so good number of attendees clearly indicate that many people are interested in the this type of the conferences. Again, another one in the half of Material Research Society Singapore. In fact, my previous organization. In fact, again, congratulations for the organizers, and then especially Professor Swaminathan. The age, I think he still is active and is motivating a lot of youngsters, like many people in research, including me. I think I listened the morning yesterday and a few talks, really motivational and impressive with the different speakers. So since they've given me time, so I'm coming from Canada, where they was presently based here. French and English speaking colony. So this is my outline of presentation. So anyway, I'm going to, due to time limitation, I have to skip some important, like few important points I'm going to discuss. Again, I'm telling that is very important. Anybody can do solid state chemistry or material chemistry. Just only we need the expertise and some specialty anybody can access. In fact, in Singapore, I had a lot of opportunities. We trained a lot of the junior college and high school students every year. It is almost like 10 to 15 years. The old traditions have been done when I was in Singapore. Anyway, here is difficult because of different environment. These are the small contributions we've been done with various programs from the different including science mentorship and then science research, etc. And also we can see some few publications we've been published based on the these are the small presentation we've been done. So the students have been presented various national and international conferences. And some students have been able to present in various international conferences like Intel International Science and Engineering Fair, etc. So I think these are the small people, although 4 to 5 students from Singapore, as well as partly, in fact, always we motivated many students from India. I think many people, they visited our lab and they finished the PhD work in almost, these are nice, not only India, some few people from UK and Iran, etc. So I think you may see that these are old traditional, in fact, Professor G.V. Subbarao, I think who are the people are working with solid state Indian community knows that he's one of the, all the pyrochlore or one of the old magnetic solid state chemist. In fact, Chowdhury also, all people are familiar with it. In fact, if people are attending ICMAT conference in Singapore, I think all people are familiar with it. And also since the solid state ionics, atoms, and then these are the Poster Eigenmuller. In fact, these are all the old trading long back that is in France. And I'd like to thank some of my present Karim, etc. And also Vittel, also we work on the single source precursor mainly and some solid state chemistry related to the projects. So these are my small collaboration. We've been only the student exchange. I used to help them, many students used to visit our lab and they use our facilities. And at the end, we are able to publish for joint work. So these are the small, my own interest was, and I told you the lithium battery novel materials, look for again, the importance of solid state chemistry will play an important role. In addition to this one, some other areas of supercapacitor and the solid and polymer electrolyte. Due to time limitation, I'm going to focus mainly on some novel, especially for cathode and anode materials. Again, I think just now previous speaker told the instrumentation is very important. As you see, the especially TM, especially batteries, we want like in situ techniques. I think there is a lot of scope for developing the in situ structural spectroscopy techniques, etc. So the one slide is the importance of energy storage. We talk about the batteries. If we need the store the solar and wind energy, or you want to talk about smart grid or all the applications, battery material will play an important role. Again, use of this material, for example, major cities, always we can reduce the environmental problem. For example, especially major petrol, if you reduce the, by use of electric battery, like battery vehicles, we can reduce the pollution. That is the way throughout the world, including that not only in India, throughout the world, always people are concentrating there. Look for the alternative fuels, for example, battery materials. So again, all people are using this type of mobile phones. You have this type of the pouch cell, and for example, if you're using cylindrical cells, if it's your laptop, or so in future, if you run with electric vehicles, we use this type of different type of cells, and they can put it in a different big packs. Again, you can see, so we need more energy. We need people to put it in the different type of packs, etc. Again, if you talk about grid storage, again, the casing materials are same, only casing and safety are all factors to take into consideration. So these are very important points you to consider. Always look for high energy density, high capacity, and adopt the climate condition in the sense that always look for the material should be, especially temperature and long cycle life. I'm going to touch about the importance of working voltage, Coulombic efficiency, impedance should be lower, and we want to be fast charging. So always people are telling that, okay, shall we use the battery for within 1 minute, 2 minutes? I think it will be difficult. We know that these are solid state materials because of diffusion problems. So that at least lithium want to come in and go out. We need some time to, that's why still there is a lot of improvement is happening, especially in terms of material development. Again, the resolve importance of the solid state chemistry. Again, after looking for safety, cost, and toxicity is very important as an industry. Always, whatever the way you do, I think these are very important. And at the end, we have to look for the what they call sustainability or recycling or circular economy. This is very important for. I think all people are familiar how they know that all people is simple electrochemistry. We may see that you may get some positive electrode, negative electrode. So, and there is the electrolyte and separator. I think yesterday Sampath also mentioned that some of the important point, especially if you use organic electrolyte, remember, always you can go up to 4 volts. If you use aqueous based electrolyte, we can go to the around 1.25. Again, there is a limitation of energy density. That's why, so always you to look for the above 4 or 4.2 volts or 4.5 volts. So I'm going to touch up on the importance of the energy density, etc. So again, negative side, graphite, lithium metal, or if you talk about the sodium batteries with the sodium metal or some hard carbon or potassium, etc. Again, there is a way it depends on the people always call the sodium battery, lithium battery, or potassium battery. Again, the importance all should make if you take lithium cobalt oxide is the lithium base, or sodium base, sodium cobalt oxide, potassium, etc. So these are very typical things. So due to time limitation, a little bit fastly I'm going. So later, if you are interested, I'm happy to spend more time on this one. Again, since the electrochemist, always we call a charge means oxidation, analytic scan if you do, and positive current. If you're electrical engineer, you call it the state of charge, and discharge reduction. These are all the common electrochemist we use. So, and electrolyte is the things, if you use liquid electrolyte, always remember liquid electrolyte advantage is that we don't have any problem with wettability, nice. And sometimes people use ionic liquid, ionic electrolyte, and polymer and solid electrolyte. Again, here there is a lot of scope for the polymer chemist or inorganic chemist developing the novel lithium base or any potassium, any type of the electrolytes you can develop. So again, I think these are the important points. In fact, we want to see the early history. I think you people are familiar with 2019 Nobel Prize is given to the chemistry. In fact, one of the good both physicists and chemists, especially John Goodenough, I think he's 99 years, one of the oldest Nobel laureate. Now, what I'm telling, in addition to another 3 important persons, I'm mentioning Michel Armand is one of the French chemists. He contributed to the early development of, for example, lithium batteries. You can see the early paper with 1972. So intercalation, and then followed by, in fact, all the discoveries started with, for example, John Goodenough. So this early work from the sodium cobalt oxide with Professor Eigenmuller from France, my previous institutions. So again, always all fundamental research has been done from the university or academic institution. They once, usually as the industry, they took the ideas, for example, so lithium cobalt oxide is taking the idea of this sodium chemistry, and John Goodenough used the lithium cobalt oxide. Finally, his idea revolutionized the concept, and then now Sony, all the industry, they use these things. That's why academic research is very important. That's why places like or any central university, any IIT, so partly some of the novel research is very useful for it. So these are the things. For example, the lithium move from one side to another side where the electron will pass external circuit. So then the main issue is that if it is a metal ion, is a cobalt is 3+ is there when a charge means oxidation. Again, for example, when you remove the lithium from the structure, cobalt 3 to 4+ oxidation state will occur. The same thing if you plot the current versus potential plots, you can see the cobalt 3 to 4+, this is called as oxidation. Again, reduction, that's why we call it rechargeable or call it oxidation reduction. So these are typical things you have to do any electrochemistry. If you do anything, that's why we have to get a positive and negative current indicate these materials are rechargeable. So this typically, if you plot a voltage versus what they call the capacity or the time, the galvanostatic potential. So we get a plot potential, for example, cathodes, we can get some voltage, and then, so typically any electrochemist or material researcher, once you prepare some new materials, always you have to go to extended plateau, like for example, this plateau, and we have to get a higher charge potential. So that is the way energy density will define. So we always have to look for the higher the charge potentials. So it is nothing but difference between charge and discharge is the voltage of the cell. So higher is better. That's why graphite is more popular because of this width is high. And then also graphite, we can, that graphite mines naturally occurring materials, and we can get plenty of materials. So these are the different type of electrochemical mechanisms. It's been, in fact, as a, if you wanted to produce any electrochemist, once you go to a lot of materials, any chemistry, all solid state materials, we broadly classified 4 type of mechanism. Among more popular is the intercalation, the all commercial batteries, anything will under intercalation, Again, the importance of the what they call a solid state chemistry, electrochemistry, and especially instrumentation is very important to understand this type of mechanism. Since it's more not so, again, here we don't see less volume variation. Again, the importance of XRD, we tell that what are the variation of lattice parameters, etc. We can see. And for example, you take depending on the, for example, tin silicon alloy formation, we can see. Again, here people have been already demonstrated how the volume expansion, contraction by using, especially not only XRD we've been seen, and also with the TM, people have been seen that how the in situ measurements have been done. In fact, there are conversion reactions and then alloy-based systems. With time limitation, I'm going through. So these are very important points you have to consider. If any lecturer want to do any research, always look for the low atomic weight. So any materials, whatever you do think should be, so our theoretical capacity is nothing but 26,000 number of lithium by molecular weight of any material. And anodes, you have to get a lower discharge potential. Cathode should be higher charge potential. So voltage of the cell is nothing but difference between the average charge minus discharge. So that's why if you talk lithium iron phosphate, 3.5 minus 0.25 this away. So energy density is nothing but voltage of cell multiplied by capacity. So always now the main idea is that if you do any new materials, always you get extended plateaus and voltage should be higher is good. That the main issue is that now there is a lot of scope for the solid state chemistry. Look for some new materials. I think you may extend up maybe 300, 400 milliamps. I think really useful for the battery community. And again, we have to look for the cathode anode must not be soluble with the solvent, in the sense that you electrolytes also very a lot of opportunities to design novel electrolytes, or for example, stable ACI, etc. And again, we would look for cathode anode. We look for the material should be good electronic and lithium ion conductor. We want there is like nothing mixed ion conductor. It's very important, so that if people want to be fast charge or anything, so we need to. So these are the important 4 points you have to take into consideration for, especially 4 or 5 points you take into consideration designing the new materials. So if you talk about this, based on this one, due to high energy volume energy, that's why, and voltage, lithium is more popular. That's why we can use it for the different type of the applications. I think liquid electrolytes, I'm a little bit quickly I'll go through, since I think previous speaker, Professor Sampath, already mentioned that. So what I'm mentioning that so usually if you talk about the inorganic electrolyte, either by lithium, sodium, potassium, we need a respective salt. Inorganic salt we need, and then we need some protic organic solvent. Again, we can go to higher voltage and reasonably what they call as good conductivity we can get, and there is a flammability and then sealing issues. That's why later people are looking for the polymer electrolyte again. So advantage, and in combination with ionic liquid. So again, at least we need some slightly higher temperature in order to get a reasonable conductivity. And again, if you use either PBS electrolyte, we need a separator, because the idea is that separators are the things we can avoid the short circuit. So again, so there is a lot of opportunity for the polymer chemistry. That's why importance of the chemistry will play an important role in the especially separator, inorganic, organic, and then solid state chemistry. So again, I'm mentioning that there is a safety issues either due to the flammable electrolyte or the oxygen release with materials and malfunctional electronic circuits. I think recently, I think the solid electrolyte play. There is although it is a fundamental. The problem is if you make a ceramic pellets to press all cathode anode and electrolyte, with high temperature is a major question. That's why the problem contact, and there is a problem with the interfacial issues. So sometimes while heating the materials, you may get something like there is a reactivity, etc. In fact, there is extensive work we've been in fact done solid electrolyte. In fact, I don't want to discuss too much details on the system. In fact, previous speaker already mentioned that one. So again, so this is a little bit a new area. In fact, there is our lab is already called as solid state ionics, is a part of mainly dedicated to work on the new development of this electrolyte. Again, if you talk about different type of sulfide-based electrolyte system, and again, the advantage sulfides are a little bit reasonably good ionic conductivity. Again, sulfur is, you know, that it is a messy system, it is hygroscopic, again, stability issues. and sometimes oxide base seems to be good. Again, we need to make a good conductivity. We need a good sintering in the sense that we have to good high temperature. We need a spark plasma sintering. So all the things we need to make a good, reasonable conductivity. We can make a small pellet. For if you want to make a A4 sheet type of materials, we need to think there is a lot of interesting debates going on. Sometimes we mix with a composite, for example, in a polymer, the conductivity will decreases. So this again, the material processing and characterization technique is very important. For example, you can see that so either you can do different type of materials depending on size and shapes. Again, the importance of the solid state chemistry, either you can do depending on expertise, we can try to prepare the materials in a different chemical method. In fact, we love the things, we have a lot of expertise in these materials. And again, the fundamental thing is that if you want to do any complex, any new materials, always you consider the charge and ionic radius. So make sure that everything has to balance, then only, anyway, you can make some defect. Overall reality is that these are the important points you have to take into consideration. Again, if you are metallurgist or so you need something like after waiting nano, what are the materials we need some, what they call densification, we need something like powder metallurgy approaches. In fact, I'm not, since although I'm physicist, because since I work on thin films, my PhD, those are all things I don't want to discuss. There is another separate topic, so how the importance of physicists. So I don't want to convince too much in this conference for the physicists. So that's why, so there is a lot of extensive. And again, people have been asked that these are the XRD is very useful tool. In fact, according to me, without any TM, you can do X-ray. I think is enough for you. So later, if you want to more depth, you want to be really nano size or size dependence things we can do. And especially for thin films, we need a specialized technique, RBS. These are all things I think accessing it will take some time, especially for the TM. So I think it's very, sometimes people are looking for a usual way that always I do the X-ray, XRD first, make sure that then once X-ray is enough to do all the European electrochemical studies, either by galvanostatic and cyclic voltammetry and impedance studies. And anyway, we can do, for example, BET, etc. And for example, some materials we can do magnetic studies and IR Raman. There are all the standard techniques we can get. And in fact, the previous speaker, morphology, by using that SCM and TM, etc. Again, depending which type of shapes you're looking. I think just now people have asked, these are the softwares we need. Commercially available, like for example, ICDD software or ISCO, and PDXL, there are the, and if you have XPS, we need this type of software, or for example, impedance, we need the Coraware, etc. In fact, there are all things I can spend almost like 2 hours, is not amazing. So only is that due to time limitation, I'm going to, I think just now such Sectwell asked and I opened my slide. So usually that, for example, anyway, with the TEM simple nano size material, the amorphous material looks like this way. If it is nano size, usually way that again, it is very complex. It depends on what type of highly crystalline material. You may not see this type of circular ring. Depending on that one, at least we need a lot of, if you go for more depth. So usually the typical nano size materials, what usually I use, we do is that take a small ring, this diameter divided by 2, 1 over D. So this D value close, usually we can compare D value belongs to low angle. So that's why it is better for you to just check with XRD, by knowing the D value, and we can get some idea. So that is a little bit better for you people to do concentrated things. I think these are the various 7 crystal systems. In fact, I'm going to, don't have much time to discuss the details. I think these are the various tools, for example, battery tester, impedance analyzer, etc. So due to time limitation, I'm going to be telling some important materials, for example, cathode-based system and sometimes anode-based, again, material synthesis, and then people have been done with some surface coating, etc. Again, importance of the solid state chemistry or some other chemical method. So these are the various layer type, and for example, olivine and then triclinic structures and cubic type of structures, lithium-based systems have been done. So these are the various redox potentials and then expected theoretical capacity. And there remarks are there. Again, if you have 2 to 3 elements are there, always you should look for the what they call co-precipitation method. So make sure that you need atomic mixing. That's why. So don't try to do with any metals. We need a respective either sulfates or nitrates or salts. We need to make a respective hydroxide, etc. So I think this is very important, the chemist. So usual way that, so if you want to do carbo or a graphenothermal reduction, we need a carbon to reduce metal oxides to higher to lower, depending on how much oxidation state current appropriate amount of carbon you can do. We can reduce it. This is the one way you can try to prepare the complex oxides. You can do something like lithium iron phosphate or vanadium So again, different type of things we can do. In fact, in this approach, we've been done with some of the metal cluster compounds. Usually, the olden time they used to seal tube. So in order to avoid that one, we can mix with some carbon with respective things, put it in tube furnace, pass with argon gas, and we can get a respective oxides. Suppose people want to be some nitrites, so again, we have to pass with ammonia gas. Again, remember, if you want to prepare nitrates, we need a porous sample so that ammonia gas has to penetrate. There is a way importance of the, and some people are working with catalysis. For them is that we need the metals, respective carbon. So more carbon is needed, so porous matrix is needed, especially for battery people. We want to be metal. We need appropriate crystal structure is needed for this one. So again, these are the various, this lithium iridium fluorophosphate, one example, and these are expected redox potentials. So again, so you can see we can try to prepare the sample. It is a triclinic structure and there are various lattice parameter. So typically you can take 70-15 weight per active materials mixed together. If it's a aluminum foil per cathode, current collector, all put together, make into slurry. Once slurry is ready, coat it on the current collector, roll it, and we can get a small type kinds, this type cell you can do in the lab scale. Once you're able to understand the mechanism, you can do pouch cell, or big things we can do, only big labs like here, or some other national labs like our industry can do. So industry usual way is that they can take kilograms of sample, they can do, everything is automated, you don't need to worry too much. Again, academic reach for new materials. So these are the kind cell you can do. You can put bottom cap and your material, put it in the lithium metal, find the cell is ready. Either you can do importance of the, especially you can do galvanostat, potentiostat, and impedance analyzer, you can do understand the mechanism. These are the typical charge managed discharge potentials for the cathodes and anodes. And again, as I mentioned, compared to all three types of cathodes, again, the lithium iridium fluorophosphate seems to be good. And reasonably 6 months, we can able to cycle. And again, we can understand by either by XC2, XRD, or sometimes we can do in situ also now. And for example, we can do some impedance studies, how the resistance of the cell, and we can do the phases, the part of, I try to understand what type, it depends on system. We can understand surface film resistance, charge transfer, or bulk, etc. I can do. So in summary, if you want to be new things, always keep in mind the voltage, higher voltage and high capacities are a very important points to take into consideration. So these are a few novel-based vanadium-based systems have been explored for the first time in literature. It's something like lithium iridium fluorophosphate and metal organic inorganic framework. In fact, these are a lithium first few examples we've been done. So this is with Professor Vittal, also with our collaborator. So again, we demonstrated the sample either by simple chemical approach with hot plate, we can do something. Again, remember these are metal, we need to get it out of the water. So that's why we have to heat the sample at nearly 150 degrees, make sure that, and we have to characterize by using this XRD. And again, the importance of the X-ray crystal powder, X-ray diffraction, etc. Anyway, you can do, these are the routine characterization either by XRD, for example, XPS, and then ACM, just to see the morphology, etc. So since as an electrochemist, always very happy, we are able to get nearly 4 volts we can get. These are real cathodes, the early example. And reasonably, so we know that depending on slight improvement in the temperature, we can see because of the improvement in conductivity, we can see the improvement in the capacity. Still, there is a lot of scope for this type of materials. We look for the low atomic weight. So then only we can get improved performance. So in terms of the potassium system, as I know that potassium is higher ionic radius, again, the mobility issues, and sometimes electrolyte, although we can get lower capacity. Still, with the recent report based on our report, then from Japan, the people have been already concentrated a slight improvement capacity can be done by using this system. So these are the lithium vanadium fluorophosphate cathodes. So again, so the early report and followed by including Manthanam from John Noble laureates. Again, they have been really put the system. I think they have improved the performance. Again, the importance of your material synthesis. You can try to prepare things. Again, importance of this, what they call as the X-ray crystallography. We can analyze the phases, etc. So again, we are able to get nearly 4 volts. Still, there is a lot of scope to improvement in the what they call as energy density and capacity, etc. I think either you can do phosphite, HPO3 and HPO4. These are all the inorganic and material chemistry we can do. We have been looking into a lot of the new type of systems. So I'm going to skip a little bit details since they're given me. Also, people are talking about the sodium. I think sodium is already known. It's not a really old. You can see the old papers. sodium cobalt oxide is almost 1973. So the why people are the main sodium compound will be hygroscopic and then voltage issues. So that's why, yeah. So if you talk one example, so I'm going to finish within 5 minutes so that my time is okay. So if you talk about the lithium based and sodium is a lower energy density. So again, another important point to remember is that people are talking about, is there any alternative to sodium for electric vehicles? For example, so lithium or sodium. So again, the lithium is low, what they call as in terms of environmental availability, lithium is compared to sodium. So still lithium are popular because of the what they call as a plot potential, and also so now what I am telling that in addition to the especially electric vehicle development, not only other material, other important thing is people talking about the permanent magnets. I think there we need some rare earth, that's why it is places like in China, there are a lot of rare earth, that's why it is more popular, especially. So that's why not only this material issues, in fact, the other points also you have to take into consideration. People are talking about the cost. So in terms of anodes, I think I don't have much time, I'll skip the details. So again, the graphite is more popular. We can get, so we did some graphene again. Although we don't climb the graphene, although we get high capacity, practically graphene alone, we cannot replace the graphite. Always keep in mind, we have to get a lower discharge potentials is very important. And I think these are I'm going to skip the detail. Again, the importance of the in situ, XRD, X-ray, XAS, etc. is very useful to understand the mechanisms. So I'm going to say again, it is the importance of the solid state chemistry. In fact, there are new formulas starting from the various hollandites, pyrochlore, tin pyrochlore. Again, remember, so we need alloy forming element accordingly. We have been looked in some new formulas have been contributed in this field. I think the red belongs to our group, and then few others from the France. So again, I think I have another 3 minutes are there. I'm skipped details. Again, some of the things, importance of solid state chemistry. You can try to prepare the high temperature synthesis, or you can do ball mill if you want to be nanosize. Again, there are early first few examples have been reported. So I'm going to skip again, another important topic, a lot of conversion based systems have been, in fact, they're all things already known. It's not a really new thing. So what I'm telling you that, so as a electrochemistry point of view, I think we have to reduce the discharge potential is very useful for the practical. Although we climb high capacity, practically we need to reduce the further average charge discharge potential. Again, the importance of electrochemistry will play an important role in this type of research. So I'm going to skip these little bit details and some of the importance of these are all the formulas we can see. And then, so what I'm going to tell is nitrites, again, if you take with oxide, 2 lithium can be reacted, and if you take a nitrogen, only 3 lithium. So again, so although we can get slight higher energy density, again, the issue is a little bit voltage issues are a little bit difficulties. Again, these are few, if you go for nano size to bulk and say the variation of the capacity, etc. So I think I have another 2 minutes. So again, I love molten salt. In fact, I don't have much time to discuss. So again, we can do importance of the solid state, a lot of interesting things with the different salts. We can try to develop either lithium based or semiconducting materials or some spinels, etc. And very recently, I think some of the garnet based solid electrolytes have been demonstrated for first time use of the molten salt approach. So I'm going to skip the details. Again, the importance of if you go to surface area, and if you go from nano size to micron size, how the energy storage performance is going to vary. So again, in summary, depending on salt, depending on temperature, you can do interesting what they call as the chemistry or applications, etc. So again, I'm going to skip little bit details since I don't have much time to examples, supercapacitor or electrocatalysis, etc. So again, I think people have experience in the organic chemistry, or still there is a scope. Again, the problem is that we don't have any good average charge potential. We cannot see little bit difficulties in this use of this organic based system. So again, these are the importance of some solid state. I'll skip the little bit details since they're giving me 30 minutes. And so quickly, I'm telling that one last slide, the importance of the in situ techniques. For example, I know that always there is a safety limit. Always the water supplier, they suggest accordingly can do, don't increase the limit. So if you increase the limit, there is a huge volume variation. That's why sometimes there is oxygen release, sometimes there is safety issues. That's why, so sometimes catching fire, etc. We can see that's why depending on appropriate electric materials, we need the appropriate voltage limit to take into consideration. And also you can do some fancy technique like in situ, neutron, etc. We know the light elements like lithium. So neutron seems to be still, let's say X-ray, XRD is very useful. We can do some in situ studies, etc. I can do in the labs, etc. So, and also some fancy techniques, for example, NMR, etc. I can do, or sometimes X-ray absorption spectroscopics. I think one last slide, I think whatever research you do, always you to tell some stories in a way. So as a researcher, it's nice to maintain the sustainability, always to recycle it. I think we cannot throw any battery in dustbin, always you to properly recycle it. I think these are the various things, consequences, and these are almost like 11 million metric tons of spent batteries have been discarded by 2030. That's why there is a lot of interesting things going on with different how to recycle the material by using the importance of pyro and hydrometallurgy approach. So in fact, these are the things I'm going to skip. In fact, these are the small conclusions. Again, the solid state chemistry will play an important role, and also we can tell so many materials. Among them, only few materials are useful for the practical applications, mainly due to the voltage. I think these are the small contribution in huge systems have been lithium-based or sodium-based or potassium system have been done, and some of the new inorganic compounds have been developed from our group from the last 15 to 20 years. So I think I'm going to already exceeded 2 minutes. I'm going to thank you very much. And then if you have any question and answer, happy to take. So our other option is that people are hurry, and then maybe you can, we can discuss, okay? So I send my email. In fact, any students are interested, I think happy to discuss, okay? Especially the academic research. So it is very nice. Thank you very much, sir. Thank you.
Thank you very much, Dr. M.V. Reddy, sir. Actually, we have squeezed you. I think you have a lot of things to discuss. But since because of actually we planned for 3 days, maybe because of other things it is constrained. Anyway, it is a very excellent presentation on electrochemistry. There are few questions from the participants. Let us hear. You can answer them. Then I think if anybody wants, they can ask. I hope. So there is one question from Tiwari. What to know about graphene oxide based supercapacitors?
Okay. So I think I can answer some. This same thing with what is Abhishek. Also among the graphene oxide reduces. It looks like is a good conductor. Usually, in terms of electronic conductivity, people want to see what they call graphenes will be better, because we know that oxides are there. Reduced oxide conductivity may not be really good. Usual way is that we can exfoliate it with high temperature so that we get rid of all this hydroxyl groups, everything, so that automatically your conductivity. So in terms of supercapacitor, always look for, you remember, the concept is that whatever the way you do, we need a high surface area. So that's the usual way is that expand it. So in order to make carbon alone, so that's why I didn't discuss. Usually, if you want to be rectangular plus, like carbon, like a lot of carbon source system or system can do, or if you want to metal oxide, mix with your graphene, RGO, and mix with composite so that you can get what they call as a pseudo capacitive behavior. You can do that. That's okay. There's a little bit. There is huge research is going on. I don't want to tell that say there is old electrochemistry. So only people are playing with the chemistry of materials and etc. I can do. So as a electrochemistry point of there is still people are more popular in terms of the carbon based. Activated carbon is more popular. Why? Because we can get a rectangular plot that is very useful for the practical applications. Okay. Still, as a researcher, as a chemist or solid state, we have a lot of opportunity. In fact, I didn't tell that my bunch of some materials people can use it. So that is the way we can contribute. Yeah. Yeah, I think that is okay.
And one more question is also there from Abhishaka. I think same thing what you have answered now. It will for that.
Yes,
among graphene oxide, which one is a good conductor? And one more question is there. Where it is?
I
something
think
about. Yes, actually, you have answered all. I think. Any other questions from the participants? One take from the participant. You can interact with the speaker.
Hello, sir. Swaminathan, sir. Please slightly. I love the old.
You have given a very, very nice lecture, and then lot of information. Now, as she said, this pieced together within half an hour. Anyway, and this now future is going to be on electric cars. Now,
yes.
What about cost of the lithium-ion battery to get reduced and all these things? Any idea? I mean, anything about OP
Sir, yeah, maybe I quickly I will go through because sorry, sometimes it is 30 minutes again because see some slide because the electric vehicle, although battery is one of the main thing. In addition to this one, that we need what they call motors, like it's a soft magnet like neodymium, dysprosium. Those are rare earths also cost. So that is only wherever the people are getting. For example, China, they have a lot of sources. Those are the especially places like here in Canada, there's a lot of natural resources. Those are the things people have been dominated. So what I'm suggesting is that cost. Still people are reducing. Yeah. Still people are reducing. Yeah, maybe I'm going to discuss. I'll finish with the professor. Okay. So what my personal opinion is, still lithium is famous because we need a plot potential. That's why once you solve this one, the people they may think about the sodium again. The sodium is also we work in the world system. The problem is these materials are like what they call stability, and people are looking for sometimes what they call as academic is fine. If you go for industry, there's a lot of different criteria. So that's why these are a little bit average potentials. These are the important points you take into consideration. Yeah.
Okay, sir. One more thing.
Yeah.
I mean that actually, that the olden days we used to have the dynamo in the cycles. You remember that? I think.
Yeah. I remember. I also.
Is there any chance of charging the batteries through the dynamo while driving the car or while driving any vehicle? Is there any possibilities there? I mean,
in fact, I know again, since we are chemists, we are talking about the story. If I talk with mechanical engineer, electrical, electronic engineer, if I talk with them, yes, these are the questions you will learn. In fact, a lot of things is going on. In fact, see what they call as the auto regenerative. These are all things is going on. A lot of technology, a lot of the only thing people, what I am telling that in order to this one, whatever what they call as the, so see, for example, the electric vehicle, we need more energy. Whatever we can do, dynamo, that may not
if it comes to practical use, the charging discharging will be reduced.
Yes. The problem is the cells, the dynamo may be useful for 2 to 3 cells. Since if you take electric vehicle, the big 1850s, almost like 2,500 cells with the big cells, because since we need a lot of energy, that's why with low energy, yes, there is, for example, those are the alternative. Still, I think future, a lot of ideas is people are spending in a different way. Still we can get that. So there are things, Thank you, sir.
Okay. Thank you very much, sir. Thank you very much for your clarifications.
Sir, somewhere.
One of the participants, Meena, wants to know about fluoride ion batteries.
Okay. So again, the story is that if you talk about the fluoride ion, or so if you make a fluorine containing materials have been done, or fluorine, like for fluoride ion batteries, we need a fluorine containing, for example, I didn't discuss with some oxyfluorides, and we need a fluorine based electrolyte, and then so that is why again the problem is that that although people in terms of still the popular lithium because of in terms of the what they call as the flat potential we can get and higher energy density. That is the best on that one. In terms of practical application, still that is good. So anyway, fluoride ion and different type of the systems we've been already looked into. The problem is whatever the research I can do, magnesium or zinc, all this one. So the divalent ions, because the mobility issues and little bit difficulties are there. Still the popular is this one. Still as academic research, yes, we can do that. Nobody can stop us since we can do anything, and that is the way research will go. I don't tell that you cannot stop. Still, you can try, and then again we work with the electrochemist within the department. So just that is the way you can do fun. I know that as a young researcher, you have a lot of ideas. Just you can try. I don't tell them don't stop. Still you try. If it works, is good. So what my personal opinion is that we need a small potential start. You can do your own way. So that if you depend on other people, again, for example, TEM, you would wait for a long time. That is not a really research. Still, anything you do it, whatever the possible within department or within your university. So that makes your work a little bit faster. That's why.
There is another question by Murugavel. What about recovery of lithium from used batteries?
Okay. In fact, again, I didn't discuss about the last slide. I discussed about the material recovery. Yes. So that's the way usually what they call as material. So usually lithium, we cannot get it. What they use lithium carbonate. If we take lithium cobalt oxide, react with carbon, we can get a lithium carbonate plus cobalt oxide. Then the main issue is that recovery. As an industry, they talk about what they call recovery cost, and for them it's expensive. That's why that little bit. If you go for more materials, no other option. Still, we have to recover. We cannot throw in a dustbin. So that's why what people are telling that you not avoid that one. That's why the battery pack, including while buying itself. some cost of the recovery things is also included, or sometimes government initiatives to get some what they call as recyclers, so that because we know that if you have 2 to 3 elements are there, so we have to separate it again, powder metallurgist, and we need a lot of so again the cost will improve very. So if you talk about the industry, yeah, yes, it is possible. In fact, I think it is possible to, yeah.
One more is also there. What about solar chargeable materials for cars?
Okay, again, the problem is the solar, solar roof, for example, that if you make any solar plant with this type of A4 sheet, if you get it, it's good. So people have been demonstrated. The only problem with we do not energy, whatever the energy with the solar roof, it is not possible. At least that's why we need a little bit bigger area. That is the only thing. So people, suppose, for example, in traffic roads, we don't have any big type solar panel. You're going to be traffic issues are there. That's a little bit difficulty. Yes, people have been demonstrated to make a bigger area, or with a smaller cars is possible. So, yeah.
I think no more questions in the chat box. Any other question means you can directly contact the speaker. He has given the email ID. We will share with you all those things. Thank you, sir. It is really very interesting, and I think you got more questions among the speakers for the past 2 days. Maybe all are interested in electrochemistry, so we will be in touch with you for another electrochemistry conference, I hope, near future. So I am just giving a token information for you, so that we will be inviting you. I think no more questions. Any questions from participants? I think no more questions. I think we can thank Dr. M.V. Reddy for his valuable presentation and information. His expertise is like it has to be exposed, and everybody has to be has to recognize that, so that we can do some sustainable contribution to the society. I think sir is doing that from Canada, but it can also be to our country, I hope. So thank you very much, sir. Thank you very much for being with us today. Maybe we'll be in touch with you, sir, in near future. Thank you very much, sir. On behalf of the organizing committee on recent advances and solid state chemistry, I thank you very much for this wonderful presentation. Thank you, sir.
Okay, thank you very much, madam. Thank you, Professor Shaktivel, and then Professor Swaminathan. I think thanks for your time. I know that you attended most of the talks. I think with his age, and you will be more dynamic than we was. So I think we have to learn lesson from you. Always, because
all with the encouragement by all of us.
Thank you very much, sir. Thank you very much, sir. Thank you.
It is a wonderful lecture, Dr. M.V. Reddy. Sorry, we have to time limit because as Madam mentioned, we have to go for the 2 days. Initially, it was planned for 3 days. So that is the reason we have to squeeze the time. So sorry for the inconvenience we have to, but anyway, thanks. And it is really privileged to have you. And I thanks Dr. Bhagyashree for the sharing the session. Yeah.
We can applause.
Yeah. Please.
Okay. Thank you very much, sir. Thank you.
So we hope we will see you offline soon. Thank you. So let us move on to the validatory function. And Nimisha?
Yes, sir. So we are going to the end of our 2-day webinar that's organized by Central University of Kerala in association with ACT and ISCUS. So first I welcome Professor M. Swaminathan, sir, the President of ISCUS, for providing his valuable feedback of this webinar. Sir, please.
Thank you very much for that opportunity. So we have listened to that, nearly about 10 lectures for the last 2 days. And all the lectures were, really excellent presentations by all the speakers, not only in one field, in the various fields of solid state, starting from the importance of solid state chemistry. And it has given exposure for all the students to the different fields of solid state chemistry. And as I said, that the research scholars, particularly that research scholars or even the faculty members, they can contact the speakers for the future, even collaboration or for interactions and other things. As said earlier, that their email ID is available, and then the students can interact with them so that they can be, use that expertise and then for the future research work. Another thing is that I know that, the ISCUS has a very good visibility now, by the conference organized by the webinar organized by this Central University of Kerala. So it should, should very appreciated. Actually, I appreciate the efforts taken by the, starting from Vice Chancellor or the Dean and the conveners and co-conveners, because all the work is done by the conveners and the co-conveners, the team of the people. So I appreciate, and then I actually congratulate all the people for giving me, a very good exposure part of the ISCAS. Because after the 2 years, the conference is being organized. We had the conference in 2019, 11th National Conference in Nagpur. After that, we are not able to convene any conference due to this COVID pandemic. So 2020, we didn't have any conference. So 2021, this is a conference which is giving a very good exposure for the people. And you know that importance of solid state chemistry, all of us know, no materials, no progress. Because this is a basic thing, that no material, no progress is there. So all the materials, because as Professor Selvam pointed out that, everything is depends upon that materials. The future world is going to the worlds of, material world. So the last lecture, that how much, information we had for all the application of the materials, whether it is any problem, because the future problem is going to be energy and environmental problems. All the problems can be solved by only the materials. And another thing is, this is an application oriented field. So basically, I am a physical photochemist. Still, I remember the paper which I published in JACS in 1983 had only 50 citations, whereas that paper which I published in 2004 in Silver TiO2 had more than 500 or 600 citations. Why I'm telling is this is more application oriented, because everybody is interested to work in that solid state materials. So I think this conference will give open a way for all the students and the faculty members to pursue their research in the solid state. And as I told you that basic aim of the ISCAS is only to promote teaching and research in the solid state chemistry, which is fulfilled by this webinar. So I think that all these organizers are to be congratulated, and this one appreciated. So thank you very much, and thank all the organizers, and as well as Prof. Saktivel and his team like Bhagyalakshmi, Ravi and other, I don't know, all the people, and all the people for their efforts to take the conference and then to go to all the people. I have not listened to all the oral presentations, and the oral presentations seems to be very good. Only a few presentations I observed. They are all found to be very good. And then it has gives a very good platform for exposure research in the solid state materials. So once again, as on behalf of ISCAS, I thank Central University of Kerala for arranging this webinar. Thank you very much. Thank you one and all.
Thank you very much, sir. I now invite Professor M.R. Pradapachandra Kurup, sir, the Dean of Physical Sciences in Central University of Kerala, to speak a few words in this occasion.
Under the department, Professor Saktivel, and he is also the convener of seminar, and Professor Swaminathan, Dr. Bhagyalakshmi, co-convener, my colleagues, Dr. Binay George, today.
Not audible.
It's not audible.
Now it's okay.
It's not audible.
Now it's okay. Now it's correct.
So, from the words of Professor Swaminathan and also the reactions by the participants, it is a well thought out and well arranged seminar with many speakers from abroad. So the pandemic actually has helped us to have people from Mauritius, Canada, Australia, France to come over in the online mode to the Central University of Kerala. And this seminar actually covered a lot of basic aspects and also the applied aspects of solid state chemistry. And The students, research scholars were all given sufficient time. Actually, we got a lot of requests for oral presentations, and most of the oral presentations also were very well presented. So I would like to thank ISCUS and Association of Chemistry Teachers for having the support for this. I also congratulate Professor Shaktivel for shouldering the responsibility of arranging this and inviting excellent speakers for this wonderful 2-day seminar. I hope that all of our participants will make use of this conference so that they are all benefited, and also the solid state chemistry teaching and research in this country will be very much visible in the years to come. Thank you all the participants, and have a nice time for you. Thank you all.
Thank you, sir. Is it time to hear from our participants? I request a few of the participants to unmute and provide their valuable feedback.
To hear you from how we can improve further.
Sir, I am Raman, most respected elders and the dynamic organizers. First of all, I thank you for given me this opportunity, even participating in this pandemic period, as Professor Karp told. So it is really an international webinar, really, because as he rightly pointed out, we have the opportunity to see, to hear, to listen, and to interact with so many, resource persons from different parts of the world, not only our country, but also, as rightly pointed out, from Mauritius, Canada, and other things. So I thank the organizers for selecting the apt resource persons in this, the topmost scientists, the resource persons in this field. By participating in this webinar, not only we know the basic fundamentals in details, in the solid state chemistry, from basics, basic to the research level. Because as a teacher, the research and teaching should go hand in hand. We really realized these things. So definitely, sir, this is very helpful to other teachers like us. So not only the research scholars and the students, but also the teachers. This webinar is very useful to us. Thank you, sir. Once again, on behalf of the participant, I thank the organizers. And long back, I am seeing Professor Swaminathan, sir, by attending this webinar, and also Professor Karp directly. Thank you very much the organizers for giving this platform to meet the leading scientists, solid state chemists in this field. Thank you, sir. Thank you, the organizers.
Thank you, sir. Any more suggestions from participants?
Another son, can you be? Is there?
We can, any one or two participants can give the feedback if they wish. Any participant is interested in, yes, somebody has. Yes, please.
Any students or research scholars? Please.
Mr. Anpu, would you like to speak?
Any students participant?
Yes,
Anybody?
good afternoon.
If somebody is interested to, you can give this feedback.
Yes, yes. Good evening, sir. Very
Yes.
thankful to Central University of Kerala for organizing this webinar. I am a research scholar at the Department of Chemistry, Annamalai University. So I attended almost all lectures regarding my work. So many solid state techniques and so much data I have collected from these sessions. So a lot of enthusiastic and professional people from all over the world, they have attended the webinar. So very good appointments I have encountered. It's more elongated means very helpful for us in the future to conduct this type of seminars, because I will also be much interested to participate in worldwide sessions. So international wide, if you expose, then only we need to know what research work in the field ongoing and what are the developments we need to we are much encountered. So I wish all the thanks to the all the organizers who are conducted this webinar. It's very helpful to my future research work. Thank you.
Thank you.
Thank you. Anybody? Anybody? Any other research scholars? Anybody? Or faculty? Any faculty members? Nimisha, can you say?
Nimisha,
Yes.
you can.
Yes, sir. I now request Dr. M. Bhagleshmi, ma'am, the co-convener of the program, to announce the winners of the oral presentation sessions.
Thank you, Nimisha. So I am very much pleased to inform the best presentations, oral presentation. Actually, all are very good. All the presentations are very good. I appreciate all the oral presenters who have presented today and yesterday for this national webinar. So we have we got more than 30 oral presentation, and then we have scrutinized it, and then we have made it in sections under theoretical chemistry, absorption and membrane catalysis, and inorganic and organic and catalysis section. 4 sections were parallelly conducted for oral presentation, and we have evaluated all the presentations, and we decided to give the best presentation. Best presentation in the sense with respect to time, clarity, the concept they explain, all those things. We have scrutinized, and then we selected 2 from each section, 2 presentation from each section. It doesn't mean that others are not good. All are good, but they are somewhat little bit more than the others. That is what it means. So I now introduce. I now announce the presentation, oral presentation. So under theoretical chemistry section, that is a computational chemistry, from 1 to 8 oral presentation. Miss B.J. Vaishnavi from Purna Prajan Institute, Bangalore, and Deepa Rachel Koshi from St. George College, Kollam. They are selected as a best oral presenters today. Yeah. The next one under the absorption membrane catalysis section, Anjana PM from CU Rajasthan, and Rajamanikam Rajshekhar from VHSN College, Virudhunagar, are selected as a best presenters. And under inorganic and organic section, Muhammad Asin from QSAT and Reshmi G from Amrita Vishwavidyapeetham was selected as a best presenter. Under catalysis section, Anil Singh from Loyola College and Chetana from Purna Prajan Institute are selected as a best presenter. So you will be getting the certificate for best presentation in addition to participation certificate. All the participants will be getting the certificate in another 1 week. So thank you very much. Thank you, Nimisha.
Thank you, ma'am. I now invite Professor Dr. A. Shaktivel, sir, the convener of the webinar, to give the concluding remarks.
Any of our faculty members, any our faculty would like to give any, Dr. Bini George or Bini madam, member like to say anything?
Hello. Sir, I didn't hear you. Sir? Hello?
It's audible, ma'am. You can tell they have network issues.
Yeah. Yeah, this one Department of Chemistry, this in association with ISCA, that this year webinar was very useful, I think, for the research scholars and all the participants.
Yeah, please.
Sir, your network is okay?
No,
Yeah,
we
it's
have
audible.
our university network has some problem, but we are using with the Geo. No problem. Please proceed, madam. Yeah.
Yeah. First of all, once again I congratulate this Professor M. Swaminathan and the convener Professor Shaktivel and our Dean Dr. Professor Ravindra Kurup and co-convener Bhagyalakshmi, because I hope all the students are benefited from this, irrespective of the subject, any area of chemistry, it was very useful. I hope all the this one distinguished people, they will be contacting for their future research and they will help them, and that will be beneficial to the CUK and the other participants. Overall, this one, what I have to say, the program was very good.
Thank you, madam. Anybody, Dr. Ravi, would like to say anything? I think in the department we have some net issue. Can you audible? Can
Am
I
I
audible?
audible now? Am I audible now?
Please. Yeah.
Thank you, each and everyone involved in making this event in the Department of Chemistry, especially Professor Shaktivel, the man behind the show, and also Dr. Bhagyalakshmi, and also the other expertise from the ACT and also the solid state chemistry. And it is indeed a useful chemistry that has been discussed the last 2 days. And actually, to be precise, yesterday I was almost absent. I didn't attend because of some personal issues. But then today, almost I was present, I was listening. And the oral presentations are really nice. And the quality of the presentations are really good. And the other lectures given by the Ajay and Binu and then other people are really interesting. And I don't have much to discuss, and I don't have any hesitation to say it's a grand success. And I hope that this type of I hope there will be a sequential conference in another next year or maybe in the following year to continue this good tradition of discussing a subject under unified theory, a unified subject instead of cutting the seminar here itself. I sincerely request both the convener and then co-convener take up this, and probably in the next year or the following year, perhaps one more conference on the same title. Perhaps it can be conducted as a biannual conference or something like that. I think that's all from my side, and I congratulate Professor Shaktivel and Dr. Bhagyalakshmi and also the other people involved in making this event a grand success one. Thank you, and also I personally I thank everyone because I was made a part of this conference to chairing a session and also the judging the oral presentations. I think the results are already submitted to the convener. I hope that he will announce the results. Thank you, sir.
It's already announced.
Oh, I'm sorry. Actually,
Right, no problem.
my connection also lost. So
Yeah, we also lost connection, but anyway, we are fine.
that's good. All right.
Dr. Deepa, like to say anything? Dr. Deepa? Dr. Deepa, are you there? Okay. I don't know. Okay. Anyway, we thank all of you for your kind support. So now we come to the concluding remarks. The whole motivation by, I have to say that Professor M. Vishwanathan sir, Swaminathan sir, sorry, in 2017 in the Solitude conference to organize something. So we were planning for offline lectures, but then due to the pandemic, we lost a lot of time and we couldn't able to conduct
some network problem is there?
Any conference. So then keep postponed. Finally, hello, can you hear, sir? Can you hear, sir?
Some network problem.
Shakti, internet is okay now. You can connect now.
Internet is okay.
Oh, it's okay, almost.
Just hold. Very sorry for the there was a internet disconnectivity. First of all, I thanks Professor Swaminathan sir because he is a role model for this doing this webinar because he was behind this seminar since 2017. I can say that he was asking us to conduct. So I thank Professor Swaminathan for all your support for organizing this event. And I also like to thank our Honorable Vice Chancellor, Professor Venkateswaru sir, because he is the one always, any kind of academic program, he always support and he can immediately, he doesn't wait for anything, immediately he approve and he always support that.
So I take an opportunity to thank our Honorable Vice Chancellor, Venkateswara sir also, and Registrar, as well as Finance Officer and all administrative members for their valuable support. And I also take an opportunity to thank Association of Chemistry Teachers. Since last 2 years, I am very closely associated with the Association of Chemistry Teachers. That too, also with us, Professor Swaminathan sir only, he has introduced me into Association of Chemistry Teacher. And I found that they were supporting Association of Chemistry Teachers, always support any kind of academic activity related to chemistry, either in the school level or college level or any higher level studies. So I take an opportunity to thank Association of Chemistry Teachers, the President, Professor Brijesh Pare, and the Secretary, Dr. Prabhu, for their always kind support and encouragement. And I also like to thank all the invited speakers, because everybody has accepted with an email or with a phone call. They have not asked, they said that time schedule, everything you fix it. They have not asked me to, they have not asked any demand in the time schedule or anything. They have given me full freedom from the Professor A.K. Tyahi, Ashok Ganguly, Professor Sambat sir, Dr. Kobina sir, Sopna, and Professor Selvam, Professor Veenu, Professor Ramasamy, Dr. Reddy, and Vijay. All of them has given a very cooperative support, and they have immediately accepted, and we have seen that brainstorming programs all the days. And I also thanks all the oral presenter, because we have received almost 38 oral presentation, but then finally we shot out 32. Then 28 has been presented. We can see that all were full energetic and they have presented very nicely. Yesterday it was till 7:30, almost the final presentation was up to 7:30. And I have to thank all the oral presenter for their valuable contribution. And most importantly, the panel members, both our internal faculty members, like all our faculty members was in the panel, Dr. Bini George, Dr. Ravi Kumar, Dr. Deepa Janathan, Dr. Bhagyalakshmi, all of them became a panel member. Along with that, the external panel members, Dr. Raman, Dr. Gulkarni, Dr. Shantpak, and Dr. Yamuna Madam from Amrita, all of them were patiently listened all the oral presentation and given an opportunity for the oral presenter, and they have given a very valuable judgment for their best presentation also. It was a wonderful time, and it was wonderful cooperation from all the faculty members and my colleagues. All of them were very kind, supportful throughout the conference. And the most important thing I have to say that all the participants, those who are registered and those who are presented all the time and interacted, all of them, I take an opportunity to thank you. And most last but not least, our PhD scholars, our departmental PhD scholars, Dana, Nimisha, Ashwin, Pramod, Bhavisha, Neetu, all of them one time or all time, they were coordinating with all the oral presenter, they were coordinating with all the judge panel members, and all the time they were coordinating with mic and everything. So they have done a wonderful job. All of them I take an opportunity to thank. So this event would have not success without the participant interaction. All the participants I take again thanks. And also the technical team members. Actually we had in the beginning also we had an internet problem. Our ICT team, within 25 minutes they have solved the issue, because the first day inauguration day, there was a very problematic BSNL connection had a problem, but then our ICT team, Mr. Srilesh, immediately called to Trivandrum office and made sure that this event would have without interruption. Now also they are waiting for their service. They given, so we have to give the special thanks to our ICT team for their patience and their valuable support. I take an opportunity to thank them. And also the Zoom coordinator Sunny, anytime whenever we call, he always there and he always control whatever the difficulty in the technical issue, he always call and control. So I take an opportunity to thank Sunny. And we could able to see that this event could able to success because of all your coordination. If I go down by mistake, if I miss somebody, please excuse me. And I also take an opportunity to thank our non-teaching staff, Sri Lakshmi and Arun, they were behind all my work. I also take an opportunity to thank. So once again, take an opportunity to thank everybody. Thank you very much. So I can say that the conference successfully completed. Thank you. Thank you for your great support. Thank you. Thank you. I say thanks to my faculty members, all faculty members, and my dean. He always there. My dean, 24, all the lecture. He was there. He attended all the lecture, all the oral presentation. He attended all the things. So he is our inspiration, and thanks. Thank you so much, sir. Yes, sir. Swaminath, sir.
One minute. No, I congratulate all that the prize winners of the oral presentations, and I see that I can suggest, but the execution is done by only Central University of Kerala. So again, once again, I thank only this Shaktivel and all the organizing committee members for giving me an opportunity for ISKCOS to conduct this conference. So, and another thing is that you can have a contact with all the eminent speakers so that CUK can have a collaborative work and later on in the future, make use of them. Thank you very much.
Yes, sir. Thank you, sir. Definitely, sir. We'll take it.
So I request everybody to give the reaction, either thumbs up or claps or any other thing, so that we can take a snapshot and we can use it for our report. So whoever is online, please, I request you a reaction online. Like this, you can see me.
We can take snapshot.
Yeah. Thank you.
Thank you, Dr. Reddy, for joining in the early morning. I think you are there in the most of the session.
Yes, sir.
Thank you.
Thank you, sir. Thank you, Professor Swaminathan, sir. Thank you, sir.
Thank you, sir. Thank you, ma'am.
Thank you all.
Thank you, Shaktivel. See you.
Yes, sir.
Okay,
Yes,
sir.
Thank you, sir.
Swaminathan, sir. Thank you. Thank you so much.
Dr. Ravi.
And
Thank you very much.
okay, sir. See you once again.
See you.
I have to say, Dr. Bini madam was yesterday till evening 7:30.
It's okay. It's our department.
So thank you very much.
Thank you, Raman, sir. Thank you, Raman, sir.
Thank you, sir. Thank you, sir. Thank you very much, sir.
Hello, Raman. How are you? Thank you.
Thank you very much, madam. Thank you very much. Thank you.
Raman, how are you?
Fine, fine, sir. Thank you very much, sir.
Thank you, Veer Singh, sir. Thank you.
Oh my God, I'm also going, because rain is coming. I'm also going. My sir, while seeing rain is coming, my sir ran away. No, I'm going.
Sir, sir, we can stop, I think.
And now, I'm deactivating the YouTube live also. Thank you, ma'am.
Certificates will be issued. Your email ID is there. E certificate will be issued to every participant.